think I especially thinks special things.
Special things.
Thank you.
Yeah, for sure. Do you have another for me? I think I should go buy one. Did you create one to DRL? Guys, put the bags there. Put the bags there because there are not too many people. I hope so. If it's empty, then it's fine. What do you need? Phone.
We better have another two computers prepared for the meetings.
Yeah, but mine is being
I updated it at least. Top of the place. There was one page missing.
Now when Ruchandra comes, we take a nice picture and then we start. Without people, I mean. I want to go through, yeah, let's go through. Put everything in. Oi. Deformation. Okay, you do it. Try the microphone. Try the microphone.
Hello.
Don't forget to put the phones away because I think they create some kind of. Sí, hello, go ahead. He gave you a USB, but I don't know what it is. She gave him a USB.
What? USB?
She. Our face is a poem.
second link, it's the day 2 one. Oh, yeah. Alright then. Did you get a laser pointer?
No.
Working?
Yeah, ready.
Me?
Yeah, thank you. production today also? Is there also an introduction? It was on the schedule.
Yeah, there is because there are new jurors and
So the same stuff tomorrow. Oh,
it's gonna be like Pat yesterday.
We're gonna be going there. Huh? What happened with what? Bad. Bad. I don't know what you're talking. Shit, it's coming people, huh? It's just 10 to 10. No, for you it's fine, thank you. No, it's fine. If I just take something, I just throw up. I am sure about it. Guys, I want to take a nice picture once Ruxandra come with all the things. Come, say. I was thinking, I think I recognize that. You put it, no? Yeah. Actually, she. It's fine. This is water. Yeah, leave them on. It's fine. Not don't worry too much. You cannot find them? They were there.
no.
They took them. Yeah. Yes. They're gonna burn.
should be. Now you can put this the crits.
The critics.
Yes.
Yeah.
Is this here? Starting at 10.
It's starting at
Ten thirty.
just introduction.
Ah, yeah, probably.
Hi, how are you?
I don't know why he was asking me. What are you asking me? These ones are probably just like 16 to 21 kgs. Ponlo aquí detrás. Nice ones, please. Cogerle sitio al papá, por favor. Thank you. We might need it. It's me. Alexandra is printing. She has been printing like for... No.
She's printing like.
In the computer lab.
Oh, okay.
I need to sit.
PowerPoint. It's on your desktop. Yeah, it's on the desktop.
On my desktop.
Yeah, on your desktop. So it's final draft 2. It's like everyone recognizes my parents. What's happening? It's not there?
Central, I find it. Yeah. Where is it? It's here?
No, it is. Yeah. Wait, let me see.
It's a title.
This goes west.
This goes last.
Okay, should we go west? And we can take this one out.
This one.
Yo tampoco, mami.
Okay. Already. There is.
I think it's from 10 to 10:30. You want me to ask Theo? Ten on 10. And it's already packed. I mean, not too much. Option? Yeah, can you bring when you come back water? Much more? No, a little bit more. Okay, I will. Just here in the reception.
super tight, and we have to have a kind of quick turnaround. So if I could just ask people to just scoot the chairs a little bit back so we can get a couple more edges here, that would be really good. Sorry for the inconvenience, but it'll make a difference. You guys okay? Ready to go? Okay, so you guys.
It's gonna be an introduction, right? Or no?
You guys have 20 minutes after you finish the presentation. That's what I want. So here in front of you. Gonna be fun. We'll have a great time. I'm happy. It's gonna be great. It looks good.
Breve. Empiezo en breve. No empieza Roxana, luego yo. Porque quiero ponerme a ver cómo se empieza.
Okay, thanks. Thanks, everybody. Hi, guys. Welcome. Good morning. It's all of my crew over here that's chatty today, which is good for conversation. Okay, so I'd like to welcome everybody to round 2 of what's been a 2-day event here at the DRL. My name's Theodore Sparopoulos. I direct the course, and with a group of faculty and distinguished consultants and distinguished critics, we try to have a kind of open platform for a conversation about a lot of the subjects that we've been exploring. Just to give a bit of a window, today is also the AA's Open Day, so we have prospective students that will be coming in, and if there's some here today, just to give a bit of an overview, the course is a 16-month course. For those that may know, it's a design research-led course. It's exploring ideas of computation, making, prototyping, and trying to think about new systemic ways of kind of evolving, let's say, the project of architecture and urbanism. What we've been working on and the way that we situate research is explored over 3 to 4 year cycles, these kind of umbrella agendas that we have, which are basically situating certain problems, asking particular questions, and creating a kind of open framework to evolve some of that conversation and dialogue through project-based research. What we've been working on for the last couple of years, this is the second cycle of an agenda that we're calling behavioral complexity. And it's really about exploring ideas of scenario-based design, exploring ideas of time, agency, materiality, forms of production, with a particular kind of emphasis using kind of new technologies of robotic production, situated kind of technologies, etc. The projects that you're going to see today have 4 different research strands, and they're run by different tutors within the course. Patrick Schumacher with Pier Andrea are basically developing a strategy of parametric semiology. They have a very case study kind of research that's looking at the design museum as an operational kind of platform to explore kinetic architecture, as a work environment that's dealing with aspects of communication, exploring different ideas of crowd simulation and so forth. We have a studio by Rob Stewart-Smith and Tyson who are exploring aspects of swarm printing, looking at how drone technologies could actually afford us a kind of adaptive model that can be distributed and deployed, thinking about how drones could actually be part of the 3D printing kind of life cycle of thinking of a kind of system that is evolving and dynamic and dealing with phase change. We have Sajay Bhushan, who is running a studio with Alicia that is looking at robotic fabrication from a production cycle and automation cycle, reconsidering the robotic arm as an instrument, developing custom end effectors, and particularly looking at plastics within the domain of architecture in a case study scenario that is being explored as a prototypical house. And myself, Theo, with Mustafa El Said, we're exploring aspects of behavior that's relegated to high population soft robotics, and how that can have a kind of evolving ecology of machine and man as a kind of formation-based strategy of dealing with population, mobility, and self-build systems. Through the day, you're going to see a sampling of each of these. We had yesterday 6 teams. Today we have another 6 teams. So we'll do, the schedule for today is to do 3 projects in the morning, have a break for lunch, about 45 minutes to an hour, continue with the other 3 projects, and then we have a keynote lecturer tonight, which is Elias, who's one of our critics that has come from Germany, from Festo, who will be giving the keynote lecture tonight at 6 o'clock, which we ask you please to attend, more than worthwhile. So if I could just quickly introduce the critics, and then we'll get the show on the road. We have Jelle Peringa, who's joining us. He is part of a company called Odico, a robotics production automation company, and also a PhD student at the Hyperbody Research Group. We have Mario Campo that is joining us from the Bartlett, a distinguished professor, Rainer Banham, professor of history and theory. We have Elena Manfredini, head of Manfredini Studios, and also longtime faculty at SciArc. We have Ed Mosley, who's joining us from AKT, who also works with our students, engineering consultant. We have Carol Scott, who's joining us again from yesterday from Tate Towers, part of the company that was presenting yesterday some of their research in automation, engineering, and call it spectacle live event design. Lias Nubend from Festo, head of Bionics, will be giving the talk, as I was mentioning. and Neil Thomas, founder of Atelier One. So with that, my introduction is completely over. Students are going to be presenting for about 20 minutes. We'll have 25 minutes of conversation and about 10 minutes for a changeover. So after every presentation, we'll just ask if you can keep these kind of thoroughfares a bit clear so we can basically put up the next team and kind of continue the cycle. Okay? So welcome everybody, and yeah, with that, the first team from Saji's team.
Thank you. Good morning, everybody. Let me start by introducing ourselves. I'm Roxandra. We have Marta, Vlad, and Lee. And together we are Team MRBL Growing System. We are part of Saji Bhushan's studio, and we will be looking at robotic fabrication as an innovative catalyst for architecture. So, in contrast to the rigid and static architecture of today, we are proposing a system of elasticity, one that can accommodate parameters of site and weather, while allowing spatial changes to occur over time. The method introduces robotic fabrication as a hybrid system, combining the precision of prefabricated elements with the adaptability of on-site fabrication. Different techniques of spatial extrusion are integrated with the behavior of the material to drive a process that eliminates the need for scaffolding. In doing so, new levels of design complexity can be reached.
We started a spatial extrusion demands materials with ability to maintain its shape as it's deposited, and also ability to create strong connections between elements. We research various material types such as mineral materials, foams, and plastics. Plastics has an advantage of creating better connection between printed parts, and unlike other materials have subtractive capacities. We are using polycrolate tone. It is a phase-changing material. Main advantage of this plastic is strength, flexibility, low melting point, and biodegradability. Main challenges is that significant amount of cooling is required for the process, and deformations are inevitable. In order to improve material behavior to the mixture, was added 10% of microspheres to reduce deformation and 1% of pigment to improve scanning. To be able to better understand performance of the material, we did a series of compression tests. Material doesn't break even after load 10 tons per second. After the test, material returns to its initial shape.
The main challenge of the material is its deformation. In this experiment, several self-supporting elements are created due to this feature without any control. Therefore, we were trying to minimize it by using different techniques. The first one is by adjusting the temperature of the heating device. All the experiments were in a range between 70 degrees that allows malleability and 210 that makes it extremely uncontrollable in terms of deformation. The lower the temperature is, the less it needs to be cooled down. After considering the previous experiments as an important feature in our research, we also decided to look into additional cooling strategies. Several systems as vortex tube, water spray, and freeze spray have been tried during the process with quite obvious discrepancies. We realized that the best option to control the significant deformation of the material is by using high cooling device that reduces the temperature up to -15 degrees. In order to start generating different geometries by extruding polycaprolactone, commonly known as PCL, we consider extremely important to test different angles during the printing process. The result is that the lower the angle is, the more the deformation needs to be controlled with an additional cooling system. This is a load test made to elements with different heights. We figure out that the optimal distance of elements for interconnections varies from 6 to 9 centimeters. These ones are capable to stand from 16 to 21 kgs.
We have started digital and physical exploration of geometry in parallel. On the physical side, we were researching material-driven systems. On the digital side, we research systems that are capable for creating a complex, adaptable structure that have a capacity to utilize material behavior. The final system is compromised between a generative algorithm, robotic constraints, and material system.
After taking into consideration all the previous tests, we analyzed different vertical strategies with PCL. The first one is made following a sequence from the central point to the external ones. This allowed all the vertical elements to be connected to each other, giving some stability and rigidity to the final structure. The one in the middle was made following a continuous extrusion from top to bottom and bottom to top. The connections between vertical elements were also made during the continuous printing path. The model in the right was made by using material behavior. We decided to consider the natural deformation of the material as an instrument to create self-supporting structures. The top grid was printed first and then lifted a certain distance in order to get some thickness. Then the dropping stage starts when several vertical elements are created after the deposition by gravity. In order to develop further the geometrical research, it was important to test the previous elements structurally. This was an important stage when we checked how many vertical elements might be needed and the amount of connections for the whole structure. We realized that to stand 72 kgs, 12 vertical elements are needed. Based on the structural and geometrical tests developed earlier, we made the first large model, 2 meter height. It follows a similar sequence that the previous one, with vertical elements that are twisted and connected to each other. The deposition sequence was simple to be executed, and the material behavior helped it to be printed from top to bottom. Once we tested the vertical components in PCL, it was important to check also different spatial arrangements of individual components using polylactide. This material is commonly known as PLA, and it has a similar behavior than PCL. Its properties allowed us to make in a smaller scale different structures.
End effector is a universal extruding platform that allows to be modified according to changing requirements of the process. It allows to change nozzle depending on required deposition strategy. It also has control over the temperature and speed of extrusion. End effector becomes a part of a smart system where elements of the system are capable to exchange data. We have studied different ways of depositing material, from single to multiple nozzles. Multiple nozzles allow to incorporate higher grade of emergent material behavior. However, it makes not possible to create a system which capable for responding to complex parameters. Single nozzle with variable extrusion thicknesses allow us to have more control over extrusion, which creates a complex system with more predictable result. For creating enclosure, we are using a flat nozzle that allows to create surface evenly with width 11 centimeters.
The design of the extruder allowed us to create models in real scale without robotic control. In these experiments, we could check the printability and precisions of the system that was divided into 2 stages. The construction sequence starts making a horizontal slab that will be lifted in order to start with the vertical extrusion by twisting and connecting. Another important aspect of our project is to create enclosure. An adaptive stretching technique has been developed in order to create habitable spaces. By applying different layers of extrusion, it's possible to control lighting and privacy.
To accommodate the phase-changing material behavior, we are looking at slide mode simulation as our generative tool. As a single-cell creature, slide mode is able to collectively perform intelligent behavior. It is able to search food sources in complicated environments, then establish efficient network structure to transport nutrients. Most importantly, the network created by the slide mode could dynamically adapt to changing environment. Our digital simulation of slide mode is based on interaction between slide mode cells and its nutrient environment. The slide mode cells are able to navigate themselves to the area with higher density of nutrients. At the same time, they leave their footprint in environments by releasing same kind of nutrients to attract other cells to follow. When simulation started, the slide mode cells could quickly self-organize into dynamical network structure. And in next step, we set up our intended load points and support points as food sources for the slide mode, regarding the slide mode path as our printing path, training the slide mode to create a realistic printing structure for us. And to figure out the proper parameter settings, we did large numbers of experiments regarding on different parameters and the initial input of food sources. We have run series of the tests on geometries generated by the slime mode simulation. The most important tests are printability test and the structure test. The printability test is checking how much percentage of the geometry could be printed without colliding into each other. And the structure stability test is checking how much percentage of the printing paths are well grouped with each other to prevent bending. These two tests tells us a controversial fact that the most structurally geometry are usually more difficult to print. The most printable geometries are always not structural enough. Thus, it will always be a negotiation between printability and structure stability. And informed by this test, we confirm a range of parameter settings in which both printability and structure performance are acceptable. And these structures were initially generated by the code. So we tested the printability of the simulation path manually by PLA with different kind of bracing strategies.
We've also started looking at how to print these structures in large scale, and we understand that the abilities of the robot are crucial for our design. We've done multiple reachability studies to see what the robot can print from one location when rotating around its axis and when moving on site globally. And we pinned down the basic types of printing paths that are accessible for the robot and the heights it can reach. And how these paths can start creating spaces by having the robot move around a specific point 8 times, 12 times, 24 times, and seeing the types of spatial qualities we get. We also realized that the robot is able to print paths that are twisting. However, the more twisting, the smaller the diameter of the printed element in order to avoid collision with the geometry. And we did a series of arrangements to see how these elements could potentially be placed, minimizing the movement of the robot on site. We're also looking at the idea of collaboration between two robots, and we did a series of studies by placing them in different arrangements, whether they're perpendicular across from each other, aligned, or angled. We realized that by putting them at an angle, we maximize the reachability area while lowering the risk of collision. And we took all these studies and started printing a real prototype.
Prototype is application of the system in one-to-one scale. Firstly, generation of printing paths based on the input. Then data is sent to the robot. Next step would be printing the base. Then all the prefabbed components are printed on the flat surface.
The prefabbed components will be lifted into the position and the robot start to connect the prefabbed components and the base. After executing each printing pass, the printed geometry will be scanned back into simulation. In real time, the slime mode network could adapt to what is printed and suggest the next printing pass. Furthermore, for each printing pass, our program is able to plan optimal robotic choreographies to avoid colliding into the environment and the printed geometry. And by comparing latest scan with older ones, the program is able to figure out precisely the bracing paths to enforce the printing geometry. Thus, the system always processes in an order of generating, printing, scanning, and regenerating according to scanned data. So these automatic feedback loops give our system great flexibilities to respond to all kinds of unpredicted situations. The outcome is an emergent result from algorithm, material, and robotic behavior. The final geometry is a 1.8 meter high self-supporting shell structure. It is printed in 12 robotic hours, and the total weight is only 35 kilograms. Actually, we carried it with a small suitcase. And combining the previous knowledge of digital and physical research, we started to develop a catalog of basic elements that we can actually construct by our system with minimum movement of robots. These elements are divided into 3 different main typologies. They are columns, apertures, and shell structures. And knowing the total length of the printing path, we could easily estimate the printing hours and the material cost of these elements. As a result, all of these elements, all of these around 3-meter high structural elements could be printed easily in 2 days with a material cost under 300 British pounds. And there's another catalog showing how to generate and construct staircases by our system. Again, the results are highly time-saving, cost-efficient, with a unique beauty of form. And furthermore, the nature of our system allows us to easily combine and merge different topologies together. In this case, we are adding a suspending spiral staircase under an arch structure. The simulation shows how these 2 elements are generated and constructed in sequence.
One of the main challenges of the project is to keep emergent nature of the algorithm and material and to utilize it to a certain extent where a system still has the capacity to change dynamically but able to accommodate structural and programmatic requirements. Elasticity of the material allows us to resist the pressure of elements and structural load. In a system, elasticity is not only a feature of material but also elasticity of the architecture, allowing us to be highly adaptable to the context. We have studied various cases of context. 5 main of them is 1 neighboring building, open space, vertical elements such as trees, 2 neighboring buildings, and slope.
Now taking a look at the full system in action. As mentioned, we are proposing a hybrid system that takes advantage of the precision and variety of prefabricated elements and combines it with the flexibility of on-site extrusion. The sequence of construction involves prefabricated flooring attached to a PCL foundation, then a robot holding prefab elements while another connects them in a spatial network. We are envisioning having 2 robots collaborating at the optimal angle previously mentioned. And the robot will start to print the paths furthest from itself and moving closer as a strategy to avoid collision with the printed geometry. And while the printing path generated by the algorithm can adapt to any type of context, like the slope and the trees and having neighbors, the enclosure can also have different levels of opacities, allowing practically for an infinite range of design possibilities. In looking at how 2 units could interact within the system, we are starting from different initial conditions, and we see how one house can grow while the other shrinks, forming an efficient and balanced system where the material can be exchanged within the system and allowing for maximum adaptability.
The research allows us to speculate about architectural space at the scale of the house that can form complex growing systems. Thank you.
Taking a look at the models, we have the large prototype.
Use the microphone. Yeah, they can use
The large column showing the twisting strategies. Over here we have the surface test using the material behavior for deformation. The compression test we've done. The series of PLA models showing different bracing strategies and structural systems. Another surface element combined with other components. The powerful end effector that we have used all throughout this process with the multiple nozzles, the one in the center being for surface. A catalog showing the components, the ability of the system to create dynamic components. Strategy for placing the houses on site. And over here in the corner, we have the large prototype, which has been done with the robotic arm. Thank you.
Yeah, you start, please.
Nature took nature millions of years, billions of years. And you've done it in 16 months, you said? I'm an engineer, structural engineer. One of the things that we try to do a lot, regularly in the kind of projects, is find ways of placing material where you need it. Because by doing that, it means you use the least amount of material. It's a very difficult thing to do, and you've managed to achieve that. I really liked the way you've gone through the process, how comprehensive it was, the way you tested the materials, looked at different, engineering testing them, compressively testing them, the nozzles, the whole variety of nozzles you've got, and this whole mixture enables you to create a multitude of forms, structures, and surfaces, which are really, approaching that point where they are optimized completely, and I would just like to see the thing continue, to keep going with it, because it seems to me then you start to talk about the surfaces, you apply the surfaces, you make those composite with the frameworks underneath, you approach a whole new way of doing things altogether. So well done, it's very good.
Sorry, I have to intervene on this. I mean, I appreciate the project a lot, and I think there's a lot of intelligence, a lot of innovation in terms of the process you're proposing, and there's a lot of intelligence about the kind of readaptation through scanning and rerunning the slime mold, which has to do with inherent vicissitudes of the process, not something an inherent advantage, but it's a relative advantage. But I want to say you're overselling the project, and I think what Neil was just saying is overselling it by kind of criminal amounts, I would say, because we got to be honest, right? So the innovation is in a totally new process, and we have to see that what we've reached with it so far isn't yet competitive. These structures are far from being optimal. They're incredibly soft. This piece is non-viable. It's inefficient. These models are incredibly soft. And I think so first of all, we have to kind of be honest with this. And because if you stop overselling, we might also then make another version where we really want, for instance, stiffness out of this. So that's something, it's just the principle of this. And that doesn't take away from the research, right? Because it's just a more honest research, and we don't have to expect in the first iteration of this, a high performance or even a better performance. This will be non-competitive for quite a while. But we know that the hypothesis is, and the intuition is, that if you keep going this way, we will end up doing something more sophisticated, lighter and cheaper and better. But we're far from it. There's one point I really wanted to stress. But I had a question as well. When you said, I like this in fact, where you said, there's a certain structural, the slime mold is an algorithm, it isn't a structural optimization algorithm, it produces something which then can analyze relative different outcomes with this structure. And there's a range, and then there's printability potential. It has to do with the robot arm reaching, and reaching back, connecting things, and so on. And I just wanted to know, what do you do with the 60% printability result? How you continue from there? It doesn't have to be 100% printable for your process.
How we are using slime passes that we generate a huge selection of possibilities. And we do not have to print all of them. Even half of them or 30% of them already fulfill the structural requirements. So it's like a collection to choose.
No, but what I'm saying is, you said 82% printable, 60% printable. Yeah. Don't you need 100% printable in order to print?
I think just to clarify that particular printability aspect is because they generate like a lot of paths, of which 60 are printable, and you don't have to print all of them. to satisfy the required amount of material. Like, so it's from all the paths that the slime mold generates, 60 or whatever percentage is actually printable, but maybe, yeah, 60% of those paths are 100% printable. Yes, that's.
Just to understand, the parts that are not printable, it is because the geometry prevents the nozzle from going there because the path is not optimized. That's
In terms of reaching.
Reaching back.
I have a simple, banal question, but I shall wait.
So what I think is powerful in the project and strong merit is sort of the conflation between geometry, generation, material constraints, you know, the ability of the robot. You deal with this in a holistic manner, and I think that is really appreciated and very interesting. I was excited by the surface extruding. That's a new outlook, and I really appreciated the printability slide. It gives it a weight and a kind of seriousness to the project. That was beautiful. The integration of kind of the feedback with the robot, very useful. That's also what I mean, that let's say on a technical level, you succeed to cross the boundaries between the technicalities of your fabrication methods, you know, and its material properties. Though on the material quality, PLA, BWAX, that doesn't really scale. So, for instance, on some of these models, which are really delicate and of a sensitivity that's fantastic. Have you considered, for instance, you know, what's great is that, you know how you do bronze casting, right? Bronze casting, for instance. Imagine that with the beeswaxing, it's completely compatible with that kind of process. So imagine that if you, I completely underscore what Neil was saying, keep going with this. Why not make these kind of shapes that we see here are suggestive of furnitures, right? Do it in wax, cast it in aluminum, anodize the hell out of it. It will be cheap, it will be incredibly beautiful. I would like to have one. Yeah, it's right. So use your printing for a next iteration in your materialization, and you could go really wild on that. Yeah.
I think there's some really strong research that you've done, and I think there's some really great work there, and I encourage you to keep going like everyone else. One of the things I think you should be recognising, like Patrick said, is the limitations of the material, and what you've undersold yourself on is the ability for this to create an enclosure where you don't actually have to support that much weight. So going into things like staircases and things where you have a performative parameter that perhaps this isn't the right material for is perhaps something you should maybe move away from, and look at the ability for this to create an enclosure and create it in places where you don't have to, where you have limitations on access. So I think when you started to look at prefabricated elements, I think that was maybe the wrong route. There's something nice about this being able to be created on site, deposited on site, and adapting to the surroundings. But I think, yeah, I think this, you need to do quite a bit more work into the surfacing to make that true and make that a real sellable product. How did, the surfacing was something that you kind of brushed over a little bit in terms of the work that you did. Were there complications with this, or were there issues with actually creating a weatherproof environment and control on that?
It has the capacity to do that. We've only started researching that part, but as you can see, it uses very well with elastic elements, so it has that advantage. And when it comes to waterproof still, it has to be very careful. The next stage of development.
I think it's a great place to apply it. I think it's one of its main strengths, really. If you can solve that and get that surfacing working well, then it gives it a lot more applicability to lots of different things.
I think it's really interesting piece of work, and I think it's the first time that I've seen any of the students actually put technical data up on the screen and show the commercial viability, and I think that that's really important, because that's really what the end game is. It's about how we're going to sell this to the world. I think really you should take it to the next level and say, this is the weight constraints, this is the weight loading, this is how much it costs, this is the height it can go to, and then draw a comparison with conventional methodologies that are out there so that your client can see the added advantage, because that's what we're all doing. We're showing everybody that there's a problem, we're showing them that we have a solution and that our solution is better, it's cheaper, it's more practical, and that's really the end goal of everything. And I think congratulations to you, you're the first team that's actually kind of got to that point, so I think that's very commendable.
I also very much like this project. Again, the process was already set, coming from material science. In the very beginning, you had a lot of random situations, working with robots in hand and both together. So, but what I really like in your visualizations, as well as in your very small studyings, you always imagine that it can be very beautiful, and finally you get a really new aesthetic, and bringing both together, on the one hand technical research and how to make these nozzles, but always having the big picture in mind. How will it look like in the end, and what can we achieve? I think this is a really good way to work on this. Congratulations from my side, especially as you said also, it's the first time that I have seen that someone printed surfaces, just not layer-wise, but at once. And I also would recommend to take a lot of more effort into printing surfaces. So this is, in my opinion, very new. I've never seen this before.
I mean, just maybe from my side, I think the project's commendable on a lot of levels. I think the question of selling and buying is a conversation that people can have, but to be honest with you, I think the important part is a form of discovery that actually has implications that are meaningful. So for example, you designed an end effector to augment a machine, and in the nozzle distribution, the real-time augmentation of its inexact forms, all of that aspects, I think, give the possibilities actually for you to think in a much more multi-material way. So how we can evaluate the status of the materiality is something that I think is an open question, but one that nobody can sort of take away from you as a kind of acknowledgement of your deployment strategy computationally, and also the machining strategy, and how that fitness criteria affords us the possibilities to do some of this. Beyond that, I think like the surfacing of this stuff and the enclosure, I think you can start to think about designing machines to actually do that better. So for example, the same way you designed this and you took a certain approach to it, you could consider different ways of heat shrinking things. You could design techniques that actually make more viable what an actual enclosure of this is. So for example, at the moment, it's a kind of surface wrapper, but you can imagine a much more intricate, kind of breathable kind of system that really takes advantage of this. It's not a surface, it's a lattice. It has variable thickness, it has other opportunities, which I think you can make the argument give very different affordances. I think it's your obligation to give legibility to that. I also think as a new generation, you have to sort of confront the older generation with a certain attitude and conviction that says that these things are more than just a random taxonomy, that they actually do have some purposeful ways of developing criteria to evaluate, but they challenge assumptions of just the appearance of things. So I really like, to be honest with you, when you actually build in the vision system and the feedback loop of the machine, and you start to give these things agency, because I think they're a design agency, and that I think is part of where we can really try to understand a more behavioral way of dealing with things. If the houses that are sitting next to me are sort of set for put on the market and to see if they can compete, then I think obviously there are some questions to be asked, and obviously those are challenges you should take up. But I think, generally speaking, the emphasis hasn't been on this. I think this has just been a testing of basically what an enclosure could be. And I think it's up to you to sort of wait where all of this world is actually situated. I think the document that you're going to develop in the next 2 weeks will be a good reflection on what this conversation could be. I think all of the comments, are very meaningful. But I think honestly it's your obligation to state that this isn't just another system, another production, or just because we have accessibility to robots, that we're going to use robots as a kind of new tool. So basically, more of a provocation for you to take a greater sense of urgency to really think about really what opportunities are afforded by the way of thinking like this. I do think this idea of on-site, the continuity of printing, are things that are part of your domain that should be dealt with. And I do think the fact that you actually thought about enclosure is really meaningful. This isn't just another pavilion. I mean, looking at it, it could be, but I think taking some of those aspects into consideration, I think, is really important. And for that, I commend you.
I really appreciate the aspect of the project where you're looking and inventing in the production process. Like, so I think it was quite a mature step to actually mix the prefabrication with the on-site additive manufacturing, because when you first show like the construction time of this piece, 3D printing is a slow process, but that's still quite, sorry, it's a slow process, so that's relatively fast compared to a lot of other 3D printing, but it's actually still incredibly slow to what's going on now in the world of prefabrication with companies like Langer Rock building whole like rooms in 15 hours, right? Like relative to non-additive manufacturing, prefabrication is slow. Having said that, you managed to speed it up by mixing in the prefabrication with additive manufacture. So I think that's a really good aspect. But by doing that, you're also arguing, I understand, that it's an on-site construction process. Is that right? Yeah. And that's why the geometries that you produced and all the catalogs are kind of trying to optimize what you can do within the reach of the robot and everything. And I think you've done that really rigorously. But I think it then raises the question, for the scale of the human, what is better, to constrain to the scale of the robot reach, or to actually prefabricate or use multiple robots in such a way that you can do things beyond the reach of the individual robot? And I think that's something I would like to see in your book document, an exploration of how you go beyond the scale of the individual reach of the robot. Because what I see, every cross-section is limited to that one work envelope, right? Even the kind of the torus thing is based on the reach of one robot, which means we're limiting ourselves to fabricating something only at the scale of an individual room. And it'd be really nice to see how you deal with, when you have such an interesting and inventive structural system, how does that structural system actually put itself in doubly or triply challenging situations? Does the slime mold algorithm work the same way, or does it suddenly have to, you know, how does it deal with depth, for instance, the slime mold algorithm, or is it simply dealing with path optimization? So if you suddenly had to triple the span, what would it do next, and how would you deal with that? I think it would be a very interesting thing to see.
I just want to come back one more time to the goal setting and the tenacity with what we want to reach certain standards. In terms of structural stability of this. I mean, the material is relatively soft, but there's a lot of also at a miss in terms of the networking of these lines. If you have a kind of structure which is only working with lines and relatively thin lines, you found to some extent there's a lot of triangulation because you figured that one out, and the kind of zigzagging between two lines creates a kind of trussing. Of course, then you have the drooping, which becomes sometimes so strong that this is countervailing this. Of course, you could go onto the ground, and that, you know, when you print on the ground, you get these triangles and you lift them up, but you have kind of left it quite vague. So this thing is not stiff at all, right? So you didn't aim for stiffness in such a structure, and so it doesn't come in. That's why I'm a little critical of this. And then I think in terms of the surface, we all love them, and that's one of my favorites as well. But I think it could also play a structural role in terms of a monocoque, a kind of structural surface, because you get the very strong binding with the thing, and that needs to also be requested. And that needs then, when you look at this, it also needs, you know, those zones where there's very large areas, and this becomes super thin, then it loses that quality. I mean, you haven't discussed it this way, so please, in a little bit, because you could have done it, right? You could have been more serious about it, but you weren't. And that's a bit of a criticism. You know, again, I mean, the project is wonderful on many, many levels, but since you make structure the topic, you have it in a loop of analytics, but then you kind of trust the kind of atmosphere here that we don't take you serious on it, but I want to.
Can I? Oh, sorry. Go ahead.
Yeah, just to continue from what Theo and Patrick were alluding to, I think there is a sense that what they've achieved with the material they had at hand, I mean, there's nothing preventing the material to be further engineered. So it is trying to attempt to deal with the kind of negotiation between a human designer and what the machines will produce. And there's I understand that the structural aspects are could be taken a lot more seriously and kind of make that the central focus. But at the same time, there is a certain design aspect here, which relate to how humans and machines could collaborate to design, as opposed to humans designing stuff and machines are used only to produce the design. And that's also something I think what Theo was mentioning about design agency, that you enable the machine to be able to produce something physical and have some amount of decision making, which I think that's something that I would like to see also kind of clearly articulated in your thesis book. I mean,
the way I want to I think it's a bit of a you're winding yourself out of the point, and I think what I would like to see perhaps is then a certain comparative model of a structural optimization network. I don't get so much on the material. I won't focus on the material. I'll focus on the networking feasibility relative to material, of course. But you know, this is also more of a network topology concept, and then one can compare that with respect to, for instance, how if the machine can meet the precision, where does this lead to in a series of deviations and compensations relative to this, or if there are printability compromises. You know, but you need a comparative setup and system which will be optimized, where some of these constraints which we have in terms of, let's say, precision and arm reaching are overcome and not there, and then you work against that. For instance, I mean, the methodology at the moment is not rigorous enough. So in a practical context, it would be much clearer where you would have to be with this. But since we're not in a practical context, we got to make, you know, we have to kind of self-impose.
I think it's very important to be clear when we're discussing the idea of optimizing structure, that actually you have the possibility here of doing just that. And you haven't quite done it, that I accept. And there are certain things about it, like the hanging things. I'm surprised that you've allowed that to go on, considering you found the mechanism of cooling these things coming out straight, which I thought was very interesting, the fact that you understood that. And part of this 2.5-week exercise should be to do just that. Patrick says, for me, these are great, you know, these are things that I would be interested in pursuing as an idea for forms of structure, the idea of combining the surfaces. You do need to think about precisely where you are placing the material and why you are placing it there, because I think it is slightly random at the moment. I mean, you understand intuitively what it's doing as a structure, but it needs a little more rigor to it. So, but I think with that in mind, you could achieve optimized structures very, very easily, and structures which are very light. I mean, what was the line Buckminster Fuller said to Foster? How much is your building weight, Mr. Foster? The fact that you're talking about the weight of these things is quite interesting. So I would just push ahead with it and try to pull in a little more engineering.
It seems to me there is a protagonist of your game which we keep forgetting. We talk about the designer, we talk about the machine, but the real protagonist of your game is the material. This is a material which has a spirit, in a sense, which behaves in its own way. And you have tried to model it, because you had your geometrical simulation, which is extremely precise. It is as precise as if your material were stainless steel, but it isn't. So when you print it out, there are plenty of things that happen. You have referred to that. So my question is, to what extent the model which you used to define the geometry and which to the limit you could use to optimize the geometry in simulation, to what extent does it correspond to what happens when you really print it out? Because when you print it out, this is closer to chewing gum than to stainless steel. It will deform plastically in a way that you cannot model. So the only way to know what you're going to make is to make it and then to look at it. But then at that point, you probably would have to rescan it, because what you have made is quite different from the geometrical and structural model you had first conceived, etc., ad infinitum, because then, when you apply some load, something else will happen, etc., etc. So there is a component of randomness and indeterminacy, which is, in a sense, the most important protagonist of your game, because it is out of control. How do you control that? Question.
I think our answer to that, like firstly, the material is extremely hard to control. It's a dream to make it precise. It's like all of the factors affect the behavior of material. For example, yeah. It's even the angle of the extruder affect the solidation of the material. So I think that the only way to respond to that is aiding this feedback loop that you can accommodate this unexpected stuff.
There are more ways to respond to that, though. I think this point is really important, but I think this idea of control is a bit of an illusion, and it's a bit of a trap. I don't think you go down this world to try to find fixity and finiteness. You go down this world because you're interested in behaviors, and you're not trying to control them, you're trying to explore them. And to explore them in a meaningful way also makes important that you make meaningful distinctions. There's a difference between a model of something and a model for something. I think you're working in a world where you're not trying to model what it is, you're trying to model a kind of set out and to find a feedback loop that allows time to really participate and treats materials not as inert things. So for example, that noise has to be creatively explored. If your world is only about optimization and you appropriate this kind of language strongly, that means something very different in an engineering discipline, and it also means something different in the way that I feel you're trying to explore it. And that has to be somehow unpacked in a way that you could find language that may be more appropriate. Because I don't think it's just a communication issue. I think fundamentally, like Lee, when I listen to you, it's not the dream to control everything. We're not here to play God. We're here to sort of participate, and honestly, like, materials have their own behaviors, and Mario is bringing, I think, a very important kind of light onto these things. They have agency, they have their own life cycles. They don't want to play nice. You don't need to domesticate them. You could liberate certain aspects of them, and you can bring them into the domain of spatializing them. Where I find your project limited is in the spatialization aspect, because I think that would also make you have to find very clear ways of working with the material to achieve things like openings, porosity, ideas at different scales of that, right? I mentioned breathability, but what an entrance is in your world, what a window is in your world. Is this a completely translucent building? Lightness is a most interesting aspect of your building, but at the same time it brings challenges. How does it get tied down to the ground? Does it need to? Is this a fully kind of monocoque kind of strategy that has different kinds of ideas of distribution? All I'm saying is like these are important questions for you.
I think some of those questions you raised now were actually addressed in the video, but I think the video you showed in the last part of your presentation was inadequate in other aspects, in the sense specifically on the technical aspects, because you certainly all of a sudden you raised this question of prefab elements, and let's say all of your presentation is technically really articulate, but the video was quite vague in that sense to me, because you could also read a completely different kind of implementation of the fabrication strategy into the video. So perhaps a bit of practical advice would be to get that sharper in the coming two weeks. I think that was really less articulate. And it was a bit distracting from the architectural proposition put forward, because, yeah.
I think it is important to point that there are inherent vicissitudes and deviations, and then there's a drooping. The drooping is the moment just comes along as a deficiency, right? So maybe then one has to, if one focuses on this, someone has to find ways of making that an advantage. You know, there's a lot of areas in architecture and structure where curves are desired, and where we like this idea of having a non-foam work ability to generate, for instance, curvature and complexity, but you haven't found it this way. Or it's there, I mean, so we know it in the abstract. In the reality of the project, we have to admit these things at the moment only come along as deficiencies, deviations which I can compensate for. There's an intelligence, but I'm still talking about ultimate deficiencies. And there's a nice example, for instance, where Fiotto is talking about fabrics and fabric weaving, and that the irregularities which he finds in a lot of natural fabrics or handcrafted fabrics, making the fabric more resistant and rigid and tough, because it can't rip along a neat set of lines, for instance. That's a discovery. Now, we should hunt and search for these kind of moments where a disadvantage is looked at again and with an alertness for opportunities. And then we might hit upon an opportunity. That's like the evolutionary process where everything which we are mutations which are opportunized upon, so that we have that spirit, but it hasn't been made concrete in this project. So that's something yet to be done. But also there's no guarantee that it can be done with this particular.
Lyssna. Chodź, Frida. 这个你帮他看一下，我去把那个模型
pretty much.
Yeah, sort of. Thank you, Risha.
Is it going to move in real time?
We do have videos of the movie.
Yeah.
Hi, good morning everyone. We are Team Synergia and we are a team of 4 people, Astrid, Ian, Ray and myself, Hitesh.
Synergia proposes a new model of behavioral assembly systems as a generating force for architecture form. Based on the recent revolutionized fields of robotics, research of Hod Lipson, which studies the soft multi-material freeform fabrication technologies as a new development for locomotion, we exploit this new paradigm as a close relationship between architecture and machines that has the capacity to fabricate optimized tools that could serve as a technological system proposal aiming to idealize into emerging model for innovative modern spaces for society.
We have working on making the grid system based on this particle spring system, and the grid system have many advantages such as flexible and democratic and the relationship between the neighbors. Also, the competition of expansion, contraction of rate, grid can give the system have the mobility. And move to the 3D world. In order to look at the most effective basic unit, and we can make a stable moment, what we want is focus on the movement affecting the rest of the body, and the one cell was the expansion, and as a result, we found that unit have the directional nature and the stable center. Variety types were made such as to make the flexible moment, and we found that the physical unit is based on the 3x3 cells. So that's 27 cells gives our system some possibility of movement, so we can make the rolling, and by searching around the information of the environment, we can develop the behavior between the two units and make them come together and do some group behavior like climbing and face-to-face interlocking. And the building logic, we developed the building logic by this system, and then by the next stage, we developed this strategy about structure building. Yeah, this kind of linear spaces is our basic builder. And by some physical experiments, we test the control the pneumatic system and by sequences to match our coding system. And by material research with the silicon, we use compressor to compress the unit and get some different state and give the mobility of the unit, so we can achieve some moment like rolling. Yeah.
As we are living in a voxelized world in this scenario, what's really important is that the most important component of this entire simulation setup is that the voxel becomes the most important part, where it holds the maximum capacity to either expand, to contract, to be rigid, or to be neutral. But its behavior is not working something in isolation. It's something that works collectively with its own relation to its own neighbor. So a hard neighbor with a soft neighbor on the other side would react in a certain way. And collectively, when we join multiple of these together, hard and soft components together, they lead to different reactions altogether. And triggering the pattern of the cell control achieves the mobility, and we carry forward the simple set of rules into the third dimension, translating the multiple actuation into the mobility of the collective cells. What we see on the screen right now is one of the prototypes that we try to figure out in terms of how we could voxelize this world with using silicon as a pneumatic cell, and how we could actuate this with compressed and vacuum pressured air, so as to see can it lead to movement. So we could come up with a simple setup where we have a rigid core in the center with a pneumatic voxelized world around it, and a very simple actuation of contraction and expansion And again, we need to reverse this cycle to make one turn. And when we do the same thing simultaneously, it leads to a continuous movement. It could be either backwards or forward. So they roll freely when they're in a free atmosphere and around with no obstructions. But the moment we test them to come together, as we would see in the next coming up video, that when they come together, they activate their sensors, which sort of activate the magnets between the two of them, which generates a connection. And then two of them can decide to roll either backwards or forward. Similarly, when two of them come together, they can actually together lift a third element together and transport it from one side to the other.
And after developing with the unit voxel, we try to make different type of unit. They can work as a structural behavior. By developing linear type, we start to consider multi-materiality. By using different types, linear type can can pick up and deposit different material in its area. So this is the initial study of linear and planar different types. And by actuating with the different time frame and different pattern, one unit can mobile, and single unit reads the neighbor in its neighboring calculation, and they can make a linear type. And by using the position of each cell, they can put the target and follow the target to make different type. And after making, they can cooperate to work, which is more efficient in terms of using energy to make mobility. So, and after making linear system, we try to figure out which pattern we can use to make them as a structural behavior. So in this way, after making linear system, they can stand with the support of other units, with the communication, and they can stand. And from this moment, they can be a builder which has a larger area. So after defining the behavior of each linear system, we start to make a rule set with the linear system. Linear system has its own area, and they can build in its own area. So by trying with the different parameters, such as area control, horizontal control, and direction control, we developed the linear system that can be a builder and climber. So there's two types of linear system. So one is climber that can grow vertically, and the other is laid linear that can build nearby in its area. By using this system, this system can make a directional growth, and this is a free growth. And after developing directional growth, we start to think about how this system can work as a structural behavior. They can, after defining the structural stability, they can calculate the stability all the time, and they can make a support itself dynamically. Okay, this is all we prepared. Thank you so much.
Yeah, mean, to begin with, some of the models that I kept here, because as I was trying to explain earlier in the presentation, that in our setup, voxel is one of the most important elements. And what we were trying to come across was that can we...
Guys, excuse me. We have a kind of open crit and everybody's super invited to stay, but we don't really want to hear conversations. If you guys have a conversation, please go outside. Otherwise, you're more than welcome to hang out here
So what we were trying to simulate earlier what we were trying to simulate earlier during our attempts and trials to understand this multimateriality more was how can we generate a system where we have the interrelationship between the voxels controlled by the material distribution within them. So we have elements which could be soft and hard right next to it, and how when they would come together, they could sort of, I mean, if I just do it by my hand, they could actually be actuated. But our ambition was that could we actually actuate it from within the body itself, then have a system which is actually controlled from the outside somewhere else. Yeah, of course. So, I mean, we were pretty ambitious with the 3D printing as a technology, as well as using soft material to print these things. So we were trying to understand how could we sort of set a patterning of material distribution within this volumes, which for a moment, if I say is a 2 inch by 2 inch of voxel, and when arranged in a different matter, could be an auxetic system or could be a simple compression element which expands in one direction and which compresses in the other direction depending on how the force is applied to it, and so on and so forth. So we try to do various studies, lattices, I would like a Voronoi distribution of systems within this thing with varying density, a simple lattice where how just by the way playing with the thickness of the elements, it could twist and bend, playing with some more auxetic systems where they could actually compress very well, and if I pull in the other direction, it becomes longer. We moved on to the next step, so we tried to compile how could we actually involve the pneumatic within the system itself. However, keeping in mind the amount of understanding of technology material we had, we sort of bridged over this thing and moved on to silicon because it was more handleable for us, given our limitations. So we actually started playing with a very simple cube in the beginning where we voxelized our world from 1 to 27. And how we simulated this in the beginning was we just made the system run on expansion. So what you saw in the simulations, the videos before, was it was a mix of expansion and contraction together, which actually makes this thing sort of move from its central point. Whereas the first attempt was to just do it with expansion. So we just varied the various degrees of expansion within the system, and it actually can move in any direction we want to control it. From that, we moved on to a little more control setup where we actually incorporated a core within the system, where the core becomes like a skeleton where it actually holds all the wiring as we see, all the tube connections that actually go to the pumping system, proximity sensors to actually detect the range of the next one, magnets as our basic system in order to connect with the next one and so that they can move on together. We built a very basic system with a control unit with valves and a mix of compression pump and a vacuum pump together, which runs in a relay. We ideally need one setup to run one cube, as you see this one, and a second one to run the second one is quite evident in front of us. So the more cubes that we have, the more elaborate the setup becomes. These were again a part of the same study that we were trying to do, different lattice studies and different distribution of patterns, and trying to incorporate pneumatic cells within this 3D printed environment to see that can we expand and contract that. Much the same. Some linear bodies that we were trying to explore with the pneumatic system, that can we actually make them turn like a torso and twist. Yeah.
Each cell is inflatable.
Yes.
So each cell must be wired with pipes.
Yes.
To actuate it.
Yes.
No matter how small, there must be pipes going there. That's the only technological creation we have put into this.
Yes, right now this system works absolutely just on pneumatic system. So you could either depressurize it or you could pressurize it, but it has to be connected to a tube. Like all these models that we see. Without that, it's a bit impossible.
they started, perhaps they will ask a question. Sure. Inflatable, you know, I have a long tradition. It was very trendy in the 60s. It was a pop thing. But at the time, an inflatable was a single unit. You inflated something which became a dome or a bubble. This is interesting because what you have done is typical of what we can do with digital technologies. We can discretize to cells which are so small that it becomes calculable and actuatable at a very granular scale. In a sense, what you did is typical of what digital technologies do to all we deal with. We take a big chunk, we discretize it, we calculate it, and we actuate it. So this is interesting because it becomes a granular inflatable. An inflatable, which used to be a big, you know, Zeppelin, which now becomes calculable and actuatable at a granular scale. And the granular scale can be as small in simulation as we want it to be. Now, for actuation, it cannot be that small because you still need pipes. This is where you may possibly conceive some other technology of actuation which can compete with the granularity of the simulation we can achieve. And then it becomes magic.
Well, actually, to answer that, that was the very first beginning when we started doing this. This is one of the models that we had. And this again, fairly big as to what you're talking about, but what our ambition again was that can I actually control the system with the memory coils and coils inside. So we did try to actuate these with, we made a couple of these. We did try to actuate them because we did not, like I said, want the system extended outside and can control the size of this. But it did not give us fairly, I would say, convincing results that I could make it move in a more controlled fashion.
But when you can actuate it at a scale which is as granular as the extremely granular scale we can simulate and calculate it, then when the two go together, this becomes a very interesting project.
Mario, that's part of the ambition. So, in a sense, they're working with what they normalized as a 3x3x3 grid, which allowed them to basically have a 3D voxel, and to use that kind of 3D voxel as a strategy of thinking combinatorially of how a system could be deployed in a very high resolution, giving these physical pixels the capacity to have some agency to come together and to create possibilities. So it's a model of actually literally taking a voxel and trying to find the methodology and to work on the project. So they started with a lot of research, which, if I'm very honest, the presentation is a complete disaster in terms of presenting the problem. And the problem was, in some of these experiments of, one, the promise of multi-materiality is not so accessible, and in a way, at least not so accessible to us here. The second one was the idea of actually working through patterns. So sometimes they were using exotic materials. Sometimes they were using shape memory alloys. They did a series of researches to try to deal with the problem of how one can control local transformations and to deal with a conceptualization of an organizational strategy that's high population. How can they communicate with each other to mobilize, create something based on these kind of local rules of engagement, just through expansion and contraction, trying to push a certain kind of systemic limit to the way that one can start to work on these things. I think some of the models have been, these kinds of struggles with the paradox of trying to work with these things. And this kind of complexity of having a proof of concept of the model is something that, at least in the studio, we felt was very important. So the limitations was actually lifting one voxel at this stage. Cables started to become a problem in terms of the way that they were uptime, but it gave enough logic of understanding as an erector set, because it was in this Cartesian grid, but there was a capacity of actually moving and mobilizing the choreography, and to use that from a very genetic algorithmic perspective, to be able to manage how a system like that could be conceptualized and deployed. I think in some senses there's been an ongoing struggle, but I actually celebrate that. And I wish you guys had the courage in the way that you've been exploring these things to actually share that. Because I don't think that this is a normative thing.
So what I think you've achieved in the project on a mechanical level is absolutely applaudable, and just the movies that we've seen are breathtakingly beautiful, really stunning. But what I'm a bit disappointed is that, you know, we are living in a world that's moving from a centralized organization to a decentralized model, and I feel that the brief of the studio and that your work is taking place in this context. You know, images of these distributed warehousing robots of Amazon come to mind. You know, we live in a world where a year ago somebody like the Greek government, courtesy of Varoufakis, was considering the Bitcoin blockchain as, you know, their financial means, and this work is taking place in that context. So I don't think you're doing yourself a favor of, you know, leaving that worldview out to contextualize the work that you are operating in. So perhaps, you know, don't post-rationalize your project, but contextualize it in that sense. And let's say there's this kind of amazing graphic quality in your animations. So I see that your project unfolds over time. So it's certain that it's difficult to do panels, you know, to project something that unfolds in time on panels. It's difficult, but still, you know, you're just throwing away 50% of the area in your panels, and the graphic quality, sort of the typography is really not great, I think. So, for instance, take a look at your very last panel, right? The sort of potential graphic quality in that drawing could be stunning, and I'm not seeing it, which is disappointing, right? So why not color these voxels per cells? You have 8 vertexes. Assign a color to every vertex, not just one color. Make them transparent. Render the graph of the voxels, the trajectory, you know, in the cells. Relate, for instance, the edge thickness to its development over time. You could have amazing drawings. They're good, but they could be amazing. And the thing, yeah, your panels are really inadequate. So if this is suggestion of what your output is going to be in the book, you're not doing yourself a favor. It can be, you know, there's work to be done there, I think. Yeah.
I'm going to take issue with Mario about the 60s. I remember a walking robot constructed by Mark Fisher, which had a multiple set of cells that was very beautiful, done around about 1966, when it subsequently kind of re-emerged in various forms in amazing constructions for pop concerts in the 70s, 80s, and 90s, and into the 2000s. That said, I mean, talking about what's on the wall, I find the transitory states of your objects more interesting than the final assemblages that you've described them falling into. I kind of wonder why you've been driven so hard by an orthogonal grid at the point of assembly, because these things, although they're made on a 9x9 grid, at a certain point when you join them together, they could take any position, and we see kind of the occasional tail that looks a bit like a piece of DNA, but it does seem to me that that these things have inherent and, you know, multi-vectoral forms that you're not working with. I've got to say that what you've done as just a straight piece of assembly, you know, in the context of a student project over a limited period of time, is awesome. But I think my view would be, again, that you might reflect a little more on what you've done at the end of the day with it.
Just to second that, I think the final large towers become very unconvincing. It's a bit of a shame. But I absolutely adore the project. I think it's an amazing achievement in terms of the proof of concept model. They're stunning, and what they deliver, and the animations, the simulations are striking in terms of the way the global configurations and body plan behaviors you can viscerally follow and are correlated with what the cells are doing and how they're synchronized to do that. And that's really stunning, and I love the body plan configurations here. There's this kind of the surface, the line, the volume in different configurations, the circle, and I agree 100%. The behaviors are the different types of locomotion, aggregation, and when you see things collecting together, and then a new behavioral capacities emerge in that assembly, and then another reconfiguration with new behavior. So to explore that world and that combinatorics explosion of behavioral possibilities is really stunning. So, and that needs to be, I think, in the scenario, become much more alive. That transformability and that active, interactive behavior. So I think there's a kind of strange focus on a self-assembly of a tower structure which isn't even clear what in terms of its usability. It just needs to be edited out, but I love that, and of course the printing research also has its own merit, is its own little project. I mean, it's connected into. You haven't made enough, even though you made the decision to do this particular proof of concept, but that doesn't make that irrelevant. So there should have been an effort to, in the final display or in the final synthesis of seeing a sketching machine, even if you don't build it physically, which utilizes this. I mean, these are in themselves stunning things, which deserve a lot of attention. That's why I agree with you. It was very important to bring that back. And I think altogether it's really, really highly commendable and wonderful and innovative and powerful project.
I also like very much the way you really worked and took a lot of effort into make it real. The movement of the robot is beautiful, is magic. I think it's really interesting to have such a cell which is able to make such many things. But during your work, you've figured out that it is really complicated to bring everything together in one space. And what my experience was over the last years, you always have to think about how can you make it as simple as possible. And here you very much tried hard to use all these many degrees of freedom. If I counted it right, I have about 20 degrees of freedom at the moment, 20 cells which you can fill, and even you can fill them and you also can deflate them. So in total, these are 40 degrees of freedom. So this is really a lot of functionality in a single piece, and this leads to a lot of valves and compressors and so on. And I think there's a lot of potential to make it very much simpler if you think that, for example, you could deflate one cell and pump the air from the one cell in another cell. Then you save valves. You also can couple different chambers. So maybe in the end you can reach something quite similar with only 4, 5, 6 degrees of freedom, and then everything gets much smaller. And this is what we very often try to achieve, that there's a little more intelligence in the design, in the material itself. Then you save a lot of effort for control and energy storing and so on. And I think this also will be the key finally, if you once will be able to have these modular buildings, these intelligent bricks, we already had this yesterday, then the key will be to make it very simple, very clever material-wise, connection-wise, very lightweight, still robust. And I think I'm looking forward for the whole group actually to see over years how you can improve going towards this direction. And I think this is a really good step.
I think the great comments, obviously, coming from an expert in pneumatics. And I think it's worth emphasizing that this is really difficult to do. Like, to do soft robotics is incredibly difficult, and it's also very incredibly difficult to scale it down. You have the world expert in the room, but I think you should really be commended for the way you've actually got the locomotion in this in particular, because it's not a straightforward relationship. You've had to work out, like, for instance, there's a deflation at the same time as an inflation. There's a whole lot of maneuvers that require multiple things and took many discoveries over a long period of time to get there. And I think, like, the models on the table show good results, but they don't really articulate the struggle that required to deliver that functionality. So I think that's fantastic. This diagram at the top here, like, I'm just looking at this, and for me, this actually summarizes a little bit the construction process I would have liked to see in those last simulations. Like, you have the individual simulation of the builder, kind of, and I would have liked to see the final simulations embodying that, and this diagram embodies that. I think it would be really good to be able to see how there could be a time-based construction sequence where you really see it building up by, you know, multiple vertical towers, bending down, picking things up, passing them on to other parts. That was kind of missing in the end result, and I think that would be something very easy to incorporate in the book. So I would suggest you do that, and also try to document some of the forces and actual physics going on in this movement process, because you really nutted that out, and it's not so straightforward. Well done.
I mean, just as a closing comment, I think you have built an instrument now that you need to start playing. I think there's a certain aspect of taxonomy of behaviors that I think, you know, your critics are very astutely aware of what's on the table, but it wasn't really described, because I feel like this is a little bit of a life lesson for you. Like, it's not about having a blind belief. I always liked the fact that you were building and suspicious and curious and all of those paradoxes together. But I think the complexity of that process, I think, is really important to be shared, so that the next generation that's building on these kind of things also understands what is it that they're really working on. Because one form of description just sees it as a bunch of cubes that get stacked, or maybe it's a group of architects that are interested in modular robotics, and I don't think that that's actually what you're working on at all. But the assumption by the work, without really exploring the whole kind of creative friction and process behind it, lends itself to those assumptions. But if you actually describe it on behaviors, and I think even those digital moments, building on stuff like Mark Fisher and others that have been actually working on these kind of things, but actually pushing it to a territory of technologies that are today, right? And that's why I thought it was very important for you at least to show some of those experiments, because in themselves, I think that the hybridity of it is where we're sort of working towards, that idea of resolution and what that actually demands. But the resolution is not necessarily resolution of more visual complexity. I think this project doesn't actually have a finite form. It's something that's always pulsing and reorganizing, it's self-structuring. How does that really work? How do we work on that problem? So I wished you actually talked a little bit more about body plans and that aspect of Carl Sims and how bodies are organized and new behaviors are born. Same elements, but combinatorially driven, radically different behaviors. And all of that Evo-Devo stuff you guys were looking at and all of that other stuff, that has to manifest itself in the book. I agree with Yele completely that the panels, in some sense, don't do any justice to it, because you've treated it not even as a greatest hits of what you've done. It's just what you've done in the last couple of weeks, or what you think you were doing. And I think these 16 months, I would really ask you to critically reflect on what you have and take the conversation that is here today as a new way of reflecting on what the work actually has. I think it has a lot of potential. I'm really happy to make sure that that bottle was actually working. I know those videos happened last night. And I think the fact that you actually do have it now, I think you really need to use it. It would be a crime to leave the project at this level and not to document these behaviors and what you've done. So I can only encourage you to do that. And I think you have gotten a very good critique not through the words that you've said, but the stuff that's actually was on the table and some of those videos that really unlock some things. So it's something that you should really take away, that the project actually spoke a lot louder than you guys did. And you should have the confidence now to actually work through actually some of the implications of what it could do. Okay, so thanks. Elena just got her voice back, so no, try.
I'll try. It's horrible. I'm just in front of this one, and I'm thinking that I'm gonna whisper. Is it okay? I think it's better whisper. That I actually would say that the next 2 weeks I will look at this thing that I have in front of me and try to figure out if it is scalable or not. I have a serious doubt that this stuff can become, all of it, small enough to make that ever workable. Somehow I think a mechanical system with a pneumatic system might never completely disappear or have a volume that is smaller than that. And I think that's not a small issue in this project, because I think a lot of the fantastic models here at the power of material behavior, whereas here it's all mechanical, and I feel like at the end of the day, this will never trump that. And I think that's the major problem.
No, I think that's beautifully said in a whisper provocation.
I'm very sorry about this.
No, but I say that in a really good way. That's a provocation for you to show what you've done in the next 2 weeks to Elena and see if you can do something. It's a beautiful way to end this project.
Yes. Okay.
That's what we said, no?
Just copy.
Ale, tavole, cane.
The AADRL is really known for its graphic videos. Take the data visualization, the materials that you have, right? So fire up your processing, write out PDFs,
maybe it's the other end. He's not. Maybe he waits to connect it.
As an architect,
Someone that has
you see what I mean? And even when the models come over, sketch how vague it can be. Panels first, so we can do open mic. Makes everything much easier.
just plug this one in.
Such a conceptual change. Right? So you saw the review yesterday. Shit. Well,
Hey, Rob, 1 second. You have a Mac, right?
Sorry?
You have a Mac, right?
Yeah.
Just trying to get the...
it was sort of printing on top of just right? They rule this
The one is playing, anyway. On a Mac, yeah. And this is not mine now. I was mentioning.
It's like a head tree,
Is it okay on this?
I'm just like double checking. I think it's okay now. Panels. You know how the panels are. Can you tell them? Put the big image in the...
Yeah.
Do you think we should put this right? No. Go back. It's there.
tu. Good afternoon, everyone. We are part of Robert Stewart Smith Studio, and our team is Minus Plus. We are Martina, Ashwin, Alejandro, and myself, Chiara. Our studio investigates algorithmic and robotic behavioral methods of design for swarm printing. Area robots have a beneficial capacity to maneuver freely in 3 dimensions. When one swarm of multicopters collaborate to perform uniform maneuvers, it teases our futuristic potential in the realm of architecture and urbanism. When considering 3D printing as an exciting manufacturing technique that offers infinite complexity and variety without assembly and labor skill, and has the potential to manufacture on site with no waste and no lead time. 3D printing with metal is under development, and we want to further explore this field. In order to facilitate continuous and instantaneous printing, the material we are proposing is a phase-changing metal alloy that can be melted down quickly and reused over and over without losing any capacity. We are interested in controlling the variables of phase-changing material coupled with area robotic flight behavior in order to achieve multiscalar design qualities intrinsic to production process.
Material phase-changing properties enable our architecture to change over time. Through autonomous tracking of human circulation that you can see in pink and occupation in blue, construction and design operate in real time in a social pedestrian environment. The cellular field represents a record of human motion. Higher alpha channel correspond to higher circulation or occupation. Learning from observation of people engagement with architecture, material can be added, removed, and reused. We propose a time-based construction that can expand, shrink, or migrate, and eventually can be melted down and demolished. Traditionally, computer vision is used for surveillance and statistics, but this technology can be put to more democratic public use in providing feedback for adaptive building that responds to people's collective choices. So we use computer vision to track people's occupation of space over time. People's choices about how they occupy space reveal the success of architecture and informs our design, construction, deconstruction, and reconstruction. 3D printing hardware, material deposition, and file control strategies were developed for outdoor deployment and indoor lab environment. Octocopper with high payload capacity can be used for outdoor printing with metal alloy, while beeswax with similar behavior can replace it for indoor testing on tethered smaller UAVs.
The metal alloy has a sharp melting point at 124 degrees and possesses properties such as reversibility and high strength. In this model, we are testing the aggregation and the spanning properties that allows us to build various artifacts. And in the video, we see how we pour the melted metal and how we cool it down using a syringe. Since wax has similar behavior to metal, we carry out a series of experiments to study the aggregation quality using different types of wax, different heating methods, and different cooling methods. This video summarizes our initial attempt to test different types of waxes, namely glass wax, paraffin wax, and finally beeswax, that was chosen to further explore due to its low melting point in instantaneous aggregation. We try to take advantage of material behavior using drippings to reinforce and to increase the source section. As a conclusion of our research on 3D printing uses phase-changing material, we can say that the main variables to consider for the building system and design are height, power, speed of deposition, and nozzle layout.
We simulated the deposition variables utilized in springs and particle system in order to embrace the limitation of 3D printing as part of our design. Printing closer to the ground ensures faster growth, but distance of at least 30 centimeters is required for drone stability. Second variable we tested is speed, and in this case, the higher the speed, the slower is the aggregation of material. Since we are using a phase-changing material, the power and the angle of deposition of water for cooling down and enabling aggregation is critical. We thus simulated a double nozzle for wax and water, and whereas higher voltage of the water results into more precision, when combined with speed and height, lower power is more efficient. Following these first experiments, we also tested some vertical aggregation of material and its capacity of span. The multicopter constantly checks the distance from what's already printed and can move up accordingly.
In order to expand the position variables, we designed different nozzles layout, how we can see here. And we tested the variables and find out how much each of them was influencing the design outcome. So summarizing, there are 3 possible printing outcomes: continuous but slow growth filaments, drippings, and fast growth, discontinuous elements. We built a canopy model to test the capacities of our material, and from this experiment we understood that different deposition strategies are needed when printing vertical and when spanning. So we came up with 2 main strategies to apply according to our design. And on the left, a dripping tower, we can see, where we are following the main trajectory using dripping to reinforce. And on the right, a tower with a thicker deposition outcome that is more dense. In this last model, we applied our research on multiscalar printing strategies, combining macro trajectory with embedded micro movement and nanoscale of material behavior.
Moving on to aerial 3D printing, we had to design a hardware system taking into consideration payload constraints as well as copter's center of gravity. Although the thesis argues for autonomous material refill, we developed a tethering system to constantly supply material and power that enabled us to carry out many experiments in indoor lab environment. Since the quadcopter had limited payload and safety concerns in the lab, we had set up a tethered lab environment to demonstrate aerial printing. This system was aimed to study about the relation of character between flight and print. This video explains the process of the material supplier, where wax is fed in a container that flows through copper heating bands to solenoid valve and that can be controlled by a switch. So water is fed in another container and micro pump can be controlled to use the water flow. For smoother flow of wax, we introduced flexible corrugated tubes in the ends of heat-resistant Teflon tube that enable stable flight. This is hardware we developed to attach to the drone to ensure it could only 3D print within a specific distance from already printed material, since we discovered that deposition height must be controlled as it affects the deposition result. These were the first 2 prototypes of onboard hardware integrating both wax and water distribution with adjustable angle for water nozzles. Since the previous prototype caused imbalance in flight and was heavy, we upgraded it in order to have better control of water deposition and at the same time reduce the weight of the attachment from 130 to 30 grams. We designed a prototypical multicopter that has the capacity to have more payload and battery life, which is embedded with necessary electronic components needed to print while mobile. And this is a close-up of the end effector where material could be printed. We digitally explored printing logistics for autonomous refilling, like switching on and off deposition depending on distance from the target, refilling material, and recharging battery. When the number of multicopters increases the printing process, it is significantly faster, but traffic congestion has to be avoided.
Moving on to flight control, we had to develop our own behavioral algorithms in order to work with aerial robotic in real time. We use robotic operating systems, an open source platform, to access and share knowledge with other different labs working with the same technology. Positioning is necessary to ensure that accurate 3D geometries can be 3D printed, and this is something quite challenging for a quadcopter. We developed bespoke algorithms for flight control based on motor-driven maneuvers, onboard camera feedback, and offboard camera feedback. As an introduction, quadcopters has 4 basic movements based on which motor we power up: thrust, pitch, roll, and yaw. Scripted trajectories are controlled by sequential machinic maneuvers that instruct power and duration for each of the 4 motors. Although the system does not have any feedback, it ensures successful 3D printed by repeated maneuvers. So as we see here in the screen, we just instruct different motors for different durations, and we can achieve different movements. Secondly, we look at onboard camera feedback using slant vision, simultaneous location and mapping. This way, we could strand points, virtual points in 3D, and based on the camera vision of the copter, the gyroscope, and the accelerometers, the copter will go to those locations. The system is completely autonomous, although it's not as accurate as offboard camera feedback. So lastly, we thought we wanted to get as accurate as possible for 3D printing testing in the lab. So we develop algorithms also for offboard camera feedback to track. So this is basically tracking position and orientation of the copter in real time and feeding that information back in the copter in order to update its trajectory vector. In the lab environment, we create a system for constant supply of material and power to understand how the character of flight directly impacts the character of prints as well as the geometry. So here we're using both slant vision was the first one, so that's onboard camera tracking, and here is offboard camera tracking. So that means that a camera is tracking the position of the drones and updating that information in the drone. So in the lab conditions, we could print thin vertical aggregations by locking the drone position in space. Yet, for a large-scale 3D printing, we needed to consider bigger cross-sections and embrace deviation in the flights as part of our design output. In order to 3D print curves, we developed 2 systems based on position feedback. So one system here on the left is updating X, Y, and Z differences in distance, and the one on the right understands the angle difference and the distance difference, and updates that as a vector for curvilinear maneuvers. So basically, what we see in the screen is that by remapping distances and angles between current position and target location into quadcopter motors, we can instruct both straight and curvilinear lines. While overall print trajectories define the geometry in space, we were interested as well in micro movements that we could embed in those trajectories to instruct character to those prints. We tested how we could print trajectories as well in the lab. We could do it either by repeated scripted movements, as we explained before, or by constant feedback, as we see in this video. So here, the drone is trying to follow the targets that are on the ground. So those are like virtual points in space and creates a circle over time. Our research proposed that we could continuously print and adapt architecture to people's engagement. So in this case, we were testing tracking learning detection. So it can track either like one person face or tags, and based on the tags in the screen, we could trigger different maneuvers for the drone. Multicopters can also dynamically avoid people and objects throughout a 3D printed operation. So here, the copter is trying to get to the targets, but at the same time, it needs to find out the path. The path is not instructed. It's just trying to get to the points, but avoiding us in the meantime. We were kind of scared. So, moving on. So, on the other hand, for a strong 3D printing construction, we needed to create behaviors for them to communicate based on local rules that they could perform. So, we decided to follow Craig-Reynolds algorithms and flocking. So, what we are doing here is creating following and then avoiding as like main behaviors for our thesis for the drones to interact with each other. So if we extend these two basic rules, we can develop collaborative maneuvers for 3D printing, such as following each other trajectories, which is the flocking, or what we have in the screen, choreographed movements, or in this case, self-organization around positions in the space. So they are like rotating around the point that was in there, the center.
In the idea of combining agent micro-behavior and multi-agents behavior, we aim to build complexity through simple bottom-up rules. Swarm behavior, cohesion and separation, seeking waypoint, revolution around waypoints, and rotation around the centroid of the swarm. By combining these basic rules, we can get diverse patterns that gives us control both on cross-section and porosity of material. We also tested how through self-organization two teams of multicopters can affect cross-section. Although they are purely moving in circles, they are actually determining their behavior in relation with the position of each other towards a dynamic and flexible arrangement that can still produce controlled geometries. This is a catalog of different vertical aggregations that we obtained by the two teams of multicopters operating on one on the internal and the other one on the external boundaries. Following the same rules, we also introduce a three-dimensional behavior in order to exploit the free mobility of multicopters. So we tested different diverse weaving patterns that can be varied in frequency, radius, and section. So the section can be in the top, a circle, or can be rotated, or can be an hybrid of both. The drones collaborate to interweave continuous threads that transition from vertical to horizontal structure elements, braced by dripping materials to connect the woven strands. By varying the frequency and radius, we are able to adapt the cross-section where more structural depth and density are needed at the base of a span, or to spread out the pattern to reduce weight in the middle of a span. Groups of drones are assigned to different tasks in the construction sequence. Two groups can weave each primary structural element from the ground up and meet in the center, but they are also able to weave between pairs of trajectories or interweave and brace multiple trajectories.
We created several families based on trajectories and weaving patterns. The proposed building sequence builds first the main trajectories with teams of up to 4 drones and reinforcing with 3 pins the connections. Once the main structure is done, we add the connections to create surface. So it was observed that the most continuous and vectorial topology was connecting 2 virtual points in space through continuous trajectories that builds the structure over time. We introduced transformations on the trajectories according to the needed topologies going from canopy-like structures to cell topologies or spanning roofs. So here, pretty much we see like the duration, quantity of material, and number of drones needed to perform each of those trajectories according to our research. The thesis argues for a monolithic 3D-printed architecture characterized by its emergence from autonomous aerial robotics flight. The flight and deposition behavior defines an heterogeneous, multiscalar, continuous, yet differentiated geometry that is three-dimensional, complex, and difficult to fabricate by other means.
Looping Matters design proposal explores the South Bank area of the Thames River in London as a test bed for a continuously changing public space where aerial 3D printed construction could adapt and reconfigure the site's multi-level outdoor spaces that comprise a mixture of podiums, esplanades, walls, green spaces, and pathways. These spaces engage in diverse uses and pedestrian flows throughout the year and host a range of temporary events. The project aims to transform the existing spaces of the site into a continuously changing architectural environment that allows for construction and deconstruction over time in relation to human behaviors and events. After observing people movement, the design space is selected, in this case in front of the South Bank Center. The animation explains the sequence of the building process where multicopters are deployed on site by boat containers, and the team observe and start building on the selected site, and the process adapts to the need of the people by creating and melting elements. As you see, it's been creating, and at parts, when it realizes it can be melted, and moves on to the next thing. Okay. To conclude, human occupation and use of the site informs an adaptive learning construction algorithm that will aim to remove underutilized or problematic constructions while enhancing or repeating well-received building activities. Thank you.
So here you can see our prototypes and models. Those are the hardware prototypes, starting from the first one in MDF to the last one that we 3D printed. And here a catalog of different nozzles that gave us different outcomes, like you can see there. The two towers we have shown in the presentation, where you can deposit with in a thick way or with drippings. Here in the center, we have our test with the metal alloy, where we try to test spanning and weaving, and again, weaving but branching. Here we have our design families with variations and the final aggregation. In this big tower, we want to show the micro movements, the macro movements, and nano movements, and we try to do it scaling it up. And one of our first attempts for drippings, micro movement that then we applied in the big tower, and something that we printed with drone that we have seen in the presentation. Thank you.
I'm really in awe by the sort of the multiple drone strategy that you've put forward. I mean, we've seen that in the other drone projects from Robert's studio as well. But I think, let's say, that is a forte of your project, and you push that agenda the hardest. And I find that a very convincing part of your project. The thing is that I've been glancing at. You have 7 panels. 3 out of them I see a sort of. Let me rephrase a little bit better. In order to be a master in architecture, I think you need to be a slave to the work. And what I see here is that there's a kind of. I suspect that there's a kind of aesthetic you are infatuated with, a kind of sub-deep marching cube aesthetic with, that seems really disconnected to what your project wants. And actually, I think that the work you're producing is a lot more beautiful than your possibly infatuated aesthetic preference, right? So kill your darlings. Yeah.
I mean, just to second this, I mean, I will pick this one as a most compelling of the models. And I think, yeah, I don't understand this. Because that doesn't come out of your process, that isn't a viable option. And none of these shells are. But what I find really fascinating when you print the spiral into the space and the dripping down creates a wall, a porous wall, and there's this element of accumulating towards the bottom as you go higher, and recognizing the need to reinforce below as you go up. And there's a lot of beauty and economy finally in this, because we had a lot of models which just kind of horrendously massive and excessive heaps, but here there is a certain economy and compelling structure, and you've explored a number of things. There's kind of step versions, and they come with different degrees of curvature. You haven't talked about how far this can start deviating from the vertical, because then there's the ones which can't often, where these drips are, they become dysfunctional. I consider these dysfunctional, and these are functional drips because they're actually tying a spiral into a surface. That's more of a kind of a pragmatic and precise discourse maybe we should have, and you got to come back and explain the status of these. I agree with you. That's what you're referring to, right? Of course, these are beautiful patterns, but then in no way correlated to your project.
I'll just answer something there. Thank you. Save my voice. One thing that they didn't really explain is that they have absolute control over whether they drip or not, based on the water flow that they control electronically, and both the voltage and the number of nozzles that are there. So they can actually do a continuous print in wax or metal with no dripping, and then they deliberately use dripping when they want to reinforce. So the spiral columns are very clearly a great demonstration of an efficiency of minimal number of trajectory, maximum material connectivity, but at the same time, they want to argue for much larger structures and also more spanning structures that they can do in metal with more precision. And the context of that is that the studio has just got a multi-million-pound grant to do this work and deliver a constructed building in 4 years' time, and that we already know exactly what precision levels we have and what we can achieve in 4 years. So the precision to do that type of thing is not an issue. There's no reason why you could not have something like that. But actually what's really inventive about their process is that they recognize that there is one level of precision they can get for a trajectory, but that is not the level of precision of the print. And so what they have is two different modes of movement. The trajectory one, which is pretty accurate, is controlled by motion capture and so forth. And then they're using the motor controls for the messier, imprecise things that enable them to do these detailed things that you could never do with the positioning system so well. So it's coming from that angle. I actually strongly support this image in the sense that, okay, the character of it, I agree with the comments, it's different. But what we're looking at is a highly ordered weaving sequence. There's no randomness in that image. It's all coming from local rules that are creating a highly differentiated condition that is creating truss-like geometries. So I think it should be recognized that there is intention in that as well.
I guess I'm going to agree with the first two speakers. But that's not the point that I'd like to make. I've got 2 points. One is the idea that's really interesting in the project for me is that gravity is both your friend and your enemy. And it really comes across in these kind of productions. And I don't know, from a purely technical point of view, I don't know how you do it, but it does seem a shame that you should be carrying large buckets of water up into the air. And one wonders whether there aren't other modes of conceiving this work that don't require the buckets of water. And but I don't know the answer. The other thing that I think is really, for me, of profound interest is whether you are actually having a global vision of what is going to be made or not, and the role of local rules and global rules in what you're doing. Because it seems to me that, generally speaking, you are aiming at things that have global structures, where there is a global design. I just cannot see that it isn't there. And what interests me is the degree to which you're reviewing the production of this global aspiration by local transformations when things are going wrong. You talk about your vision system looking at people, but for me it's kind of, would be much more interesting if it's comparing what it's making with some idealized form as to what it actually wants to make as a collective of individual participants in a construction process. I think that, for me, that's fascinating, and it's still an open question in the work.
So, I know it sounds like I have a terminal illness, but I just lost my voice completely, so I'm gonna whisper like Theo. I wanted to talk about this project for 2 days, so I will. I looked at the tower for a few, for 2 days actually, and I thought it was fantastic for a few reasons. This is the first project where I think that the technicalities are not that important actually. We've been talking about how things are made, how feasible they are, and this project, I think the design somehow is such a much more important part of the project. It looks like the Babele Tower, it looks like Icaro, or a grotto, or there's something tragic about this project and incredibly appealing, like lava. And I find this the first project that really excites me beyond the inventiveness of the methodology, because it brings back in a contemporary way things I haven't seen. Also, I think it's very Catholic and Italian for some reason. I think there are two there that really have something about it. Yeah, I can tell. So nothing, that's all I want to say, because I know that I sound horrible. Sorry.
Well said. And I think it's probably not just that it's a kind of Tower of Babel kind of image, but I think the moment in this one that I find striking, and unlike the other models, is that there's clearly a moment of transition from an incredibly formless piling up of stuff to suddenly a fairly iterative, highly structured movement of whatever that depositing agent was in this case. And I don't know if it was your fingers in a plastic bag or one of your flying machines, but it doesn't really matter. It's that you're trying to take control of that idea of form that can move really across the spectrum, in which those two concepts aren't oppositional, formless versus formed, but part of a continuous spectrum in your universe. I think it's terrific, and to do that in a world that's deliberately monolithic is a bit of a tour de force, or tower de force. And I gotta say, the thing that I'm struck by is that you introduce, unlike a couple of the other drone teams, it seems like you willingly introduce an additional variable, which I don't know how to name, but it's like a delta Z variable, in which the distance between the nozzle and what it's going to hit as a surface is another thing that we can control, in addition to three-dimensional location, speed, acceleration. You've already got a lot of physics in these projects by design in any of these drone briefs, but the idea that becomes for you almost the means by which to introduce what in old-fashioned 2D space would have been called pen width. That the further away that point is from the surface, of course, the more splatter you get, and the less precision in an old graphic sense by design is introduced to the system. I think that's a terrific discovery, and you ought to, in wrapping the work up in the monograph, I think you got to really focus on how that's something that I think comes out of the project itself. It certainly wasn't in the initial brief, and again, it stands out compared to a couple of the other teams that have worked with your same level of aerial ingenuity in moving these things around space. The only other point I wanted to make was that I'm still struck by your obsession with superstructure. Like, that's what, for me, confirms you're still wannabe architects and not just form makers, because, modern architects for a century have presumed that the superstructure has got to be where all of the energy is, and we're going to get to questions of cladding and interior, and God, I don't know what floors are like in your universe, but they're all going to come at some point. And the only thing I was going to say is that your machine, it seems like, in addition to being able to print three-dimensionally superstructure, it could as easily, like your next team of drones flying in would be spraying the clear films that would become like cladding or like, a horrible word for you, like windows. These things that you shouldn't be fearing as a problem in the kind of Misesian sense that they're a second-order problem to sort out once we've got form in control, but that actually is just another layer of complexity, and it's absolutely terrific. All we got to do is change from a hard material to a fairly transparent one that would be, applied in millimeter micron kind of thicknesses, and you'd have enclosure. If I then, flew a team over it with spray paint and I have, air guns flying, I'm actually coloring it. And all of those problems, in a way, could be folded into the basic machine so that it can really be creating a kind of spectrum of thinking that no longer, in that kind of modernist sense, orders material, particularly around questions of superstructure. And in a weird way, I think that comes out of your obsession with making it monolithic, which as I looked at it, or rather as I walked in and smelled it, I thought, it's like walking into a sculptor's studio, which I've been saying for years. There ought to just be a wing in the DRL to make sculpture, because it can become the basis for developing ideas of form that eventually go into architectural realms. And again, we got a century of that sort of thinking. Early Mies, early Gropius, Kiesler, make objects literally this big, and out of that try and think of a future architectural project. I think you ought to have enough confidence that they really could be just shown on plinths. I'm hoping sculptors in the room aren't seeing this stuff, because they're going to steal your machines and start printing them out. But I think you can really trade it as an argument about form that encompasses a much broader range of architectural questions than just the structural ones that it seems like you're biasing in a very familiar kind of DRL way. Because it could easily become all of that other stuff with just the slightest shift in material in it. And given especially that Rob's got to, with your guys' expertise, deliver one of these things in a few years, it isn't going to be just superstructure over 4 years' time. It's going to have all that other stuff folded in. I think the earlier you can get that into the conversation, the more ahead of everybody else you could get with where it's going to end up going.
I like your idea about the monolith, and the project kind of relates to brutalism in that sense. Yeah. An architecture is made out of one piece. In digital architecture, there's been this. In digital architecture, there's been this trend of this rally of, I can make a project of 100 components, 1,000 components, 20,000 components, and I find it just very dumb in a sense. So I like this idea of, one element, a monolith, brutalism. It's beautiful, I think, in that sense.
Just a footnote on sand heap tectonics. You may not remember that because you're young, but in the 70s, when you were not born, but I was, the sand heap was the typical example of a non-linear physical structure. By the way it grows or it accrues, you let a drop, a grain of sand fall, and at some point, unexpectedly, the sand heap reorganizes or self-organizes. It takes a new shapes, and you cannot tell in advance when and how that is going to happen. And it means that if you repeat exactly the same operation 1,000 times, you will get 1,000 different results. Now here you can calculate the position of the drone with excruciating precision. That's why you're using a drone and not a traditional chopper. It wouldn't work that way. But you can never calculate what's going to happen when your material, which is not sand, it's something more designable, but still you will never tell. If you repeat exactly the same movement, with exactly the same material, with exactly the same weather conditions and temperature and humidity 1,000 times, you will get 1,000 different columns. Now, if you want to get exactly what you had in mind, as architects often want to do, you will fail, or that will drive you crazy. You must know which game you're playing. So long as you know it, it will work out fine.
Well, I think just to come back in terms of the precision discourse and the dripping and the qualities you've generated, I think, first of all, the flight cannot be fully controlled, and you will be subject to a lot of vicissitudes in terms of wind and the positioning, there's always delays. And so, but the precision you've achieved here, if you scale that up, because this is the 1 to 100 or something, in these, I don't think there's columns, I see them as spaces potentially, and walls and surfaces, and with certain variance and degrees, that is for me credible, right? And in terms of the precision you've achieved, we see these kind of absurd splashes over there where you really are. So that's why I'm still saying there's something kind of jarringly contradictory about this. But what I like about what Brett was suggesting is what you have here, you have water and this plastic, you have wax, you have various materials, and that layering of different substances in the choreography also of multiple drones to give that more, because this could also be done by one. But if you have an interweaving of different materials, the transparent and the black, and then you have a gradient of the white and black, and that's to do with because there's 2 black drones and 1 white drone, and then they keep changing, and then the accumulation of the material viscosity, and then also maybe this kind of idea of melting out or etching out. I mean, you mentioned sculptures. I mean, these are art sculptures that remind me a lot of some of the work of Anish Kapoor, and he's also doing additive as well as subtractive with eroding polystyrene, with acid etching and so on. So that's, and it remains in that interesting domain of the inform, of the amorphous and disarticulate. It's very, very anti-architectural in many ways, but for a while, we have been starting to accept that and make that, there is an aesthetic to this, but what we can't do is I feel, just creating out of nothing an aesthetic. This comes out of a certain modeling world and not out of your world. I mean, it has this, this might be an intention where you say maybe this is something which you approximate with etching out later or with a viscous material which generates these pores, but you're not in that world. So that's why I have to say, put that into brackets, and I wouldn't put that all over the cover. I mean, however beautiful that is, the beauty of this is interesting. But again, I think the material is a way to redeem the multi-drone, more than just saying, oh, we can accelerate the process.
I'd like to just continuously looking at what you've made. I think it's a tremendous achievement to get a group of critics just always looking up and down here. Everybody's scanning backwards and forwards and looking at it. There's a thought that's going through my mind, which is that I don't know whether you'd like this, but there's an element of the sublime in this, in the kind of early 19th century view of the sublime. One wonders whether it oughtn't to be inhabiting much wilder landscapes and adding to much wilder landscapes than the terraces on the south bank. Because you could imagine creating events in a sort of more wild landscape where you're not quite sure whether it's the landscape you're looking at or the thing that's been dropping from above. There's sort of like bridging points, but I mean, maybe that's all too romantic for you.
I would like to just say that the fact that you actually considered how you were going to take your temporary structure down at the end of the day is very commendable. And that was something that some of the other teams hadn't done. And the fact that you say that this material that you're going to use outdoors is a lightweight alloy that can be melted down and it can be reused, I think is hugely commendable. I think a lot of the stuff that we've seen so far has been built on like a linear economy of we start with something, we finish with something, and then what do we do with it at the end? You've gone full circle and you're completely sustainable, and I think from a point of view of architecture going forward, I think that that's really where we have to be at. We're in a world of finite, resources, and you've really tackled that problem, and I think that you glossed over it so quickly, but it's something that's actually monumental in your project and very commendable.
Yeah, I'm going to echo a lot of the things that have been said already, but I think one of the things that would be really interesting for me is, I love the way you've embraced the drip and taken it on as part of your form, but when you actually look at the scale of the things you're looking at for the South Bank, that will just be the filigree, that's the finery, the detail, and actually, when you look at how you do your deposition, that's more influential on some of your geometry. And so when you do actually scale that up, I mean, what we've seen on these size pieces is the deposition's dominant in what form you get out as the conclusion. Whereas when you scale it up to the sizes that you are looking at, and I think the city scale is the right sort of scale to look at these things, then that again becomes a detail and it stops being so dominant. And it would be interesting to see that detail worked into some of these images, and whether you could get Rob's images or whether you get something actually more interesting that comes out of the chaos that's generated by that. It would be great to see.
I'm sure it's in your bibliography in the studio, Delanda's book, War in the Age of Intelligent Machines. But he has an amazing thing in the opening of that book, in the preface, about trying to imagine from the historian's point of view how machines have seen the world, rather than the historian embodying the organic, familiar person's view of the universe. And what I was touched by in that beginning of your clip was the Google Earth zoom in to a DRL site, which is like a convention, a genre, and that you all do, where like we start in the outer space and we end up at a point. Weirdly, for a moment, was the drone coming down and finding it. And what I was trying to imagine was how you actually, the building work is part of this larger sphere of aerial activity, the mapping of sites, I was struck that you chose an aerial view of the South Bank. Like, it's not the normal way in which those brutalist monuments get looked at. And I think what Smithson called an aeriable sensibility of sculpture and form way back in the 60s is in a way becoming an operational technique in which all of the problems or all of the things that we have to think through are put into that vantage. And it might be a little accidental right now, some of those things. Like, I keep seeing it over and over again. One of your drones has escaped and it's watching the work of his friends down below. But I think to invoke that more as, instead of the desktop camera and you as designers sitting in a studio space that's very familiar, you're dealing in a realm in which, very much like the drone operators now in Las Vegas, that is the vantage by which we understand the world. And I think the more you can, it's no longer a single camera, even the cinematic 20th century bias toward one point of view that jumps in montage from one point to another. It's that you're seeing more like, 20 camera angles simultaneously that are somehow literally being used in your programming to make these things not run into one another, but also a way to start to describe your world, to be an incredible thing to start to claim as your own kind of discovery out of this work. It's a completely different sensibility of seeing the work and not just undertaking some research. And I think the more you can force that into the description of it, the more it becomes this strange alien world that's multi-dimensional in more ways than we can count, almost, where time itself becomes a kind of constraint in it.
I think Stephen and Brett have touched on, a very important part of the project, which, one thing is how we think the world should be and how we see things, but actually, really what is at stake is how these machines see the world and how they see each other, and how those decisions are actually really predicated on their own agency to take decisions. I think that there's been a conversation about this siting and pavilion and this other kind of attempt to make space. Honestly, I would kill it from the conversation, because I think it makes such assumptions on certain things, where what I most appreciate about the stuff that you do is this spirited work of working with these materials, working with the machines, trying to understand actually what the machine should see. And Stephen pointed at, is it looking for a kind of ideal version of what it should be building? Is that the communication strategy? How does it respond to that precision, imprecision? I think it's very well and commendable that you guys are going to print something in 4 years. The question is, are you going to approach that with a kind of open perspective, or are you going to try to dominate something within itself? To be honest with you, should be radically opening up a new territory, instead of reinforcing a kind of caricature of a certain kind of world which becomes like the experimental test. South Bank, for example, doesn't reinforce the need for this kind of deployability, while at the heart of it, that whole choreography is a beautiful thing to see happen. You can imagine the qualities of not only the product of these kind of formations happening, but the excitement of people actually and the wonder of trying to see this whole process actually unfold. So in a way, maybe that reinforms this kind of idea that the material has a life cycle and it could be redistributed and it could be part of this kind of more spectacle of things. or it's just that it's something that actually is yet to be defined. But I think at the moment that you start to introduce techniques that are not necessarily part of the same way and the same spirit, and you give it such a presence in the presentation in a way, I feel like you're missing an opportunity. I feel you're starting a process, and I'm more than, let's say, open to the fact that you'll achieve something. But you have to have that same spirit to continue in the next 3 or 4 years to discover, I think, new possibilities. We don't need more systems to reinforce some of the challenges that we've been working on here for a long time. We need young kids to be like, you know what? It's been done, fuck it, we're gonna do a different way. Difference for the sake of difference is important because at least it makes you challenge the questions that you're gonna ask about this stuff. These sculptural qualities, the helix, the economy of things that Patrick is saying, I think is a really important thing. Because you see the description of that is just a line. That information will be complexified by the choreography of how these machines that have a certain agency negotiate that. How the materiality and the distance and the environmental factors influence that. That's a world of complexity through simplicity that is at your fingertips if you want it. And I would suggest that at least you give legibility to that, because I think at the end of the day, if it's just printing, the world is full of people talking about printing. This is more than printing. This is vision systems. This is thinking about machine learning. And I think you've approached it in a way that has a lot of, I think, not only charm, but it has different conversations on the table. I don't think there's a dominant conversation. So if I was you, I would be open-eared and listen to things and try to find a way to continue the project in a way that I think brings on to these conversations of those art experiments of the land artists. I keep thinking of Roxy Payne as a really important project. He has different projects. Some machines are just squirting materials, then he has other synthetic trees that he deploys in landscapes. This paradox and ambiguity and synthetic nature, synthetic formation, I think is just a really interesting territory. So it's not a criticism, but it's more continue the speculation. And I think, you have 3-4 years to deliver something. I don't want it to be something that's familiar. I want to be surprised. And that enchantment,
there are constraints to those research grants.
I know, but something though, there's a really big difference.
But there aren't constraints, they're not the same constraints that DRL can speculate. DRL can always push beyond that.
I know, Rob, but what I'm really saying is like, you've won half the battle, and now you have to fuck with the system. Because if it is that the grant is going to dominate the way that we approach how we work, and we don't make a meaningful kind of putting forward that these things actually start to open up a new territory, we're gonna lose. We're not losing a battle of can we print, or we're gonna get money, or whatever. We're losing a battle of the authenticity of why we did it in the first place. And I'm just stating that as something to consider. We're starting a process, we're not finishing it.
Yeah, we haven't lost anything yet, we just started. I mean,
that's all I'm
that's
saying.
The first thing. The second thing is, I think...
This image, this idea that this is something that's something so meaningful, I think you step back for a second and say, it's an attempt, and it's an attempt for the kids to try to do something, and it's an attempt to think about it, and we need to do hundreds and thousands of versions of that stuff, and they're more than capable of doing it. Like, seeing the kids working on the stuff, seeing failure and bringing that back, having that complex conversation, I think is beautiful. I don't use words like beauty and stuff
we're not
like
saying
that.
we're not saying much
like,
different,
I understand
except for
that.
one aspect. But for instance, I would say that Theo's and Brett's comments are basically showing that you've produced enough interesting work that we can start to speculate on more and more things that can be done to it, which means you've opened up a whole field rather than closed one down. And that's exactly what we wanted to do right now, and you guys have done it really well. As for the criticism of the image and things like that, I support them on that, and I would say I agree with the comments that these two things are different. I mean, we can't deny that. But what I support them on is that I think design's a very messy process, and I think design experimentation is a messy. And what I mean by that is, it means we sometimes have to do multiple things in parallel and recognize that some things are ahead of other things, and some things take some time. So this might not have the same material effects as that, simply because that was one thing beyond what one can focus on in a one-year research. Having said that, it still embodies the order of the trajectories of movement that start to describe a geometrical order that comes through flight in local negotiation of autonomous decision-making. And for that reason, I support all those design speculations, because they're still stretching the understanding of how multiple robots can collaborate to actually produce something like that. So it's very easy to kind of dismiss an image like that at a superficial level purely based on its character. But if you look at its order, there is a logic there that fits completely with the project. And so I guess what I'm saying is we have to categorize each thing. I completely agree with the ambitions of that this can go much further. And I think particularly with the idea of collective localized vision, it is a completely different way of seeing the environment before you do anything, let alone how you might do it over time and redo it. But I think they've already started to speculate that by the fact that they're arguing for a time-based process that can be continuous in a sense, where it's remelting and reconstructing. So I think they're already starting to articulate something beyond just the idea of an object as a, like, design for them is not just a single object, it's not an idealized form. And I think that's the mistaken identity in this. Of course, we still recognize an interest in design character coming through flight behavior and through the mechanics, and they've explored that a lot. And the models still are very expressive, and I think the aesthetic of the models is deeply interesting, but at the same time, there's the idea that it's not one object. It is almost like, I think, a lot of the Kapoor work that was referenced before. Like, the Kapoor models, you have to understand not just one, but the series of them communicate that experiment. And I think it's the same here, that what we're looking at is a series of work that span multiple materials, multiple flight experiments, multiple vision, and that's what actually communicates more than the aesthetic of one particular image.
I support the project 150%. But, and I think there's a big but, the work of the last 3 weeks to try to force this into a conversation, I think is good as an experiment, if that's something to tease out like a dirty habit. I think the reality of the things is there's so much intelligence that they've learned through this, like seeing all of that vision system, seeing the experiments. I don't think it does justice. Like, for me, it's a forewarning. When 3/4 of the panels focus on the last 2 or 3 weeks, and that was symptomatic of my previous team that didn't present any of the research that they've done. I think it's a problem, because I think then it's not a problem of how we see it. We continue. Tomorrow's another day and we're back to work again. These guys are bringing a certain level to closure, and they need to wrap it up. But at the same time, it's a new beginning. We don't want them to sort of just put a book on a shelf and say, hey, I came to the AA, I did something, it was cool. We want them to continue, and they will. They'll continue with you. The question is, like, to continue this project with that authenticity is, I think, just such a meaningful thing to really put legibility
they will.
on.
I think they're just living dangerously. They're prepared to do a lot of work in the last 3 weeks. Like, I mean, I think it's congratulations for doing a lot of work in the last 3 weeks, rather than just kind of dusting your hands and saying it's done. I think live dangerously. It's great.
There's been enough dangerous living, I think.
Go for it, Jelle.
I mean, 4 of the commenters made really interesting points. Theo mentioned landscape art. Brett mentioned the Tower of Babel. Elena made a very beautiful comment on how this is Italian and very Catholic. I think that was very apt. But the comment that nailed it for me was Stefan's notion of the sublime, and I think that's very true. But let's say these are 4 attempts to sort of appropriate the project culturally, and I think work can be done on that sense. So maybe those 3 panels written, maybe you could use that area for that effort. And your comment on the sublime reminded me of a beautiful article of Herzog and de Meuron. There was another comment of how this project sort of interweaves the natural and the technical, and that article of Herzog and de Meuron touches upon that, which was I failed to reproduce it accurately. It was about these Chinese pebbles where holes were drilled into it, thrown back into the stream of water where erosion continued to form these elements. And this is kind of a fairly apt reference in order to frame and appropriate your kind of your work, right? You need to you as a creator, you need to understand your work the best. And I think, you know, all of this admirable work, you're really lacking in sort of the cultural understanding of what it is you're doing. So I think there work can be done in that sense, right? It's all there, but I think you can, you know, others are at the moment perhaps understanding it better than yourself, possibly. Yeah.
Thanks so much.
puntatore. Il puntatore. Non è un avvio. È il puntatore per quello lì è il puntatore. Io andrei poi con caldo. Sono sudato.
How'd it go?
Not bad, man. It's alright. Hey.
Want to test if this works?
Where's the freaking board? Oh, okay, it's at the back.
log in?
Adi?
Just want to make sure it works before everyone comes in.
Yeah, sure.
G-A-U.
On mine? You found it?
G-E.
Alright. G-A-U.
G-A-U. G-E.
Thank you.
L-A-N.
Okay, perfect.
No, incorrect.
G-A-U.
G-E-L-A-N.
Thanks, man.
G-U-A.
G-U-A. तू का nervous होता है? अबे नहीं था. Still wrong.
So when you guys present, make sure to speak into the mic, and when you're answering questions, I'll give you a hand mic.
Awesome, man.
Always
Thank you
have
so
it.
much.
Yeah, come in and break it
It's on, huh?
Slides.
It's alright.
सगळे slides एकदा run करू.
down. All right.
Should I run all the slides?
No, you're good.
Huh? Yeah, I've run through them. Yeah. You're good. Let's get this. That's fine. We've done enough. That's enough, no? Big volumes of माझी work काय टाकता आलं. Lights enough lights. बघ टाकता आले तर टाक नाही तर राहू दे. One more? No, it's fine. Just keep them with you. Yeah, yes. Let's get this. World Cup final, guys.
Is it plugged or not?
Yeah, it's plugged.
If I play here, it plays there. No, I don't want to play there.
Huh? Why is it not coming? Why is it not coming? We're showing it on the big screen. It's fine, it's fine. Let him see. Dave.
Okay, what was first? This one?
Mm-hmm.
Which one is that?
Plastic.
Yeah.
That was the PVA plastic.
PVA.
PC. PVC.
PVA.
PVC.
And thermoplastic.
PCL if you want. PCL if you want. Thermoplastic.
I don't think I'll manage.
It's fine. Thermoplastic.
What do I say here?
So now we noticed that that this one wasn't adequate for us. So we needed. So we set these two against each other.
Three plastics, and then we tested them.
And it's clear that this is architecturally much more.
Yes. Okay. Yeah. When are you gonna go to show the models, right? I don't mind. Whoever wants to. I'm just saying when you go, pick those 3D models and give them in their hands.
Yeah. Actually, the prototype should have been a bit.
Yeah, should be.
It's too far.
You can't move it, no?
Yeah, like.
Rams.
In the corner.
Jade, do you want to do this one? You know what to say for it? Better. Fine. Yes.
So you want me to say this one, right?
Yeah.
Test.
Instead of changing something, I'll tell you what I have in mind. Okay. So once we started testing,
Leave it. I won't get it. It's fine. I'll say.
Good afternoon. Our team name is Boundless Inflations. We are Pierre, Ritesh, and myself, Esteban. We are in Shajes Bouchan's studio, and as you already know, our brief focuses on developing architectural and fabricational systems with the assistance of the robotic arm. Therefore, our main interests were focused mainly in exploring the systems with the assistance of the robotic arm, exploring materials that can be phase changing, volume changing, and programmable. In terms of phase change of these materials, we're looking for an architectural system that embraces different material states. When we're speaking about volume change, we want we feel as a strategy to adapt, react, and occupy space in time. And the programmability, we want a design and building system that can be fully automated. Therefore, our research began with material research. We tried to inflate different types of plastic like PVA, also PVC, and see how they would react to both temperature and pressure. And lastly, also PCL or thermoplastics. But at the same time, we always went back to the idea that it is the robotic arm, the one that should handle these materials. So with both PVA and PVC, they weren't strong enough in order for the robot to be able to control it. However, thermoplastics proved to be well and stable enough material for this experiment.
So with our first thermoplastics experiments, we started trying to identify the source of inflation. We started sealing an environment and trying to inflate from this location. Eventually, since it reacts with temperature, we cooled it down with cooling sprays. The material, however much better it is than the other materials, it's still highly sporadic. So we have to control it. We have to control the way it reacts as well, how we go about using it. So we attempted originally to constrain it in certain manners, and then try to articulate these constraints, but it still wasn't achieving. We then moved on to trying to achieve similarities on the computer and trying to get digital simulations of what we were doing. And back to the material world, we're seeing that even the direction of the source of inflation guides the type of inflation and the geometry that will come out. Almost immediately, we also said that these things are going to have to be aggregating together. So the way they come together, how well they stick together, how many you can have touching each other, were all important features that we needed to explore from the beginning. So then we started seeing how to apply it in a fabrication world, where the industry has been inflating plastics for a while now, and the bottle industry is most especially, where this system is proved and tested. We might try to replicate it. However, we gave ourselves the challenge of removing the outer shell, the final to achieve a final geometry that is not restricted within a mold.
So once we decided that we don't wanted the mold, we started designing the preform. So you have the flat sheets which you cut down and roll them up, and then you seal the top and the bottom edges of those flat sheets to make it those kind of blank molds which you can use later on to inflate. So you have this set of blank molds loaded whenever you wanted. So once we had the preform, we started seeing what all different sizes and shapes you can use and what are the different outcomes it can give us, like going more vertical and horizontal. Then moving on to further studies of size and shape, we started seeing that once you have a slender preform which has even thickness around it, once you inflate, you get like these breakage points in the middle, which then affects the inflation. If you have a linear one where once you start inflating, you get thickness variations, which breaks it up. And once we got the ratio between the length and the width, you get kind of these proper inflations. We also tested a linear one, which had a long strength and quite a thickness, which got slumped because of its own self-weight. So after doing all the studies of the preform, we came to the conclusion that the average inflation size and the average inflation preform size, which was around 10 centimeters, safe length. So then from the preforms, we went on developing the system. So you have a network of air, you place the preforms, and then you inflate those preforms. Then we started designing the end effectors, which could be utilized to perform these actions. And these are the tests where you identify the points, and then you have the end effector, which on the other side has a gripping mechanism which kind of holds the preform, which you then place to the position and inflate. So then it goes to the next position, places and inflates, and then it keeps on getting the information continuously and then keeps on building up the whole sequence. And then this is a junction detail where you can see that once you start inflating, we're using the cooling spray to hold the shape of the bubble when needed, and then keeping on adding and connecting those junctions. So then later on we said that the network was creating a really kind of constraint thing, so we wanted to remove the network. So we said that what if we could inflate directly using from the preform itself. So you have this individual source of inflation. So we took the preform and we placed it on the robot, and then whole action was performed using the robot. You take the preform, you take it to a heating chamber, it goes to the heating chamber, it uses the 6th axis, it rotates it clockwise and anti-clockwise to heat the preform. And once, since it's a thermoplastic, it heats it up, and when it's heated, you kind of give the information of the next position where it wants to go, and then it goes to that position and inflates. Because the material is malleable, it inflates. And then you have the detaching mechanism where after inflation, the robot comes out of the inflated bubble, and then it is ready for the next inflation point. So after that, we started studying different end effectors which we can use, where you have a diverter and the needle to grip the preform, and the diverter which are connected to the needles, which are used to pass the air from the needles, which will be used to inflate. So then, as comparing these two systems, the first system took us 15 minutes per inflation, whereas the second system, in which you have the preform directly on the robot, took us 3 minutes per inflation.
Establishing this, we saw clear that this was an aggregation strategy between the inflations. So we are proposing a compression mechanism, and this will be identified in our architectural system, where from the form finding through the structural analysis and the deployment of the inflation points, these would all be fully compressed structures. With this in mind, our form finding studies began with very basic primitives, triangles and rectangles, and seeing how these react to as a fully compressive mechanism. And later on, we saw that the anchor points of these were very important and would give us different results, even though the geometry, the edge geometry, the boundary would be the same. If you constrain different points as anchors, you will always have different results. And this is also true when these anchors are also moving in a vertical level, where we can see our architecture adapting to topography as well. We develop different tests to identify this. And in terms of the growth strategies, we started to match these primitives and see how they affect each other, and how these joint lines start to become very important structural features for us. As you can see here, the system keeps growing, starting from a very basic primitive until you can get to very complex geometries.
Once you've done the form finding, we took it through a phase of analysis where we vaulted it and identified where the forces were going through. These forces could then be articulated by manipulating them and stretching them, and to really bring out the intricacy in the vaulting that we'd like. This is one very orthogonal shape, and then we can also do it in a very much less ordered and less mannered way. So once we have to populate it, we had these meshes, and we said that we should try to populate on them with these spheres as well as possible. Our initial instinct was to populate them with a primary part and with a secondary part, where one's more structural and the one is less structural. So we went along the edges and we found where those forces were, and we just laid them on. When you analyze what comes out of it, it's a very feeble structure. It's a one layer thick, which is not quite what is necessary. So we started finding ways of trying to thicken the volume of inflations that we could have, and we started trying to create these point clouds where the inflations will be identified in accordance to structure or to fill, and they're scaled in accordance to them. So the structural ones will be smaller because they retain certain strength, whereas the larger ones can achieve certain sizes and even start offering other characteristics, possibly translucency. So to then start articulating those inflations, we're manipulating the force diagrams for these primitives and trying to deploy the structural inflations in a designed manner. So an aggregation strategy was developed. So we analyzed the surfaces, we had the forces, we put the forces on heat maps, and then the aggregation of each of the inflations will be attracted and scaled dependent on the forces on the surface of the mesh. So we're ranging from 75 millimeters to about 400 millimeters, which is a bit more than what we've achieved, but it could be speculated upon for the future. These heat maps can also offer a bit more creativity, where we can actually test out different styles and just going about and seeing what else we can achieve through this tool that we have developed. And then we started looking at the meshes and possibly an idea of thickening it, because might not always be necessary to have. It's a very, very laborious process, so it might not always be necessary to always have a high density of spheres everywhere. So some places could actually afford to be hollow in certain areas, where thickening the mesh might also give us an opportunity to curtail this. And we developed a system of code to try curtail this in our own way. So we had thickness, we're identifying the frame areas, we have an aggregation system that can be controlled, and then we can also control our own specific what we'd like to come out of it on the inside as for lighting. So the thickness would be controlled between the footing and the center of the vault, and we can start creating a bit more structure towards the bottom. And it can be done in various ways. The thickness in the top might also be interesting, and so on. The main fill area could also be articulated, can be brought out, could be made interesting, could be stretched, and the density of the bubbles could also be varied within a range of interest. So you can also achieve high density from similar shells. You can also reach higher density ones and lower density ones. Flooring became an area of interest a bit late on, but it's about thickening it and replicating the forces on. And then lighting on the inside, where we'd like to organize possible shadows on the inside. So the smaller the bubbles are, the less light will get through, and so we can control it a bit, the lighting on the inside.
So once we had the information about the population and the points which we got from the mesh, which has been populated, the next target was to transfer this information to the robot. So you have this set of points, and then the robot takes a vector and draws it along the inflated geometry. It stops there, and it stops at a safe length, which we have decided according to the preform inflation size, and it goes and inflates against the existing geometry, and then it keeps on using the same information, like traveling against the vector and inflating against the geometry.
So having this in mind, we have a very lightweight material and a lightweight end effector. So we started to analyze the possibility of different sizes of robots. The first thing we did was test the reach of a medium-sized robot and a small robot, a light robot. And also, what would it mean for these two to react in a similar manner, to build the same kind of structures that we want? So we took one bolt and tested how many robots do we need for, how many big robots and how many small robots do we need to achieve this, in order to see in which way both the small or the big robots could be used in a very strategic manner. And by putting them together, we established different strategies. Definitely, if we want to build on site for the big robot, it would have to be on rails. And it's pretty difficult to move it, and it requires a lot of effort. But for the small robot, it doesn't require that much effort. So we started to envision a system where the big and small robot would work together, completing each other's path whenever the big robot would reach to the maximum reach that it could get to.
So once you know the arch which you want to build and you have the point information, you give this sequence to the robot. So it goes and takes this points information and it keeps on going to the position, inflating. It takes the preform, it goes to the next position and inflates.
So with all of these ideas in mind, we established ourselves, we envisioned a setup of a space where we already included all the elements and features like flooring and a thick mesh in order to see how these robots could build this. So the setup would imply that the big robot and small robot would have to have certain adaptations. The big robot would be in a unidirectional rail to have as little movement as possible, while the small robot can be on tracks and on a vertical lift, given its lightweight. So when you define the structure that you want to build, then the rail is placed and the two robots go into place. They would pick the preforms and go into place of inflation. If we would want to achieve, for example, the primary arch, the idea would be that the big robot would start building first the foundation, while the small robot keeps completing the footing of this arch. This way, both the cantilever and the footing grow at the same time. And the same is true for the other side. And whenever the big robot already reaches its limit, then the small robot can continue building the top parts, and while the big robot would finish the floor. And in that way, there would be a very strategic manner for the two of them to complete a structure. When you see what else you need to build after that, then all the strategies depends on how many movements you have to do with the big robot, and the small robot would always follow these movements of the big robot. So once you have the structure, also these two robots can start to cooperate in how to build the infill of the geometry, the surface, in which the structure would rest.
So once we got the information that the end effector is really light and what we're inflating is really small, we started thinking that what are these different types of extensions which you can use on the end effector, which can affect the outcome which is coming out of the inflation process. So we started attaching these extensions to the end effector. So once you inflate against those extensions, you kind of get like different outcomes which is affected. So it's like it's in the process, it's constraining the inflation, whereas in this you can see that the one side is completely constrained against the inflation. And then these constraints can be used later on for different things like floors or edges, or maybe some sort of curvature where you want a circular to a flat finish, or some sort of furniture or something. So we started understanding that how we can use this end effector more efficiently by connecting these small extensions. So once we had the extension, we did a small test where you kind of take the preform, take it to the position, and then it's on the big prototype standing at the back. You start inflating, and then you can see that it's constraining the inflation on one side. And then once it's finished the process, it kind of detaches itself from the inflation, and then it is ready to take the next set of information which it needs to complete the whole sequence of that side. So you can see that it quickly starts making one side completely flat. as in making one side of the whole thing completely constrained.
The culmination of our analysis and our studies has resulted in this sort of model. This model it relates to the scale of the house. However, it's just we're identifying our production method, our fabrication method, and trying to articulate it to the best manner we can. We're trying to bring out certain features where some of the later features do not yet appear on it, but it is already evidence of the way we can go about with this sort of model. A lot of these models were extremely heavy. The processing power required for it was extremely substantial. Anyway, we tried to achieve the best, the most articulated form that we could. Anyway, thank you.
So going to the models, this first is the proof of the inflation through a pipe network that we developed with a robotic arm. These models over here are some of the experiments that we did, as in how could we constrain these inflations in order to bring some sort of order to it, or for them to start doing what we wanted them to do. Here's a catalog of the different end effectors that we developed for this. And this model is the biggest inflation we have achieved so far. So it's important for us to keep a sense of what's the real scale that we were trying to achieve, and therefore how would each one of these inflations be performing. These are the printed models that we could extract from the digital models. We tried to make them as intricate as possible. They took a long time to print, but however, they contain a lot of information of how the gradient and how this whole system starts to place each one of these inflations. These two models also represent a little bit of the difference between having a system where the inflations start to connect from one another and they get inflated individually, and where you have an inflation through networks. With these models, we started to test also what's the different thicknesses that we can have in both the same bubble, or also in different ones. So it kind of like, for example, here it kind of goes in a gradient. And this model is also one of the first models that we tried to do as a spatial strategy. And this is our prototype, where we tested different features like the footing or the flat edge with the assistance of the robot.
Can you tell me why you felt that the material that you were working with should be resolved in compression only?
First of all, because of the aggregation capacities and the scale that we would work with. We tried at bigger scales, but for the robot to be able to control it, we established the scale that you can see right now. So then it became an aggregation system, where we thought that if we would create anchor points in compression shells.
Now, I mean, the reason I'm asking is it's quite clear these things stick together. And I've worked with thermoplastics, devilishly hard stuff, I have to say. To be congratulated in terms of what you've done. But if it sticks together, then why can't it take tension?
Because once you start having these 2 or 3 bodies, and it works really well in compression. Once you start pushing them, since when you inflate, the layer thickness is so thin that because of the tension, it kind of breaks in tension.
I see. Well, I sort of see. I mean, it just seems to me that 2 layers of a mat of these things, if you could control it, would be a space grid. Anyway, I'm sorry, that's being terribly mundane. I'd pass.
No, I don't think it's mundane. It's very much the point. I would have the same question, but also if you do it as a compression aggregation system, we would have to look at the compressibility and compression strengths of these bubbles. And I have quite a lot of doubts there, particularly with what you have actually created. I mean, of course, you could imagine a thicker boundary, but what comes quite clear quite quickly in the model here, that's where my suggestion comes in, that what is going to be very hard for you is the concentration of loads in these initially quite elegant and thin footings of these shells. I mean, quite a surface structure where you have very much distributed stresses are acceptable, and we've done a lot of lightweight structures. The problem is always coming towards the edge, and in particular the foot points where you have a concentration of loads, and that becomes very, very tricky. How do you manage that? And you seem to recognize it because you end up with these elephant feet as of recognizing. So, and I congratulate or commend you for that, but at the same time, it is a pity also. So I wonder what other strategies there could have been, and what strategy I see is in terms of the bubbles, that maybe there's the same material, but you need to really go into dense, solid pellets, plastics, or rods, which maybe, and then the question is how do you transition from those into the bubbles? Maybe kind of branching or bundling of veins running up and collecting and bringing to a point these forces, so which starts to talk about a bit of a more of a differentiation you've already been doing. So nearly a multi-system, while simply perhaps still a single material project might become a multi-system project. And I like the way you've done the differentiation between primary ribs, which are smaller, and I guess much thicker, and then those bubbles which deliver envelope and insulation and all of that, and translucency. So really much appreciate and like that. But the next step would have been to perhaps treat those footing points, because in the end there's a strange feeling of a lightweight project which seems strangely overdimensioned in its volumetrics.
Yeah, I think there's a lot of aspects of your work which are very comprehensive and very good, and you should be commended on. I think what's coming out of the previous two comments is that actually one of the bits that is missing is the material testing. For a start, I do think it will have very limited tensile capacity. I do think you will find you have large feet. I do think you'll find all these things come through. But if you actually have the testing and the numbers to go behind it, then it adds a bit more rigor and a bit more reality to what you're doing. I also think that using some of these, you can see the largest one you make is not so translucent as to be a window. So maybe there is a small exploration into the plastics which are behaving structurally and the plastics which are behaving more as the envelope, and maybe they're not the same material. Maybe that's the next step. But I think fundamentally you should be highly commended on a lot of the things you've done here, so I think it's great work.
I very much like this idea because, in my opinion, you are the first group now who dealt with a size of robotic printed or mated parts, which is really realistic. And it reminds me a bit at these buildings made from ice blocks. And you got something in a way similar, similar aesthetics, but you already have insulation with this kind of material. And you really developed a lot the process how to make these bubbles. And I can imagine everyone knows these water bottles, and they are really stable. You can fill them with 6 bars air pressure, and then they're really hard. So I think it could be quite realistic, finally, to produce those kinds of bubbles which are stiff enough and stable enough. Maybe also translucent if you have the right plastics and the right process. But you already went quite far, in my opinion. Also, I like the idea that you influence the way the bubble shapes just using those kind of boundary parts. I think you went really far with in my opinion, really new process. I've never seen this before, and probably there are a lot of things possible with this kind of technique.
Yes, I also enjoyed the project a lot. I wondered perhaps a little bit about the question of standardization and whether the variation between the bubbles, certainly in the models and what you're drawing, whether that has an advantage as opposed to sort of going down the standardization route. And I thought the point that's just been brought up about insulation was good, but also whether there could be some relation to deformation, let's say like the airbag, that actually the application of this might be less building per se, but maybe in terms of infrastructure where vehicle impact might occur, something where, in a sense, its crushability had value. So I'm sort of kind of veering away from some, let's say, shelter in the conventional sense. And then, of course, you know, if we look at it in terms of the sort of family of inflatables like PTFE, pillows and so on, the acoustics, the drumming of the rain on top of that, how would that sound? And again, could that be an asset? So these are questions that I think the project's raising, which are super interesting. And but I'd kind of push the variation. I think this question of tolerance in relation to standardization and variation in that, has that not got something you could push further?
So, can I, I really like the work you've done, and the idea that actually having spent a lot of time understanding the properties of the scale you can inflate, and it was also mentioned previously in terms of the shape. I think with the form of it being a series of bubbles, you are right that it has to start from a compression point of view. But if you go back to your early research that actually says that you can actually change the shape by the way some of the early constraints you give into it, means that you can then create other forms which are not round, which then gives you the idea to actually expand it further to take tension. Because by actually breaking it, the rectangular form of inflation you have allows you to lap it in your gluing process that allows you to then start dealing with. It will be quite interesting to bring a combination of different forms and shapes by actually using the circular shape and the rectangular or trapezoidal forms to see what else you can do, how else you can expand it. To me, that's one of the most interesting things. The other thing is, I believe you haven't explored the variation in the size of the forms, because the variation, you've done it in the right way. The smaller members are the lower section where you've got bigger stresses, and the bigger ones at the top. But I think there are other, in terms of the material, there's other way of actually making it more translucent, as was mentioned, but also recyclability. Because it's a material, you can then look at how you collapse the whole thing, reform it, and reuse it. So there's a massive variation of what you can do. But in terms of the work you've done, the research you've done, I think it's very good.
In relation to that comment, some part of the project that really struck with me was when you are printing these lines on top of the spheres that you were making, and it did not completely succeed, but the lucidity of the surface really stuck with me. And the previous project we discussed sort of drove after an aesthetic
as a framework for concrete. And I would imagine that there are incredible materials you can use. I think you have a framework more than a material itself. That's all I want to say.
Yeah, I just I want to commend you, I think, on terms of the novelty of exploring, I think, something that is a kind of familiar aspect in terms of using robotic arms, but actually informing it now with a process that I think in the beginning was a kind of experiment. And I think you've stuck with it for a while. I really like this kind of mosquito-like quality of inflations, and I think Albert was mentioning your preform. The preform right now privileges the sphere, but within the preform pattern, you could actually have very different kinds of strategies for what this incremental inflation could be, and I think that could respond to maybe some of the criticisms. One of the things, though, I think that is in an open conversation, I think, with the project is it's in the digital world right now, you've deployed this as a completely space-filling system. The whisperer strikes again. And to be honest, I'm sitting next to one of those early models, which was incrementally built, and aspects of transparency, translucency, gradation of materials. One aspect is in its inflation, how much you inflate, but another one is its foam-like characteristics, the subtractive and additive features that could actually flip from one to the other, I think would be really useful, because this guy creates space that then potentially could have a different kind of way of interpreting it. One could be thermal aspects and all of that stuff, but on the other hand, illumination. A window here, the whole building could just be a translucent body. We have, I think, at stake a different way of thinking about these things, and the pressurization aspect of it is obviously inherent to its inflation, and I think there's a lot of stuff that you guys should sort of push further and describe. I think the ways that you've been dealing with the generative form making, I think you can explore that. When you see these kind of cross sections, the overpacking of these kind of column-like shell feet, it maybe is necessary, maybe it isn't. And I think you can grapple with this in an iterative way and try to find something that doesn't become so intensely heavy in computation to try to run all of these things at once. But you can try to use your ninja style capacity to work between these different things to try to actually speculate beyond what you're doing computationally and what you've managed with some of the studies. I think you're at the moment where you guys could really try to problematize this whole process a bit further and take on board aspects of illumination and closure. What is the take on your side of things? I think it's a fantastic project because I think it puts on the table certain questions. It could be many different kinds of shapes and forms, you know. Greg Lynn's version of this we know, and I think it's a good anti-model to this model, which is still using robots and plastics, but instead of scanning and using component-to-component assembly, I think this process is beyond novel. I actually do think it has a lot of merit, and you should really continue to try to develop it, because I do think that there's something at stake here. Sorry.
I think one of the understated aspects of it is its primary merit is its power, right? Just try.
All right, we're going to pass the potato again.
That it is so simple, that we can almost envision that you're giving agency to the robot to now be able to kind of behave or do something with that capacity. Right now it is just following instructions or predefined instructions, but because it is such a simple system, it is amenable to be robust, which means now the robot can safely begin to take certain decisions, and that's a kind of aspect that I think you can also situate within the book to kind of, now that you've gotten this far, the next step would be to kind of, what will be the next step to enable the robot further, right?
maybe one thing just to expand on that. I also am a big fan of the project. I think the material deployment was very novel, and the way the teams worked on it throughout the year has constantly progressed in quite a rigorous way, never straying too far from what constraints were real, but you would try to challenge the constraints. I think that's fantastic. I particularly think these two photographs demonstrate for me the best level of the design at the moment, where there's a clear indication of material placement as something related to the shell itself, which I think is very interesting. I think the thing that I would imagine would be the next step would be that, seeing as we have this thermosetting plastic and we're deploying it using that property, we could also then come back and manipulate it afterwards. So for instance, perhaps some of those edges of the shells, you might be able to grab a robot arm and remelt the edge and kind of pull strands down to become glazing mullions or something. I think that could be pretty interesting. Or for instance, ties, like tension ties or something, where you pull a cell from the top of one shell and you draw it across and connect it to somewhere on another shell. I think there'd be a lot of opportunities for additional things that would break the kind of language of what you have a little bit, but probably add something else that would add extra functionality and curiosity.
Yeah, thanks.
everyone. Thank you for being here. We are Team Information. These are my colleagues, Dieter, Kyle, Sarah. I'm Jonathan, and we're thrilled to share with you today what we've been working on for the past 16 months for what is the proposal for the new ZHA architects. The studio brief is divided within these 4 major terms, and we've interpreted these within our own terms. Biomimetics is the study of natural organisms to solve real-world problems and formal strategies. Kinetics is the movement of not only a single object, but also an interest in the exchange between 2 moving objects. Semiotics is the study of signs and the transmitting of information across several receivers. And we're interested in crowds, not only large bodies of moving organisms, but active and passive, dual swarming within one system. And so our thesis is focused mainly on these complex kinetic objects that we populate the London Design Museum with an interest in, again, this dual swarm where people and objects negotiate each other. Zahadid Architects is an international firm, as we all know, with major global appeal, with projects all over the globe, with their headquarters here in London. And we focus in on the new proposal for the headquarters, which happens at the London Design Museum, located along the River Thames. We're interested in this building because it's along the river, with this sort of public front, and the history of the building as a historical building. We look at kinetic precedents. We were interested in architectural projects that displayed kinetics, where the transformability was also a facilitating program, and changing signals across the projects. So in these examples, the performativity is affected through the kinetics, in that people can access or not access space through the transformations. We also looked at the history of the office, and studied several kind of office layouts through time, with the specific interest in the Hermann Hertzberger precedent for the use of rigid spaces and small flexible elements to create an ever-changing environment. In observing natural systems, we were specifically interested in the mimic octopus for the way that it can assume different postures to mimic other natural organisms, based mainly on stimuli. So that is typically a threat, and it can change its shape and coloration to look like other things around it. We looked at several other organisms for their degree of transformability and their surface qualities for inspiration for materials. Specifically, we were interested in the sundew plant, the armadillo, the dragonfly wing, and the Brazilian butterfly. Through these observations, we started to focus our research, and the first step was to create kinetic systems. These systems that we developed were made by choreographing discs of different sizes to facilitate transformations in different axes and different directions. We were then able to choreograph several arms within one system to allow for a kind of dynamic transformation. We moved forward with our research into membrane systems, where we were interested in a kind of folded surface through origami kind of techniques, a magnetic surface and a pneumatic surface. We were most interested in a material that's called a photoelastic material, which is achieved by sandwiching plastic between UV film. And this is interesting because we can achieve different types of transparencies based on the orientation of the film. And here you can see the photoelastic material allows for interesting variations where the transformation can send signals through the observers. And what is happening here is there's a live stress deformation in that material. We started to define our terms by looking at other institutions for inspiration. We were interested in set design for the reconfiguration of space through vistas, changing levels, colors, by the use of kinetic systems. And we were also interested in the library for the use of several reconfigurable spaces with dynamic program. In focusing in our crowd section, we were interested in low and high, collectiveness, stability, uniformity, and conflict within large moving bodies. And these are two precedents which were interesting for their research in crowd activity. The Bank of America precedent used research where they attached trackers to their employees to gauge happiness of the employees based on spaces they occupy. In the Pixar example, one organization with several departments uses a single gathering kind of space to facilitate creativity and the exchange of ideas between people that would not otherwise interact with each other. And this is the research of a psychologist which we observed that demonstrates that the peak of comfort in the workspace is at the psychological level, and this is achieved by employees being able to have some kind of control of their environments in the workspace. We did a survey at ZHA Architects to find out that team sizes changed during the phase of a project. So this informs a somewhat fluctuating office space. And we were also interested in the type of meeting scenarios that occur in the office environment currently. Starting with our design proposal, we were interested again in the sites for the kind of public riverfront boulevard, for the views across the river and this major building front that is open to the public, and for the Chatham Street adjacent, which is a sort of tight corridors with these connecting bridges. The existing building is a reinforced concrete construction with a fairly even column grid. And the first prototype that we developed was a direct inspiration from the kinetic systems, where a desk can transform into a partition to direct the movement of crowds in the space. In inserting this in the system, we found that the footprint of transformability was too large for the space. And this inspired our interest in maintaining the column grid to have that system executed in the space to facilitate different sizes of teams based on the postures that they assume. In this iteration of the desk, you see an interest in a plug-in kind of desk system where 3 desks work in a single arm, and we change the geometry to facilitate the needs of the worker at the time. In executing, again, this desk within the space, we can achieve a variety of layouts in the office, again, that can inform team sizes that may be changing. In the most recent iteration of the desk, we again use inspiration from our kinetic systems, where the desk on the right is the most recent one, and it moves in both directions to facilitate a far more dynamic set of options that can be used within a single office space. In this animation, you see the desks sort of working together semi-autonomously to assume several postures. So in this final posture, it's perhaps more private, where people are secluded and teams can work more privately. We were interested then in how these postures can influence circulation through the space. And you can see clearly on the left where the desks are in a more private posture. Circulation across the space is more difficult, whereas on the right, they're open and can encourage a type of collaboration between people moving and people sitting. This animation demonstrates the semi-autonomous desk facilitating 2 teams of 3 people that are working quite separately from each other. A transformation occurs where the desks change posture to facilitate now a team of 6 people. And in the final posture, the desks come together to create what we were quite interested in is a casual meeting environment that can be executed fairly rapidly in the office space. Continuing with our interest in maintaining the column grid, we played around with some ideas of a spiral staircase that can transform to restrict and allow access between vertical levels. We were interested in having destinations along this vertical ascent where people can rest or actually set up work. And finally, we developed this mezzanine where the stair leads to a platform. And in the most recent iteration, we can accommodate up to 16 extra people. In this next iteration, we were interested in having an interlocking geometry, as you can see in the plan, and also developing a desk system on that surface that works in the same sort of mechanism as the petals do. And so here you see that we create a new work datum within the office space in a building that could not otherwise accommodate the demands of the program of the new ZHA office. In this animation, you can see that the mezzanines bloom and connect at one moment along a slab and bloom on demand based on the needs of the office environment. Continuing our interest in access and non-access, we were interested in having these mezzanines rotate to allow connections at certain points so that 2 mezzanines can be connected to each other. One can be isolated, or they can work together to be all connected within one new office datum. This is achieved through an asymmetry in profile and a system where there's a sleeve around the column that allows for this rotation. Here we tested several options for the desks opening and closing to allow access between these mezzanines. And we move forward with option 2. This animation shows an explosion of the parts around this column system. The desks have a motor embedded to allow for their transformation at 15-degree intervals. There's ball bearings around the knuckle of the column, and these pedals are made of carbon fiber with ribs embedded inside them for stability. Here you see a section of that detail of the knuckle. And the desks, you can see, move passively from the transformation of the pedals. We were further interested in adding some resolution to this casual meeting zone in the office by having a partition system. And this was the first study we did, where simple interlocking geometry. In the second iteration, the prototype can assume several more postures and can transform from very small to very large so that they can be stored away quite easily and executed to separate a large distance of spaces. We were then interested in sculpting the architectural space by sort of very easily staggering levels to allow different views across programs. That led us to develop this kinetic staircase that can fold and close to separate space not only through access but also through visual cues. On the left, you see what we anticipate to be people leaving an office space to a meeting area and the desks closed to facilitate the privacy that that meeting may need. We developed several postures for this desk that can be executed in the office space, including rotating treads that become shelves in a gallery space within the office. In the first iteration, the tread is flanked by the structure, where each structural element and tread is unique and scaled towards the center to allow for an easier transforming motion and a smaller force. Here are some photos of the model. In the second iteration, we transferred the structure to the center of the tread to give us some freedom to sculpt that tread edge. And finally, in the most recent iteration, the stair is sculpted to match the architectural space. We did several building program organizations, all moving towards a sort of scattered programmatic distribution that works very well with our prototypes that can quite easily reconfigure space through access and non-access. The orange represents intervention, and the slabs are sculpted based on the constraints of the prototypes. On the left, you see a circulation diagram, and on the right, you see a prototype distribution diagram. We did several facade wrapping strategies where there was an interest in communicating internal activity to the public front through changing postures on the building volume. We achieved an elastic effect by overlapping tiles. In this iteration, the internal transformation is registered on the facade, where the strategy we build up to accommodate the program needs, and we wrap based on the distribution of the prototypes, creating frames for the public to see through. We developed these photoelastic strips with ribs that are choreographed to achieve a bending. So you can see in the most bottom video that bulge is asymmetrical based on the ribbing behind each of these. Here you can see a few images of the building volume that helps to frame these complex prototypes that are distributed within the space. Again, the plans and sections are executed where the prototypes are sort of distributed close to the building perimeter to allow for that registration and building form to communicate internal activity. In this crowd simulation, you see that a rotating mezzanine signals that a change is upon the environment, which signals to employees to ascend the staircase. And you can see here the stair working with the mezzanine to assume a bridge posture to allow for access to that mezzanine. In this simulation, you can see on the very top floor that the signal of the staircase sends to the desk prototype, which transform and allow for people to be aware that there may be a meeting happening that they need to attend. In the floor below that, you can see the prototype of the partition executes working with the desks in the casual office environment. This is a rendering of the internal vertical core and how the prototypes intersect and connect different levels. Thank you. We can show you some of the models and demonstrate these initial models that can be, can you show these? Executed by a very simple pulling force, replicating a somewhat muscular activity that happens in natural systems. These are some studies of the stair, where you can see it's a very simple interlocking structure. And finally, a larger model of that stair prototype. Can you show? That demonstrates the transformation facilitated by a small lip that is executed, and the tread can rotate so that when it's in a different posture, a tread can then become a seat, for example. These are some initial mezzanine studies where there was a strategy to have a sort of counterweight to facilitate that transformation. This is the photoelastic material where you can see the live stress deformation. we have several partition studies, and you can see that it's the mechanism allows for a very easy rotation so that it can be executed fairly easily throughout the space. This is a full building model. It shows how the prototypes executed in the space demonstrate a fairly dynamic interior, which we frame through the facade. This is a model of the mezzanines, both in a closed and open posture. And you can see that they rotate together and can connect and disconnect in the space, having both performative and performance qualities. The stair model, we hooked up to a motor that is equivalent to a pulling force that might be in real life. And so it's quite a simple force inspired by these natural systems that we initially looked at. Thank you.
I think he likes it.
Last start. I think you've done an awful lot of work since I saw it last. And it's convincing. For me, it's the thing I like most is the idea that the building has got a population of people and a population of objects that are working in symbiosis. And I think that while one can pick holes in various bits that you've made, the overall quality of what's coming together, I think, is great.
The breadth and the depth of the work is appreciated, right? I mean, this group of designers must have, from day one, have pounded it and just kept going to the very last, right? But so that's, you know, there's a complete exhibition of it, and the work is robust, right? As a critique, I feel also challenged. Because there's a certain hermetic quality to it's difficult to pierce into, such to say. So the terrible thing is that my question to you is a little bit psychological, in the sense that if you wanted, out of your time of the DRL, is to come up with an incredible portfolio and to, you know, to move on as a professional designer, you've absolutely succeeded. There's also the possibility that, you know, I suspect that some of you have been accomplished designers and architects before you entered this program. And this is my reservation, in the sense that, have you sufficiently lowered your professional shield and opened up to other possibilities, in a sense, right? The work we've seen so far is more of a more experimental nature. So I don't know you well enough to comment on that, right? So if I knew you a bit better, I could sort of challenge the robustness of your works a bit more critical. Yeah.
I echo that as well. I feel that technically it was absolutely beautiful. The presentation was wonderful. I can see it from beginning to end. But there wasn't any raw quality of something new, and this is a burning issue, and this is really where we're going to go forward and where we're going to push the boundaries. And I think technically it's wonderful. I just would have liked to have seen something more passionate and raw.
I must say, your presentation was very good. The way you actually, your research and what you've researched was very specific, based around what you're trying to do in terms of the building form. And I think I like the way you've presented, even the images and the models, everything is very coherent. But again, I think you could have been a bit more pushy. I mean, this model is a very interesting model. It actually shows the coherence of all what you've done, but the reality is that you could take it a bit further in terms of how you can bring some of these platforms and stuff together, rather than it being, it appears you wrapped it around the columns, rather than them becoming the columns, working more. So there's still opportunities to stretch some of your ideas. But in terms of the way you've presented it, pretty good.
Just want to pick up on a conversation we had over lunchtime about the effort we put into the backstage and what ends up on the front stage and what will be delivered. And this one is, of course, very design and result oriented in terms of, let's say, all the robotics and interaction intelligence and the scripting logics appear as interaction in space for the real thing and not just producing something which in the end might not have these qualities. So that, and to some extent, you can say something like if the 19th century was a century of machines, but they were all backstage in the factory and never appeared in the world of everyday life. And then the 20th century brought all the machines into, we're living now with the machines. So to some extent, I feel that the 20th century at the same time was building underneath in the back rooms, robots, machine intelligence, computational intelligence. And maybe the 21st century is now the century where these things become part of our lives and we're living with robots, machine intelligence, and so on. And that's what is one of the aspects of this signifies. And if you see that kind of technology transfer, the kinds of machines which a lot of the teams have been building, production machines. And here we have a similar effort of machine building, and now these are machines we start to live with and interact with and so on. And of course, these things are tied in with each other. And but that's where the research focuses. And I think that's an interesting one to establish. But a second thought I had, or what I want to explore and explain, and maybe where a critical moment comes in, although there is a lot of nice scenario explanation, and I commend you for that truly, also on the micro level of the team reconfiguration. I think there is a lot of hints at signaling and a semiological potency of this with respect to an action announcing and drawing people together. There could have been, and that's its own kind of, I think, interest and study in terms of the different timescales as it happens, how these chain reactions feed through from users into machines and from machines back into users, and the orchestration of multiple of these. And I commend you for you wanting to show these animation, a section where a lot of things happen simultaneously. And then you start pointing out how these things become a symbiotic and an ecological transformation. And I sometimes feel, of course, there's a restraint of this, that the actors and players, which are quite different and quite unique with the particular purposes, that they maybe don't come always close enough, that this partition is never wrapping the chairs enough, and the desks reappearing maybe on the mezzanine, etc. So there is this urge for me when I say that there is a number of moments and players, and to push further this idea of, first of all, the behavioral logics on different timescales with different loops of feedback, forward and backward, negative and positive, but also the symbiotic interplay of these. And of course it's there. But the question is in terms of, is it phonologically strong enough and is it foregrounded enough? So that would be a kind of outlook of where this project would go. But I think it is true that it is highly accomplished and result focused, and these results are pulled off, and so I'm quite happy with that, moving forward on that count. And the integration of crowds is it's just the beginning, I think, for something which is very, very strong on my mind as a research trajectory, where I'm saying if we don't have crowds in the model, it's no longer an architectural model, because that's focus on the final purposes and and if you have a series of subsystems at play, it's the subsystem of the actors, the human actors, and their interaction is what all the other stage machinery is actually about to frame, cajole, guide, inform, and make to happen.
I guess to pick up a bit on this current of conversation about, is this working? Yeah, research and design, the question would be, at what point can we claim it is either successful or not successful? And that bit I'm not so sure of, and I think maybe that's a communication issue, but I think some of these things need to be qualified, mainly through quantitative analysis perhaps. Like for me, the strongest aspect of the project is the furniture reorganizing. I think that is an interesting take on the Hertzberger model, that you now make this kinetic, and that there's a whole lot of different configurations in an office that's broken into clusters and then project teams. That becomes a very useful model. But how that actually plays out in time is not really demonstrated or qualified in relation to whether they're fixed workstations for an individual, whether they're hot desks. And I think there's a lot of questions we could ask just about that would make an interesting research project in its own right. You know, that's something DGW was working on for years, was the whole thing of the workstation and how that even impacted facade, mullion spacings and so forth. There's a lot of work that could be done just in that one panel there. But I think from the design side, very well accomplished, but from the research side, I don't see that you've yet qualified that this is the best version of the project. And I think that probably has to be qualified through some more empirical analysis of the simulations that have been done and a positioning of the relationships that operate in the office.
Maybe going on to comment a little bit further about the issues of the specific issues of the furniture and maybe screens, other pieces, is I don't see why they have to be nailed onto the building. I think that if they're migratory in the way that the people are migratory, it probably could be stronger. I'm not sure about the fold-down mezzanines. You clearly need structure for those, so perhaps that's a different conversation. But otherwise, you really could imagine a lot of this stuff migrating. And then you'd be asking yourself, who's causing it to migrate and why? And I think that in its own right could be interesting. I mean, there are arguments that people have, which is the continual view of a shake-up, that you really don't know where you're going to be, might actually allow you to be more creative than if you knew. I think that gets into very interesting territory in terms of the sociology of offices and productivity. But that would be my comment. Perhaps a further iteration would be a bit like some of the images we have of the screens, that they're almost migratory, like sailing across the landscape. It's a thought.
Well, I feel, just to come back on that, I feel that there is a certain beauty and economy in the ability to say, have these desks fixed, have that very, very simple diagram, and then yet pull off a combinatoric explosion of patterning, because that degree of stability is also useful. This could be cable, this could be electrified and so on. I agree that there could be more degrees of freedom, but what is striking here that with the limited degrees of freedom, you have a kind of surprising combinatorics pattern explosion, and there's this element of gestalt configuration which I find strong here, and in terms of what you focus on and what the units of interaction are and how this decomposes, and because you end up not seeing this tripod, you end up seeing lots of other resultant where there was a part and was a whole becomes continuously refigured, and that's just with one kind of system, and I find that quite a rewarding and another kind of thing to be teased out. It's similar with the mezzanines, and through that simple move of making them asymmetric and rotating, you get a lot of connectivity diagrams and also gestalt potential in those, and there's an economy in this between fixity and mobility and simplicity of actuation. That economy also we have to see minimum amount of effect, maximum amount of, let's say, transformable potential or capacity.
Okay, from my side anyway, I think it's a kind of moment for the project which I think is pretty interesting. I appreciate the section to kind of see these two interactive agents. What you call machine is furniture and interiority of this project, and then you have actors. Actors don't necessarily mean that they're participants, or at least willing participants. And I think the distinction between, and Stephen would know this because he's one that we've talked about this quite a lot, between reactive and interactive, between actually the mechanisms of control, all of these different things have certain affordances. And I think where research would lie in the project is in your capacity to play with this kind of architectural machine and actually discover how the crowds would be either, I mean, because at the end of the day, the work environment isn't a crowd environment. The work environment is a very task-dependent goal environment, and that's individual. Dealing with that kind of complexity, asking these things to perform different tasks. Like for me, my favorite part of the project, because I think it radically refigures an existing building, is this staircase. But mostly because when you have it in a curl state, you said, well, it'll have a different form of occupancy. It's not just a device that segregates spaces. But through that transformation, now we have a meaningful difference. And so how that can sort of be coupled, I think, are the opportunities that I think you have to search for. Some of those things, I think, when you see how it's deployed in the building, as soon as you deploy them, the question is how these things are sort of collaborating together to actually create other opportunities, right? So moments where maybe the architecture disappears in some way and we're actually witnessing these transformations is more than just a passive observer. It's a signaling that these dynamisms can coexist and people can continue to sort of occupy this kind of ecology between these things. And all my point is about is the fact that I think that you can explore these things a bit further now. Having these models in the documents about where you put the attention towards things. The animation seemed to be more of a reactive thing. But we know the human agent aspect of it, I think, is a very powerful aspect. That's what makes all of these surfaces adaptable and multi-programmed, is our capacity to recognize and to reoccupy. And I think the more that you have these transitional states question some validation, duration, and all of these other aspects, I think it opens up a very interesting territory. I think the fact if you don't do this, though, leaves too much to the imagination, which I think, honestly, by building the models to try to make these things operable, it gives you that quality. What does it mean if this thing jerks and curls up really quickly? How do people kind of respond to that? You would have to somehow evolve your human behaviors to this new environment. It's not something where habit, in terms of one signal something, always maintains that same kind of communication. So you have to learn, and the building has to learn your responses. And I think that's a territory which I think is something that should be continued.
I just want to mention, I mean, of course we can congratulate Rob for his research project getting a funded next life stage, and this is the same with this research project where I managed to get some funding and make that a more serious piece of research which aims to deliver this as a viable and marketable service within the space of 3 years, and that's this kind of result focus comes in. And I want to mention the crowd modeling has this other aspect. It's not only illustrating and animating and make clear what the meaning of a space is when you know, and just somebody turning, 6 people sitting with their back with each other being a team which communicate versus turning the other way and being a meeting, and that makes us see the space different. You can see that and intuitively and illustratively, but there's also a series of possibilities to operationalize and mathematize nearly the key criteria of success within this. For instance, if you switch the configuration, you have permeability, flows, and throughput. That could be measured, but also you have complementary actors which read signals. Now this is an information enhanced and enriched environment where actors are not only reacting to physical boundaries, channels, but there's a semiologically encoded system which brings them onto different, it gives them signaling and orientation which makes them move faster, and then you have relevant encounters. You can measure encounter frequencies, you can measure team formation, team duration, dwell times, interaction, etc., etc. There's a whole series of metrics and measures which would be highly relevant to clients, where a lot of the success of the institution and the whole purpose of this building would become an explicit set of measures and simulations, and that's the new quality of service which we're trying to deliver here, and that's also the potential of the crowds. They're not illustrative also, but they're very strategic, and I can work on the live process through live process modeling, and not just kind of in the end kind of invent it, but I'm actually strategically working on it. I'm producing it out of rules, of autonomous actors and agents given rules which are plausible, and then the outcome is not something, a keyframed animation which I'm imagining, but it's really generated out of bottom-up rules and emergent patterns, and then is measured up and in comparative setups, of course. And that's the potential of here finally operationalizing and making a soft science out of something which so far it only exists in a vague, intuitive groping of somebody with experience saying, yes, this can't, I can't work. That's a new level of expertise we're trying to develop here.
I'm proud of both of you, and we're going to move on.
everything there. You don't need to. Lisa has everything.
Georgia, if you're correcting things, Lisa needs to know.
Okay. Okay. It's just one time.
Do you want me to introduce all of us?
Yes, just to be.
Yeah, we're good. Hi, we're Team XO, and I'm Lisa. These are my teammates, Georgia, Alex, and Susan, and we're from Theo's studio. In our presentation, we will be discussing self-regulated, mobile, self-structuring systems that achieve these properties through goal-oriented communication patterns. Evo Devo has been one of our core references. With this, we have paid special attention to the process of cell differentiation within a homogeneous system. Through embedded information within the cell and communication with its environment, the cell becomes specialized over a period of time to form specific tissues, organs, and by extension, organisms that perform different tasks. We've also looked at Carl Sims' virtual creatures, which evolved to perform specific tasks such as swim, jump, and walk. Each of these tasks is goal-oriented, and the creatures set out to gain control over them. Sims is addressing a genetic language that uses nodes and connections to exhibit a variety of morphologies and behaviors. Harvard's Whitesides research group has investigated soft robotics at a singular level. They have focused on the specific soft qualities of the robots as gestures and mobility. We find this research a good foundation in soft robotics, but our emphasis has been to explore soft robotics that form higher levels of organization and populations. Festo provides another good example into soft robotics and highly controlled actuation. We find their work on jamming specifically interesting because it addresses changing material properties through actuation. What excites us about softness is that it allows for volatility, change, and redundancy in the system. It tolerates a large margin of error when it comes to connection, where many outcomes can be seen as favorable. It does not work with fixed states, but rather goes through temporary stages of varying stability, always somehow finding itself somewhere on the spectrum between liquid and solid, chaotic and ordered, and stable and unstable. Therefore, what we wanted to investigate is softness in both material and a programmatic sense, where changing the material property can create difference in an exciting and meaningful way. Having this property be part of a self-regulated system enables the system to use it as a way to deal with issues of mobility, formation, and structuring. To enable the system to deal with these issues, we use communication strategies which form different levels of organization and association inside a differentiated, interacting, high population-based machinic ecology. The participants of this ecology are two distinct body plans which divide labor and enter symbiotic relationships. It is exactly this collaborative action that further enhances their abilities and allows them to change material properties of the system locally. This in turn enables them to address more complex goals, no longer as individuals, but as codependents. The system therefore becomes an exploration into how and why these temporary relationships between body plans emerge in the ecology. The way these relationships form is based on meaningful information exchange that informs actions of the participating species that result in change of the material and behavior properties of the system.
So let's start by introducing the two already mentioned distinct body plans that encountered inside our system. The sphere and the gripper are seen as two species where the primary goal of the gripper is defining the connection, organization, and building up frameworks in the system, while the sphere is in charge of occupying and actuating these frameworks. Once this merging is achieved, they become a part of a wider array of more symbiotic modes of interaction. Starting with the sphere body plan, locomotion is achieved through inflation of compartments in its skin, which offsets its position through titling, thereby steering the sphere. Tested both computationally and physically, this model exploited softness as a means to deform its outer, soft, actuatable shell in order to achieve locomotion. The right sequence of inflation of the pockets resulted in eventual controlled mobility. With such a simple, fully symmetrical body plan, the question of how one moves became quickly resolved in the idea of continually offsetting the sphere's center of balance and enable tipping over to be a strategy into achieving directionality and steering. The mobility of the gripper was proven to be a little bit more demanding. The most basic idea of what this body plan is a radial setup where limb-like extremities extend out from a middle section which joins them into one body. The strategy now would become proper limb designed, where reaching the silicon body would allow for a limb to deform in a defined direction. Ballooning, curling, bending, and coiling, when used in sequence, allow for controlled mobility. The idea of the evolving body plan was especially taken on board for the gripper species. The only static part of the design was the idea of the radially organized limbs joined at the center, while their number and pattern was varied over time in order to find the most favorable conditions under which a gripper would successfully move. We started to test mechanical actuation, where the control was focused on releasing and sequencing valves with compressors for inflation. 5-legged gripper seemed to provide a lot of stability in movement, being balanced with two side limbs that remained unactuated, while the tripod variation became more easily steered in different directions. Triple chamber and attached limbs liberated multidirectional bending in one limb, which was before constrained to one axis of movement. Because we eventually wanted to see these body plans talking to each other, the next step was to address the problems behind interaction. The first of that was addressing materiality, such as experimenting with silicon coloring as a way to index the inflation visually, where the skin stretches, the color changes and lightens up. This change is easily indexed by RGB sensors, making others around that unit understand whether inflation is going on or not. The bend sensor studies were more concerned with the gripper body plan having a sense of its own limbs in order to know what the remaining limbs should be doing. Also indexing the property with light so that the others might be aware of it.
However, in order to truly understand the implications of communication in our system, the number of agents participating in this activity would need to be considerably magnified, which is why we turned to digital models. So leading into the part of the research concerned with high population communication, the main problem of control came down to the question of how information proliferates in our system. Therefore, we start small by defining an element with low limit of vision, able to gather only very locally based information, because interactions occur and are resolved in a highly localized level. They're effectively disabled from directly accessing and knowing what kind of global conditions they generate and inhabit. Every element can access local neighborhood metrics that become resolved in two ways, with the element either becoming a caller element, sending out signals to others to come closer, or listening element, waiting for external input for caller elements. After establishing these simple rule sets in what change can occur when, we started observing global behaviors in our globally blind system. We certainly had the ability to view the system globally, but it was very interesting to see it perform in reproducible ways which seemed to belong to the same family of behavior based on the rule set, even though the only thing each element effectively knew was its own state and that of its immediate neighbors. These simple conditions cause a seemingly anonymous behavior when deployed on a small population, but this in high population enabled us to affect consistency of strings radiating away from the deployment area, evaluate seemingly different behaviors and establish them as subsets of the same general rules, affect string thickness, or test time-sensitive rule sets which allow for gradual change. Moving on from strictly localized communication, we started to address the problem of mid-level structuring. Practically speaking, it is addressed by forming mid-level organization we call clustering, where certain elements explode their area of effect by switching the affiliation of others in their vicinity to themselves in order to begin successfully identifying as a subset of connected elements that belong to a bigger overall population. This is where the system was becoming able to recognize what part of the population was because the cluster itself was able to approximate its shape and take decision based on that knowledge.
Thinking about grouping led us back to considering what would happen physically once these two body plans started to relate to one another. Once grouped together, grippers and spheres begin the symbiotic relationship that enables the system to include structuring as an evaluation criteria. At this stage, we started considering how grippers could start connecting to one another. The viable connections included curling around others' limbs, as well as using magnetic connections which gripper limbs could actively seek out in order to connect to others. Here, the intertwining of the legs is an inexact connection option, but one that leads to many body plans that come together in various ways. The test of the embedding of the magnets further increases the ability of grippers to attach one to another. Because spheres don't have a way of attaching to one another, grippers are the ones responsible for the interfacing of the spheres. Once this is established, groups can be formed in a number of ways. Two of the ones we see here, we're exploring where grippers pick up the spheres or are being propped up by spheres. The result leads to a number of various groups that can actuate as one. We found this actuation most useful for mobility of low-level population. One unit is, however, not fixed element and can merge and share its metabolism with others. The flexibility of this design and the release of these extra grippers allow for the formation of another unit.
What is, however, particularly significant about this relationship between grippers and spheres is that a latent property of the spheres is activated once it groups with grippers. This ability is jamming, which enables the sphere to turn from inflated and soft to deflated and rigid. The infill material inside the sphere creates the ability for the sphere to structurally reinforce parts of the populations as needed, while exploiting its expansion ability to introduce deformation. With these newly established properties, a population of collaborating grippers and spheres can possess and self-regulate. Excuse me. And we started to use this material change in mid-level population to address structural principles available in the system. Setting up anonymous beginning conditions allowed us to understand the basic deformations and stable areas that would emerge inside a population based on a particular deployment of softness, rigidity, expansion, and contraction. However, because all interaction was still constrained to a plane, the challenge was to find out what kind of interaction could be expected in the z-axis movement and addresses growth. We started by deploying populations into separate seeding points, and with all the information that was available in the system, the population would start negotiating and interacting with one another. What this resulted in was a setup in which we for the first time deployed different rule sets to separate populations that would spawn unique behaviors that through mutual interaction started hinting into protospatial qualities our system could offer. In an effort to address Z movement, we started exploring a potential scenario in which grippers start constricting around spheres using their pneumatic ability to push them up, while spheres could use their jamming ability to affect the overall rigidity of these emerging stalks. This ability was enabling our system to achieve greater height without explicitly using climbing as a strategy, but rather exploiting its material properties to its advantage. As a second layer of growth, rule sets we started relating neighborhood stalks to one another in a process where they include into their development a growth bias slanting towards lonelier stalks in order to maximize the surface for receding point higher up in the population. In that way, peaks can be bridged together by gripper taxonomies and therefore create new levels for the deployment of the sphere taxonomy and stimulate further growth. Letting these rule sets play out, we observed how deployment affects growth inside of a population.
The idea of working with pre-designed blueprints is no longer the goal. The way of thinking about design problems will therefore have to become systematic. Systemic design assumes that the driver of change is interaction that enables elements to enter different relationships which are continuously made and broken, and where the flow and exchange of basic information teases out behaviors that become indicative of how a higher form of ordering in high population. Soft modular bodies for us become a window into this world of speculation about what space and space making would entail once the building element becomes animate, interacting, self-regulatory, and responding to change within itself and others of its kind. It does this not by assuming a fixed place inside an assembly, but continually computing and interpreting many levels of organization within the system, and aligning its own metabolism with the newly established conditions to enable further change and adaptation. Thank you.
So in the beginning of our studies, we did a lot of tests in terms of the leg of this gripper. We did tests in terms of the ridging within the legs and the air inputs. We embedded flex sensors in order to see how we could control the bending. Then we went into 3 different shapes of the gripper. We have the Y, the X, and the 5-legged gripper. We tested out different skin designs, such as hair or adding balls in order to lessen the friction from the surface. We tested out different connection types, so curling or connecting by magnets. And our one-to-one model, we started testing out the actuation of it mechanically. These are our kind of aggregations of the spheres and the grippers. Here we got the jamming, how the grippers kind of push up the spheres. And these were our earlier models about with the unit and the net that would encompass the cells. And these are the sphere studies, the mobility of them. So these are mobility studies of the single sphere.
Say something, and I was thinking, it would be terrible to say it's a gripping project. It's like the worst joke ever, but it really is quite a gripping thing. And what I'm struck by is before we talk a bit about the kind of performance you're teasing out of it, which is really quite jarring. I mean, how effective the kind of aggregation building into a superstructure kind of thing starts to become. But what the first question I would have is why did you take the environment out of the equation? Like, I'm struck, in fact, that's almost a classical definition of behaviors. It's the bundle, it's the pattern of movements and actions and reactions of an organism in relation to its environment. And I mention it in a way because one of the beautiful kind of tests of it would be what this stuff would do in that world we know. Like like it would really attack Mies in an interesting way. Like, and I really want to cut it loose. Like, if you could get an exhibition somewhere, these things could literally start to live in these rooms in ways that would, in part because it's a kind of fastener technology also. It has the ability to find, almost in that early Harvard example you show, of these things squeezing under a gap. And yours could, of course, jam into those and create, much like the sort of logic of chocks and bolts for rock climbers, the ability to turn an environment into a completely different kind of thing because of their material intelligence. And I just wanted to mention it because before they start climbing on one another and becoming their own thing, the fact is they've got a world in which you could cut them loose and you could get a thing that sometimes might be, you know, a bit closer to Ridley Scott's original Alien, like terrifying sort of reworking of an existing interior that's really interesting. And in the one example you show of it, it's almost like that orthogonal, ordinary, flat surface stuff that to us, we're used to reading one way, given the intelligence of these things, would start to use it in a very different way. And it could be incredibly interesting kind of test of the intelligence that's even happening at this level. And you can imagine as they learn to do that, much in an evolutionary sense, they would then start to figure out how they could start to crawl or almost do the opposite, start at a ceiling and hang themselves down, or, you know, do things that would be on their own logics, but in relation to that environment. And I think that's just, I say it only because the behavioral complexity, I think, is our theme, is the you know, that is the one demand of distinguishing movement itself from behavior. And you've got brilliant kind of movement happening in relation, obviously, to the energy that's going into the system, but the other one that you've got ready-made is almost all of these surfaces that it looks like they crawled out of to come into the world the way they did. But terrific, terrific project.
I'm going to say again what I said when I saw it before. I think these things are really exquisite, beautifully made. I think that the thing that we all might start thinking about with this is the role of the architect and the role of architecture in this. And it strikes me, it's a follow-on with the conversation about the environment, that it's almost as if you need a topology for these things to inhabit. That you kind of, if you counterpointed it with a dumb architecture, these things would actually find areas that were easier to move and more difficult and more beneficial. And that counterpoint, kind of almost like a synergy, could create an architecture of, if you like, interaction in its landscape, in a hard landscape. And then I kind of go on to the next point, which is, what's the role of the architect in relation to these objects that have accretion rules and can develop their own kind of characteristics and so on? And my view, and it's very old and naive, I think, is that the architect becomes a gardener and actually says, well, these are nice here, so let's put them over there. And these look like they're really flourishing over there, so we'll have some more over there. And one's dealing with a very much a landscape and gardening metaphor. And depending on one's take, it's either that one's being very kind of ruthless about it or allowing them to grow wild in various areas. But that's very much my own point of view. I think it's really important to have a conversation in some way along these lines.
For me, this project always takes me back to some favorites like Haus Rucker and Gunther Dominik. And for that, scale comes into it. Like this image here reminds me of an image of an inflatable with a bed and a semi-naked couple. You know the image? Great image, right? Now imagine there we have naked couples in close proximity to one another. And then a minute later, they're completely separate from one another, right? Like, the whole thing about these projects in the 60s was there was a kind of social dialogue and a questioning of how this type of soft architecture would put different context to architecture and create a different type of built environment. You know, Cooper and Blau's cloud projects as well. And I think that's something that I would like to see in the book a bit more of, is an exploration of kind of where this is going in terms of its kind of social impact. And I think it's about kind of, and Theo may disagree, I don't know, but for me it's about speculating a little bit on what scale you imagine these things to be and how they actually are in that environment. So this image, we only have 4 there, and I think that's already a really powerful image. If I imagine each one of those is at the scale of that bedroom. And then when you start to imagine these things at larger scales and you start to take Brett's comments about how they can kind of cram into spaces, then you start to go back to some of those other 60s projects where there's things like, you know, inflatable rooms, cantilevering outside of buildings as temporary extensions to other buildings. I think there's a whole lot of exciting opportunities for this project. And it's not, I mean, the work's already there. It's just about kind of how do you position this work culturally and, you know, in reference to some of these projects, I think would be a really interesting thing to do.
It makes me think of that, maybe it's the world of soft furniture, of beanbags, rolling and coalescing and coming alive, and you know, and I think that is missing here at the moment. Any dimension of this speculation. I want to compare it to, but it has its own merit because it has a higher level of complexity in the previous project in terms of the soft cube and its aggregation, and it seems to be that you're taking that, you can produce that, you reproduce that as one of a set of compositions out of these 2 elements, and they aggregate into these components, which then in the next hierarchy level become that brick which climb on each other and so on. That's the scenario. I mean, there's not the proof of concept as we had with the other one, because you have more ambitions and more complexity here. But it seems also so that the idea, I guess, of the decomposition is that then you have a variety of modules of different sizes. Yeah, maybe 6 spheres and 8 and 9, and then all the way to this kind of more monstrous slime mold amoeba creature. But yeah, I mean, things are incredibly charming, and I think what needs to be also understood then that by themselves these are also elements which have behaviors, and then there are various compositions of them, and one wonders what you know, as the 2 come together, where there's always a kind of 1 to 3 or 1 to 5, or the different concentrations of them, where these brackets are in higher concentration, less concentration. There's a whole world. But how far can we postpone that question of scaling, of a domain of application, if not yet as a starting point for exploring its functionality or its set of feedbacks in the selection process, if there is one. So that's why I find one of you had in the interim brainstorming sessions where this was started, or is it just left to the next team?
Thanks a lot for this very inspiring project, because it goes far beyond what we have today, and especially I like the animation, which is for me a kind of view in the far future. It's said that the last 1,000 years were the years of physics, and the next 1,000 years will be the years of biology. And I can imagine that, I don't know, maybe in 50, 100, 200, 300 years, we will have an environment which is much more like this, and then we don't have transportation cars anymore, we don't have houses and offices, but we have maybe really amazing robots, fluid material which is intelligent, which just enables us to open up each space we ever would like to have. And in a way it's really crazy, it's really science fiction, but what I very much like is that with your models you show that in principle it would be possible. There's a lot of work to do. You have not solved the energy problems, the control problems. There's so much to do, but I also like very much the pictures of the biological role models you showed in the very beginning. Actually, this is the proof of concept. It will be possible once if we have the material, if we have the way organisms if we could handle the way organisms live. And especially these two things. On the one hand, these science fictional animations, and on the other hand, these proof of concepts together is for me really something very inspiring.
Yeah, I think it's an amazing project, and I think the architectural side of it, personally, I think we can park that for a bit, because this is really about what's just been discussed about material, about having to get something so soft to actually become intelligent, the way they work together. There's issues, as just been explained, to solve energy problems, but there's also opportunities to actually look at introducing nanotechnology into it in terms of processes to allow them to interact, scaling them. What kind of scale are we talking about? But also, I think I said before, your video, in terms of the 3-legged and the 5-legged, you can actually do a lot more on the materials. How do they glue together? How do they interact? The only thing I would say is that, and I think it's something Brett mentioned, is by actually not defining some constraints to it. Everything works within a constraint. So there's no constraint at the moment. It's too open, which means it can go in any direction. And for the period you have, yes, it's good and it can be taken further by another group, but you need some constraint, either an environment or a parameter for it to work on, a medium. And I think that's the only thing, for me, the only cream. But as a project, I think it's fantastic in terms of, I actually like this one more than anything. Engineering-wise, because you're trying to solve nature in a way, which is fantastic.
So for instance, where there's thickness, then that obviously constrains the inflation, and then where it's weaker, you get more inflation and so forth. And we start to see a building up of capability. And I think there's some really rigorous and exciting work there that aspires to the soft robotics brief. I think that's very nice.
I think technically it's very impressive. You could see the amount of control you got, particularly on the grippers, was very impressive. But I think there's still a little way to go, but you can almost see that it's feasible and you can take that next step. I was quite interested that you had two forms in terms of the physical form, the spherical and the gripper. You also had two sociological characteristics. You had the callers and the listeners. And that those two weren't actually linked, or that thought process wasn't necessarily linked. I think there may be something that you actually have multiple layers in your societal organization, and that perhaps the top of that is the architect or the gardener, perhaps. And those perhaps tie into different representations in the physical form as well, so they can tie those roles and that thought process together. I think that's something that might be explored further.
I mean, I just had a question when you showed some of these larger swarms of creatures. You were starting to talk about, initially you said there's only local awareness of immediate elements, and of course we look at the overall pattern, and then you were talking about the idea of clusters, which are not observers clusters, but the true self-recognizing clusters. How have you implemented that, and what were the criteria of self-awareness of cluster unity?
There's two microphones. It doesn't work.
The way that we implemented clustering was, in a sense, the local interactions were no longer enough to address the system. So the sharing of information between the elements became something where multiple elements start identifying as part of one thing, and the shared information about what that thing is gives them some kind of an inkling or a hint into what they might be morphologically in terms of size or shape or how they interact with one another.
What was the criteria of individuation, of cluster individuation?
At first it was randomized, where the ability was there for every element, but then over time the elements would get discriminated against, and some would achieve more dominance over their neighbors rather than the others.
I'd like to mention one other thing. When we look at this, I mean, maybe I'm alone, but I actually anthropomorphize these things. I begin to think that these things have got kind of emotions, and they're doing things, and they're being kind and gentle and cuddly or aggressive and so on. And there's a book that you might want to look at, which is a book by a guy called Breitenberg, and it's Vehicles. Have you had a look at that in your travels? Because it describes how, through a very, very few, very simple moves about interrelationship type behaviors, you can get behaviors that are apparently very complicated and very much reflecting human ideas about greed and jealousy and love and lust, and the actual rule bases are very tiny. It's a completely different kind of line of work to self-assembling buildings, and maybe not somewhere that you want to go, but it's really interesting. It just came to mind looking at what you're doing.
Yeah, I'd just like to firstly compliment the team on the clarity of explanations. I think it's an incredibly complex project, and to explain that clearly and simply is no small achievement. But I'd quite like to pick up on 2 points. One is perhaps in a way what Stephen's raised, the question of the anthropomorphic, or anthropomorphizing the pieces. And the other is the question of the binary, the use of binary relations. So on the first, on the anthropomorphic, I'm really curious about the problematic of that, because it could potentially interfere with the potential of the project in relation to the counterintuitive. Because I was really interested when you talked about inexact connections, when you talked about the deformations where something, when it was deflated, was rigid, when something was inflated, it was soft. And then finally, when you talked about the pneumatic and the jamming as mechanisms which were not about climbing. So I think there was a suggestion there that there are things sitting or bedded in this project which will take us in directions which are not the way we think as humans. And I think that's very important. And in relation to that, I was quite interested in the question of community, where you're talking about the cooperation, again, anthropomorphic, you could say, relations of friendliness, of neighboring, of loneliness. And I was wondering whether, in fact, one should be looking at more the idea of community without community, and whether, indeed, one could take that forward. Again, the counterintuitive approach to what you have shown us. And then, so finally, in relation to all of those things, I guess I'm tempted to say, what would happen if you added in a third ingredient? Because whilst it remains in this binary relation, I don't think there's enough to disturb the problem. And I'll just leave that as a thought.
Maybe that third element is people. And I think one of the things that, at least in a lot of the research, it's being wrestled is, and maybe this goes also to the comments about environment, is of course these are relational systems and they have to address these things. And at the same time, they have a certain imperative that they also have to identify each other. I think the parts of the project which I find are quite commendable is to acknowledge that there is these two species and they have certain performance criteria, and they need each other to basically address certain ideas of goal formation and goal delivery, goal evaluation. I think the aspects of human agency and the emotive aspect, of course, is a very important way of thinking of this as a space-making strategy, as a communicative strategy. And I think that these kind of things are always kind of evolving. And so when we start to talk about strategies for addressing this, the part that I think needs development is recognizing how those goals are always going to be necessarily needing to be constructed, formalized, learned, and that has a huge important influence to evolving an intelligence within body plans. So you speak about the body plans of two discrete species, but within those species, and you started off with this with the gripper, there's a taxonomy. How many legs, an addition of a leg, what does that offer? Does it compromise a system? Does it complexify it for no need? I think there are a lot of things that I think it's important to kind of tease out, address, and then try to see how that world actually allows you to genetically and computationally engineer these things and test them in playpens which actually allow them to try to see how they resolve a particular goal. Like that part of the project I feel is something that I would try to continue if I was you. I think the aspects of the making, the ideas of how they're sort of relating to each other, they do open up trajectories. I think part of this is to try to identify where the intelligence really resides. I think moments like actually being opportunistic to see that inflation and deflation, even with a simple color pigmentation, could be a signaling device to these elements. It also becomes a transformative device of how we would recognize difference, and potentially then also starts to complexify how those differences, no matter what organization and population deployment, would be opportunities to create a more emotive kind of engagement with these things. Because in a way, they have to, and you're basically showcasing their relationship to each other. The next step of this kind of evolution is basically their relationship with us. And this kind of human-machine, human-to-human, machine-to-machine conversation, I feel the way that you can approach this in a meaningful way is to look at it through behavior. So behavior is not dependent solely on the environment. Behavior is a way for us to understand how these interrelationships are formed, that they're time-based, that they're durational, that they change, that they deal with uncertainty, latency. These are kind of, I think, things that we could try to problematize the role of architecture today by acknowledging the uncertain and the latent. And I think that that's where some of the adaptive features here, I think, play a really important role. So the communication in terms of information, and I thought, Alex, what you were mentioning is really important, that's going to change. With every meaningful organization, there has to be a way to evaluate how one creates new body plan strategies, and then now what's enabled by that. So even the idea of mobility has many, many variations. I think you've shown two of them, right? The walking, which is a very limited way of doing it, but the fact that the gripper could become a sphere and roll is an example. Like that goal can be met in different ways, but there are ones that obviously would have pattern legibility that would allow more affordances for something else because it wouldn't take so much control to drive that kind of individuated aspect, and collectively that behavior would be mitigated between its relationship to others. So I really like the fact that there's an aspect of agency. I think the aspect of computational control, no matter how challenging it is something that you need to continue to discover. There has been a lot of conversations about grant money, and Harvard, for example, gets a lot of money to do that one robot which you made. And what I really like about the fact, no matter what the brief is here, is that you can take this on board. Not only could this contribute in a certain discussion within soft robotics, but I think it has implications radically for architecture and space making and systems design. So I think that openness to try to bring those worlds together through an architectural approach to these problems, I think is commendable. So thanks. Okay, so for those who've been with us for 2 days, You're going to stick around with us for a little bit more because we have a keynote lecture of Elias Nuben from Festo, who's going to give our talk at 6 o'clock. We're going to ask everybody to leave the room so that we can reorganize this. We have enough time to go and get a drink and come back. Thanks so much.
PowerPoint crashed.
Some sound, wasn't it?
Yeah, PowerPoint crashed now, I hope.
So I can't bear PowerPoint. I do use Mac.
Just after
Yeah.
putting in
Oh
the,
no,
the
leave
plug.
it a second, it's okay. It's probably that thing where it's seeing the presenter view.
Just have a look if the video is all okay. Okay. I will talk during this video, so the sound shouldn't be too loud.
Test. Test.
Okay, welcome everybody. Just gonna catch my breath. It's kind of like 2 days of marathon, and I'm not really physically that fit these days. My name's Theodore Sparopoulos. I direct the DRL, and over the last 2 days we've had, I think, a quite engaging conversation on many kinds of subjects that have to deal with aspects of design, communication, how we sort of explore new territories of innovation, how architecture participates and facilitates ways of thinking that kind of open up, I think, new approaches to conceptualize, to spatialize, and to put forward as a kind of active engagement between a certain community that we would call the architectural and urban, that many of you actually are, and communities outside that are developing work that we feel are not only inspirational but have capacities to sort of foster new relationships. I know today is the AA Open Day, so we may have some guests to the AA community. And so if I apologize to the ones that know what the DRL is, but it's called a Design Research Lab, fundamentally because it's really a space to explore architecture and to experiment and to be unapologetic about the role that design plays. I can say in many ways we believe that design is critical. We want to interrogate a certain intellectual project, but have the accountability and the passion to sort of work through some of those problems. And that may be sometimes an uncomfortable place. The way that we work on these projects, we develop a very self-organized manner in terms of how we work together. There really isn't a hierarchy. It's more about fostering a community, about trying to explore some of the challenges and the complexities that some of the contemporary conditions actually bestow upon us, if we like them or not. And I think one of the things in ways that I think are really critical for seeing the activity and the conversations that evolved over the last 2 days is opening up that process, sharing what we have done, being part of a community that's not only here and within a domain of architecture, but actually is a community that I think has to sort of readdress a certain kind of problematic, which we're in a world full of problems, and to try to find creative solutions for them and to propose and to have potentials for alternatives, I think is probably more pressing now than ever. With that, with my staff and faculty, we try to invite critics that can help us shape things. We have an umbrella agenda which will explore certain questions over 3 or 4 years. Students will self-organize and work with us explicitly in 3 or 4 people teams that are working on these problems. We qualify architectural research as something that over 3 years, 36 to sometimes 40 teams exploring, wrestling with these problems and really trying to contribute at least what we can do as part of a larger kind of conversation. And that conversation, I think, for me has always been critical to help us shape the way that we think of the program. And I'm reminded how many years I've been here, and Patrick has been here quite a lot, so as our old guards or the old dogs of the DRL. One of the things that I think is completely inspiring is the fact that the youth that come to a place like this come because there's a certain belief that ideas should be interrogated and explored, and a certain belief, especially in a school that's so international, that coming together to work on these things, regardless of resources, regardless of finances at times, and I've been there in terms of paying back my student loans for a long time, the power of where ideas can be fostered and this idea of working together on kind of creative solutions and how much that could actually open up not only the way that we think, understand, but actually how we can communicate and evolve some of the things that we could be exploring. How we problematize things, I think, is really important, and setting up the capacity to suspend some disbelief, to open up new territories of response, to challenge the finite and the fixed, to challenge habitual sort of responses, I think is something where I feel this place still maintains a quite spirited way of approaching some of these things. We've had and continue to have every year keynote lectures. We ask, even after this marathon, our critics to speak and to share their work in the same way that the students have shared to the community that's here. And I think continue the conversation, bringing in their knowledge and their perspective through their work and their sort of ways of communicating and working, if it's through industry, if it's through practice or theory or history. And I think this year we've been quite fortunate. Yesterday we had Adam Davis from Tate Towers. Today we have Elias Nubin, who's next to me, very patiently waiting. And I think in some ways he doesn't really need an introduction from me. The work of Festo as a company has been, I think, very important. But actually the work that Elias is working on with his team, exploring concepts of bionics, seeing how actuation could actually have animate and lifelike characteristics is things that I think we could say we've drawn a lot of inspiration from. And we hope that we can, as we're sort of sharing and communicate some of the things that we're doing, continue the conversation in some way. So I don't think that there's a better way, at least for me, to complete these 2 days than with giving the platform over to Elias to please share his work with us. And with that, ask you guys to warmly welcome him to the Architectural Association.
Thanks a lot, Theo, for your kind introduction. For me, it was a really big pleasure the last 2 days to really get inspired from your work, from the students' work. And I hope I can give back a little bit during this talk and inspire you as well, and show what maybe is technically possible these days. Before I go a little deeper in some of the projects we did over the last year, I have to show 2 slides about our company. Actually, Festo is a family-owned company with about 17,000 employees. We are located close to Stuttgart in Germany, but we have subsidiaries in 36 countries and are located in 250 countries. So our main business actually is factory and process automation, and I think this picture shows quite well how it looks like today. So there's a lot of aluminium, a lot of actuators, pneumatics, electronics, mechatronical systems. All of those components are modular designs, so they can be arranged in all kind of ways, and they are optimized for high volume production. So almost each consumer goods we can buy at one time came in contact with those kind of components in order to sort, to move, to grip, to handle, to assemble, and so on. But actually we are in a very, things are changing. In Germany we are talking about Industry 4.0. This means the 4th industrial evolution. And it's a kind of paradigm shift that the production will change in the near future from a linear high volume production to a more or less processual production. This means we want to achieve that we can really flexible and economic produce minimum lot sizes. Therefore, it's very important that all the machines are really networking together, that they communicate. Also, the humans have to be connected with these systems in order to produce on-demand single pieces. And to face this situation and to get ready actually to make this paradigm shift, we also look into nature and use biology as a source of inspiration, because we believe that we can really learn a lot by studying motion, studying control, also decentralized intelligence, which you can find at animals, which I will later on explain. Adaptivity is a big keyword, also efficiency in every mouth, diagnostics and processes. So all of those things we are dealing with already in our industrial world, but we believe we can get much better in the future and we can really learn from nature. And therefore we have established in 2006, 10 years ago, the so-called Bionic Learning Network. And since then we make 3 to 4 projects each year. And we are actually an interdisciplinary core team with 7 persons at the moment. But we have the chance to work with specialists from relevant departments at Festo. So if we need some specific electronics or control engineering or so, then we just can go to the research department, for example, and then they help us. And also we have a lot of external development partners, professionals, which we are working on since years. But a really big part is to cooperate with universities and institutes. And I always have students within my group, at least 3, which are really helping us. They're staying with us 3 to 6 months a year. And together we try to find new concepts and to bring our ideas to reality. Always, when you think about the projects in the very beginning, we are very topic-driven. This means, for us, it's important that all the projects we do are in a way related to our core business. So on the first sight, it's sometimes not that easy to see. But if you look at the topics, then all the projects deal with energy efficiency. So always we try to build as lightweight as possible. We do research in flow optimization with underwater robots, for example. Function integration is a really big topic. This means how can we bring actuators and sensors in one piece, in one single piece? How can we use new technologies like laser sintering, for example, to miniaturize parts and to bring as much as functions on in very little space. Intelligent control and regulating is a big issue. Therefore, we did a lot of experience with machine learning so far, also swarm behavior, autonomous robotics, all these topics of artificial intelligence we are actually working on at the moment. But we are sure that also in the future we always will have humans in the production lines, and therefore it will be very important that we have a human technology, a human-machine cooperation. And so we're thinking about how can we assist humans, how can we use flexible structures, soft robotics, adaptive mechanisms, modular constructions, actually in order to bring humans and machines very close together without being dangerous. So over the last 10 years, we made about 45 projects, and we had our own evolution, I can say. We started with helium-filled flying objects with wing-beating mechanisms, and after showing this manta ray on a fair in 2006, a scientist from the German DLR called us and said, "Oh, you made everything right, but it should work without helium." So we decided we want to go to build a real bird. Then we came up with a smart bird, which was a cooperation with 3 teams, actually, aerodynamical teams, control engineers, and also craftsmen who built it, and model workers who designed and built it, actually, the bird itself. Then we continued with the dragonfly and autonomous systems, and last year we came up with autonomous flying butterflies, which I also will present later on. So what you see in the middle, this is our Festo DNA. This is much closer to our core business. So all those projects are dealing with handling and gripping and sorting and moving goods, actually, which we hopefully can use in the next future. And with the projects on the bottom, we also want to explore what is possible with new technologies, MID technology, energy recovery, and all these things. So in order to get the freedom to make those kind of projects, which are not always so close related to our core business, we figured out that actually we have much more objectives which our work which helps actually to we have more objectives within our work. For example, we can visualize our problem-solving competence, and we can generate enthusiasm for technology, especially for the youth. It's important for us to make Festo well known outside the engineering persons, because as a B2B company we are not really popular, so these kind of activities helps us to find new talents and to make Festo well known as an attractive employer. But I think the most important part of our work is that it helps us to create new networks, that we can discern trends in research and development. This is also the reason why I'm here and why I'm trying to get inspired in completely different fields. So actually, normally I don't come in contact with architects, but due to your openness and your very innovative research, it is also, in my opinion, very interesting for us to start networking with people from completely different disciplines. And this helps us then to develop also their ideas together with us. And then we can start in dialogue with our customers directly on the fair, and we come to completely new applications which we never thought before. And on the fair we can analyze the feedback of the customers, and this again helps us very much to expedite our product pre-development. So in a way it's quite similar to the car industry, what they do with their concept cars, bringing as much as innovative technology in a simple project and then discussing what is interesting or what is already achievable. And each year at the Hanover Fair, which is this year again in April, so very soon, we have to deliver our 3 to 4 projects. So my colleagues are really busy at home, hopefully. And after the fair, most of the projects go around the world, are represented at the trade fairs, congresses, and in our subsidiaries. We are represented in some museums. Also, once we have been in the Museum of Modern Art in New York, which we were really proud of. Then we achieve more and more social media attention. And for sure, all these marketing purposes are important for us as a company, but probably more important and more interesting is that we really come to technical solutions with this approach, which we probably never would get without starting such an open future concept thinking. And therefore we have actually a kind of process, we call it top-down process. This means an engineer or also customer from us identifies a technical problem, and together with biologists and research for solutions in nature. Or we have the so-called bottom-up process. This means biologists figure out very fascinating, interesting principles, and then we as engineers together with them try to understand these fascinating principles and just to learn from it, and hopefully in the end we come to interesting applications. And one of those bottom-up results actually is the so-called fin ray structure. It was originally found at the tail fin of many fishes, and the technical abstraction is a very simple structure. I hope you can see it here in a bit. It's just a piece of plastic, and if you press here, then it bends against the force. So this effect actually helps the fish to have a very efficient paddle, because the water pressure presses against this part of the site, and then you get this amazing movement. And in the we found this together with our network partners, I think about 12 years ago. And in the very beginning, we started with underwater robots using this kind of structure for each kind of propulsion with jellies and manta rays and fishes and penguins even. But then we found out that it can be used for adaptive cripping. So I don't know if you can see this here. There's no electronics, no control, nothing. It's just a passive structure, but by moving it against anything, it perfectly adapts to each shape. And this very simple structure actually nowadays is used in the food industry, especially if we grip things with irregular shapes, apples, potatoes, onions, and things like this. Then this structure really helps. So over the last years, we developed it further on, try to get a really high quality. And this actually is one of the hard parts in industry. We came up 11 years ago with this structure, but it took us almost 10 years to really bring it to the market, to get it foot-proof, to make it that stable, that you can handle with it thousands of pieces, millions of cycles, to make it available all over the world in 24 hours. So there are many gates actually which you have to reach to finally make a product out of it. So what we are doing is really at the very beginning, and it's an ongoing process. Another concept we figured out over the last 2 years together with students from the Design University in Oslo is our so-called flag-shaped gripper. And this is inspired by the chameleon, and I think it was about 3 years ago I gave a workshop there in Oslo, and all the students had to find any animal or plant or biological principle which they are interested in. And the students came up with the chameleon and thought, oh, this tongue mechanism is very interesting. It's the catapult mechanism actually was at the first sight the interesting part. And then after watching YouTube videos, doing some research, they figured out that actually the tip of the tongue is also very interesting, because the chameleon is able to grip all kind of shapes very fast, very secure. And this is what we need in industry as well. So we tried to find a technical abstraction and came up with this gripping device. This combines a pneumatic cylinder with a water-filled silicon cap. And actually I think it's the best way to see it in the movie. Here you see actually the natural role model. And here the technical abstraction, and it looks different, but the function actually is very similar. So we just wrap this soft water-filled silicon part about almost any part. Also, we are able to grip more than one part at once, which is also something new in industry. We can have how's it? We can just grip in a box and get almost everything out of it without a lot of control and camera tracking. Also, sorry? What do you mean? Yeah, it's strong enough to carry things like this. So it's still room for improvement for the industrial process. So sometimes the silicon cap breaks so far, so we have to improve it further on. But I think it shows that with a totally different approach than we are normally used in the engineering world, it's possible to grip with a very simple thing very many items. Another project I decided spontaneously to bring it into my presentation today is our so-called bionic handling assistant, which is inspired by the elephant trunk. And this is also a kind of soft robotic device because we have only chambers completely 3D printed in the laser sintering technique. And actually the whole trunk is made only out from three pieces, 3 parts. Each part has 3 chambers, so in total we have 9 degrees of freedom. And by precise controlling these, the pressure in these chambers quite precisely with piezo valves, we are able to move very smoothly and manipulating with this really lightweight and flexible and soft structure a very new kinematic. So again, I have to say there's a lot of know-how included and has to be developed further on in order to control those kind of systems precise, in order to make them robust enough. In a second step, we mounted it on our robotic platform, Robotino. And still, this is quite far away from being a product, but it's a handling, and it is so much different from robots we usually know with steel and gears and metal construction, that we think there's a lot of potential for the future in order to work close between human and machines. Human-machine cooperation, I said it already, is a very big issue for us. And in 2012, we built this so-called exohand in order to have a kind of interface between human and machine. And this exoskeleton hand is built up in 3D printing again. And we have 8 degrees of freedom using cylinders from Vestas, pneumatic cylinders. Therefore, in the design process, we scanned the human hand and tried to using this generative manufacturing for a perfect fit of the exoskeleton to the hand. And we have position measuring systems, proportional valves again, and advanced control algorithms. And what we want to achieve actually with this kind of exoskeleton is diverse. So on the one hand, we can have a kind of force amplification in the assembly process in order to assist persons who have to do many repetitive tasks all the time. So the workforce in Germany in the production assembling lines has an age from about 45 years in average, and they still have to work 20 years more. So it is a goal actually to assist these persons in order to make their workplace more human-friendly and to help them. Also, we can use these exoskeletons in a medical therapy. Therefore, we combined the exoskeleton with a brain-computer interface. And what you can see here at the picture on the left side, the right side is a training setup for patients who suffered a stroke. And in this training setup, actually, the patient get the order to open or to close the hand. The patient, in this case, is not able to do it again anymore because the connection from the brain to the hand is broken. But getting the order to open the hand leads to activity in the motor cortex, which we can measure. And it's fascinating actually that the activity in the brain is almost the same if you think the movement or if you really do the movement. So by thinking the movement, we get the measurements, and then we can use the exoskeleton to actively open or close the hand. And doing this many times, the patient again will be able to restore this broken connection. And finally, don't need this setup anymore after a while. Therefore, we are in a cooperation with a university hospital in Tübingen, close to Stuttgart, and hopefully they make some progress soon and can use it then for therapy. What we really built it up as a demonstrator for the fair is a force feedback for safe remote manipulation. And again, this is better to see in the video. Therefore, on the right side, you see myself with this exoskeleton glove as an interface. And on the left side, there's a robot. And the same hardware actually is mounted, but combined with a silicon hand. And I'm using virtual reality or webcams actually to navigate because I don't see the robot itself. And the motion of my hand is scanned by 3D scanners. Also, the position of my fingers are monitored all the time, and the robot and the artificial hand tries to follow. And in order to handle goods and to do this task, actually, it helps a lot if you get force feedback. And therefore, we measure the forces which do result while gripping on the robotic side, and we can transfer these forces back to the interface side, so I really can feel that I have gripped an item. I don't have tactile sensors, so I don't feel the temperature and not really precise the shape, but at least I feel if I have gripped and the force, so it makes it much easier to do this job if you got this force feedback. So this is, I think, a nice example where humans and machine really come that close together that you sometimes have the feeling you are a machine. Another project which was really advanced and in a way crazy, because many persons asked us why you came up with the kangaroo, but that it has a reason. The kangaroo is a very sympathetic and fascinating role model for very efficient, energy efficient movement. The kangaroo, for example, can speed up without using more energy. It also is able to restore a lot of the energy from the landing phase and to take it over into the next jump. And then it's in a way similar to what a rubber ball does. So if you let a piece of rubber fall from a certain height, then it comes back 90% maybe. And what we are doing here, we just add this 10% of energy to achieve the same height again. And then you just give it a one impulse at the very beginning, and it doesn't matter actually how fast it goes. It's just the parable is a little different. So this effect was actually interesting for us, because we are dealing very much with acceleration in our handling systems, and we have to stop it again. And the question is, how can we save energy and get it out of existing movements already? And the way the kangaroo does it actually is mainly with his Achilles tendon, and therefore we did a lot of research also with our biologists and anatomic studies of the kangaroo. And in our case, we combined an elastic rubber tube with pneumatic elements in order to get the power for jumping, and we added electrical drives in order to move the legs precisely. Then there's a lot of, sorry, I put the German slide in it. I haven't seen it, but I can explain it. It's a quite complex process of movement. At the very first beginning, we had to give tension to the elastic element, to the rubber tube, using our pneumatic energy. Then we changed the center of mass while moving forward, and then we have to find the very exact movement to jump. During the flight phase, we have to bring our legs in front, and this movement has to be compensated by moving the tail in the different position. And then we have to decide if we want to go on jumping or if we want to stop. And if we want to stop, then we have to absorb all the energy. If we want to continue, then we have to manage actually the landing phase very precise, and to figure out when to jump again and take the energy with us into the next jump. So it was very important to have a lightweight but robust design. The whole robot has a weight from about 7 kgs at the moment. We used a lot of sensors and control algorithms in order to stabilize the whole jump. Also, it was for us important to have all the energy with us. So we had two versions, one with a mobile compressor, which in the end was too noisy and not strong enough. And in the other version we have presented, then we had a small tank from these air gun devices actually, filled with 200 bars of pneumatic energy. And with these 200 bars, one liter about, we can make 35 jumps. And this is how it looks like actually. So in the slow motion you can see a little bit better as it works. So first of all, we're using the tail to start the movement towards the forward direction. Then we switch the valves and get the power of the pneumatic and the tension of the Achilles tendon While landing again, we use the pneumatic cylinder to absorb the energy. Pneumatic is very fast, very powerful, very lightweight, but on the other hand, very hard to control really precisely. So this is why we used servo motors in the hip to control both legs. So we have inertial sensorics, faster control device, also batteries in order to power the electrical drives. What you can imagine maybe with this project, we never are going to sell kangaroos. But we really learned a lot, and in the end of my talk I will show a short making of about our work, and then you also see how we worked on this project, and then you probably can imagine that you really learn a lot doing those kind of stuff. And also we used a gesture control device, and unfortunately we were not able to turn while jumping, so also again we looked into nature and have seen that the kangaroos as well using their tail and their arms to rotate, so we tried to copy this. And there's no connection in this case between human and kangaroo, just with our gesture device we can actually show what we want the kangaroo to do, and the kangaroo gets the signal, okay, jump towards me or rotate, and then hopefully it does what we want to. Another very advanced and very complex project we did, and we almost didn't achieve finally to make it fly, but in the end we were lucky. Also, you can see this in the making of afterwards, is our so-called dragonfly. And it's our bionic opter, so-called bionic opter, inspired by the dragonfly. And after the bird we made, I don't know if you ever heard or have seen SmartBird. It was a really popular robot, so many hits at YouTube, and it was so successful. We were really surprised at this time. It was very hard for us how to continue. And then we thought, okay, what would be the next step? And we figured out that the dragonfly actually has it's the king of flight in nature. It's able to hover in the air, even fly backward. It is very fast, very agile. It has so many features. It also has a hydraulical system in the wings, so it can adjust actually if a wing is broken a bit, then they just put a little less hydraulic material in it, and they're really very fascinating. But we tried to come as close as possible to the functions of the dragonfly, because we know you never can copy nature. So nature is ridiculous, and they're dealing with living material. We always have, so far we have to deal with that material. We just try to come as close as possible to the functions we are interested in. And therefore we figured out, in order to fly like a dragonfly, almost that agile, to hover in the air, it's important to control each wing individually. So we have in total 9 degrees of freedom. One brushless motor allows us to flap to flap with all 4 wings. We can also adjust frequency, but then we are able to rotate each wing up to 90 degrees, and we can control the amplitude of each wing. And also we had some movement with shape memory alloys with head and tail, but this was more for design purpose, not really necessarily for the flight operation. And I want to give a little detail to the technical solution we found. Actually, it looks quite simple up here, and it's explained in the animation I will show afterwards, but this is just a very short part of the film, so I try to explain it here. We have a crankshaft mechanism that allows to convert the rotating movement of the motor into a oscillating movement of the wing. But this crankshaft is not tilted with 90 degrees like it is normally done in shaving tools or things. So in this case we tilted it about 45 degrees, and this allows us to change the mechanical cross point of the crankshaft from a more distal to a more proximal position, and so we can change amplitude, and also we are able to rotate the whole wing around this crankshaft and to adjust the direction of thrust. And here you see the result. The whole robot has a weight of 175 grams. Each wing has to be controlled precisely. Therefore, we use onboard electronics in combination with inertial sensoric again. But the pilot itself gives signals like the direction of flight, for example, and then the electronics have to calculate the movement, and these mechanical parts are actually transform the signals into reality. So here you see again this crankshaft, and now we can move with a servo motor the whole part of the wing is mounted, and so we change amplitude, and while rotating the whole part we can adjust direction of thrust. And doing this very precisely together, we are able to hover in the air and to fly quite stable for about 2 minutes. So quadrocopters are more efficient so far and much easier to control. But here the big advantage actually of this flying principle is that you don't have, with the quadrocopter you always have to tilt forward or backward or left or right in order to move. In this case, the whole dragonfly stays horizontal, and everything is done just by the movement of the wings. Also, I decided to spontaneously to show this project because it might help you with your projects you did with the quadrocopters I've seen today and yesterday. In this case, we call those projects emotion spheres. We have autonomous flying systems, and we combine helium-filled ballons with propellers. And in compared to quadrocopters, we are using 8 propellers, and 4 of them are horizontal mounted, but 4 are vertical mounted. And this again helps us to fly very precise without changing the orientation of the whole part. Also, due to the helium, we have a really lightweight construction, so we can fly, if you're lucky, up to 2 hours with one balloon. Indoor, outdoor is difficult because of wind situations. And one bionicle input in this project was that in order to control the thrust very precise, we have to change the direction of the propellers, the movement of the propellers. And all propellers you can get so far are optimized in one direction, because no plane, no boat, no one actually has the need to change the direction of the propeller. So what we did, we developed an adaptive propeller with a foil in between the frame. You can see it a bit on the picture up there. And it's in a way similar to a sailing boat. So if the wind comes from the one side, then the profile moves in this direction. If the wind comes from the other side, the profile moves in this direction. And this passive effect actually we use and is a result of changing the direction of movement. Also, we have included active infrared markers and using external camera systems in order to have self-localization and fly precise. Again, it's easier to see in the video. Very small motors, also less noise. I forgot to switch on my sound. Sorry. Okay. And I think we can achieve accuracy from about 5 millimeters in this quite big space. And therefore we use, as I said already, external camera systems which only can see infrared light, but with 160 pictures a second. And on the balls we have active infrared LEDs, and this has two advantages in compared to the Vicon system probably you used in your system. We are really absolutely robust against each light situation because the infrared markers are really bright. And also we can communicate due to the flashing rhythm of the infrared light. So the system always knows exactly which LED it sees, and using triangulation we are able to know quite precisely where we are in space. Then we calculate outside the movement, or using swarm algorithms like you can see here. And then the system again tries to follow the planned path. Okay, so since this project, which was made in 2013, I think, we took a lot of effort in autonomous behavior and also cooperative behavior. And our opinion was that ants are actually the most fascinating role models for cooperative behavior. We have seen this already, I think, yesterday in one of your talks. Because ants are able, with very simple rules actually, to work together and to solve a complex task which a single one wouldn't be able to. And we think this could be one possible solution in the future in order to come to a very flexible production. So we have a certain robot. This is able to do something quite well, but together with other robots, it will be able to do something really big. And therefore, we developed our bionic ants, which are also, again, laser sintered. But afterwards, we combined the laser sintered prototype with MID, 3D MID technology. This means we are able to bring all the electrical circuits directly on the body of the plastic part. Also, we could assemble most of the electronical parts directly on the body. We attached a 3D camera system in the head in order to achieve self-localization. And we have a lot of wireless devices, all kind of sensing systems in order to communicate and to figure out where we are. This is still one of the hardest things in robotics, to know quite precise where you are. Yeah, this is how it looks like. Actually, there's no hierarchy in the system. There's no external calculation. They just know the task to move an object from one point to another point. So they have to communicate and figure out which one can pull, which one can push, how close they can come to each other. Actually, they use this pattern on the wall in order to self-localizate, to localize themselves, and they also can use their I don't know, these metal parts to charge themselves. And what is also quite new is our actuator principle. We're using piezo elements. This is actually a carbon part combined with ceramics on top. And if you apply about 300 voltage to these piezo elements, then they bend without any noise, very fast, millions of times actually if you don't overload them. But the hardest thing actually is that the movement is very tiny of these piezo elements. So it took us a lot of effort using lever systems, specific joints to achieve the movement of the legs with these more smart piezos. But piezo technology is a very important technology for us, and we're using these piezo elements in a lot of proportional valves. So we have a lot of knowledge in-house, and we won't sell ants, but we learned a lot with the piezo elements and also with swarm algorithms and cooperative behavior. I think this will be my last project. I can go a little more into detail. Also, a project from last year, our so-called emotion butterflies. And in this case, we combined what we have learned with the dragonfly and with these emotion spheres. So again, we are using the camera system, in this case, a camera system which is even a bit better in the performance. And in order to know the exact position of each dragonfly, you have to imagine that we have to use 10 cameras. Each has a resolution of 2.7 megapixels. We calculate them 160 times a second. So in total, we have to calculate 3.7 billion pixels each second in order to know where the dragonfly is at the butterfly is at the moment. And doing so, we are able to make them fly completely autonomous. So they just fly random-wise, and they try to avoid collision. And therefore, they have some rules. The biggest challenge actually was to make it really lightweight, because we have only a very, very tiny battery. We have a very low frequency of the beating wings, actually. We had to have all the electronics on board. So this is real time, it's not slow motion, this is real time. And we can fly again up to 2 minutes. But therefore we had to optimize the motors very much. We put everything away that was not absolutely needed. So the whole butterfly has a weight of 27 grams, including 2 motors and wireless connection and infrared LEDs and 2 processors and inertial sensorics. So this is really hard to make it that lightweight. Okay, so I think I've shown the newest and most advanced prototypes we did over the last years. I would like to spend some more minutes to talk a little bit about our methodology, because in a way this is quite similar to what you do and not real typical for the way engineers in industry usually work, I would say. For sure, for all this work we did, you need tools and methods and processes. You need time and money and good stuff. But what you, beside this need, you need to have the playground. You have to have the freedom and to be open. You need to have the self-confidence to show these really early stage prototypes to the decision makers. And you have to have the courage to fail. And I think this is what you also showed the last 2 days, and what you have to improve for the next time in order to ask with this simple, or not simple, but with this early prototypes actually, in combination with this really advanced simulations you do and these animations of the big picture in order to ask for money, to ask for resources. So if you finally get this, and I'm in the lucky position that after showing these early stage prototypes to our decision makers, I got some money, I got some research, I got the stuff to work on these projects. But then you still have to take the risk to fail, and to have the patience and really a lot of frustration tolerance, and always you have to believe in the project. And I think again this movie shows much more what I mean, because in the very beginning we start like this with students with actually almost no budget. The biggest thing I think always is how to get started. Again, we do a lot of prototypes, really early hands-on iterations. And then if we came to a stage like I've seen now, then we show it to the decision makers, and then if we get resources, we also use simulations and all kind of technology. But always you have to do it step by step. You have to divide the big problem into basic problems, and to find how you can come close, and then always reduce complexity. In this case, we found out that if we make the upper part of the legs as a bow, then we get a little more time on the ground. And very often it looks like this, and then continue walking and believe in the project. And then if you're lucky, and actually we were lucky over the last years, very short before the fair started, you can enjoy. And again here, this was the very beginning of the Dragonfly. We don't start flying at the very beginning. We try to find a technical abstraction of the biological role model. And therefore, it's always important to ask the right question. And also ask others if you don't feel comfortable. Accept help. In this case, we used the helium balloon because the weight was just too big at the beginning. And again, it looks very often like this. In this case, the hardware is already on a state where you think it could work. But then the control engineers have to bring in the intelligence and the control algorithms. And then you think about how to fail safe. How can you save time for repairing and invest time for developing and bringing it further on. And for sure, this is the work of many hands, many young people, not only, but a lot of very young, very enthusiastic people, and also interdisciplinary people. And maybe this can be a kind of advice to you guys. I know architects are in a way able to do everything. So I really appreciate it, and I think it's a great opportunity to start programming and to deal with quadrocopters and to make them fly. My personal experience is that there are a lot of other guys in the world, they know this much better. And if you are once able to cooperate with those guys, then it might be easier to take more time to shape the future and not to stick so much on technical problems. But I think time is not ready yet. So the way you are working now is the perfect way, because our thinking is still, we have the engineers and we have the architects and we have the designers. It's still not that much interlinked like it should be. And I think in the very beginning it helps that each discipline is open to what the other discipline does and learn from them, and then probably cooperations get much closer. And I do this kind of work 11 years now, and I'm still not able to program really. But I also understand which problems they have, and also the colleagues of mine, which are really engineers, they know our problems, and the communication is getting better and better, and the understanding is getting better and better. So it really helps to work the way you do. And the last video I show is after the fair, we bring our projects around the world, in this case to an event in Bratislava where a lot of children and young people were. And for me, it's actually the best thing if you see that they are very enthusiastic about technology. And I hope you are also in a way a bit fascinated of our work. And thanks a lot for your attention. Sorry?
How big was the ant?
Like a hand. Yeah.
Any more questions? Elias, what's your background? Let's use the microphone.
My background, actually, I'm studied industrial design, but originally I did an apprenticeship in metalworking. So I always say this because this was one of the most worthful education I had. Because what I learned at this time doing handcraft work is that you work 8 hours and at the end of the day you have to have something that you can sell to someone. And in all these industrial design studying, or also during my dissertation afterwards at the university in Stuttgart, you very often forget that the work you do has to be something worth to others, because you are so fascinated from the technology, from your ideas, from your concepts, and to have both, I think, for me it was a big advantage to know that each hour actually you work is something worth, and it helps to focus on making really make things real. So.
Any other ones?
What were the things you've made real from your those? So the use cases and things you've made from the things you demonstrated, the butterflies and the others. You said your metalworking, and maybe one thing you had to have something you were going to sell at the end of it. With all the butterflies, the dragonflies, I mean, a lot of fun.
Yeah, okay. Yeah. What we are going to sell are the gripping devices. One we sell already, the other one we going to sell. Hopefully we once will sell the elephant trunks, and still may take some time. And I think that a lot of the things we learned during all the other projects, we also can reuse in the development processes of all kind of algorithms, linear access handlings, and so on. I think you understand me not perfectly correct with what I said, that everything has to be worth money and can be sold afterwards. But in the way the work you do, this is difficult to explain for me in English. It has to be something worth in case that someone else really can use it. It's not just my presentation is done and then I put it into the rubbish cup and it's finished and I get a grade, as it is quite often in my experience in the creativity business. So many designers and architects as well, they work really hard to get the order to build it finally. So many really good work finally ends in the rubbish ton. And I think this is really hard in the creativity business to deal with that. This was my experience. So this is also maybe one reason why we have this different objectivity, different aims with our work. Yeah, it's not just in the end to have products which we can sell, but it's also to fascinate people for technology, to make it in a way that you really can communicate it, that you can show it to everyone, that you can publish it, that you can to try that the things you made, there's something in you can learn from, and you can transfer what you have learned to someone else or into another project. So this is actually what I meant, that all the work you do all the day is more worth than just what you see at the moment.
Yeah.
It's I hope this helps a bit to understand what I really meant.
Yes,
Yeah.
probably picking up from that is,
Consequential, I think. Consequential.
Yeah.
yeah, the question was that one. I mean, I can envision so many applications. So you said you're not going to sell ants or kangaroos, but I can envision so many applications that I can't believe you have already some business case behind it. I think you do, don't you?
Yeah, for many applications we don't have business cases, but again, if we show these kind of demonstrators on the fair worldwide, then we achieve two things. On the one hand, customers come to us with applications we haven't thought of. Sometimes they bring in the money to develop it further on together with us, so we probably would not invest much money to develop it, but if there's a real use case, then it helps us to speed up with development. What understand else? I forgot my second point. And also we find persons who are doing research in something similar we are doing. So it's very easy to set up new networks and to find persons where you can get even more know-how to a specific question. Yeah, maybe this answers your question. Yeah.
Incredibly inspiring, so thanks so much. This was really wonderful to watch, and the ability to bring these projects to a point of perfection, just in terms of the agenda and goal, is really incredible. And I just wanted to know two things to put that into perspective. What's the time frame for each of these? I know you're launching 3 or 4 per year, but what is the lead-up time? What's the total development time? Maybe up to the point where you show it to the directors, and then from the directors go ahead to final presentation, or whether you have an open end or whether it's a strict. And then what would be a budget for typical of these?
So actually the time from showing it to the decision makers to the fair is exactly 1 year. So this year again, at the Hanover Fair, on one day, I invite 5-6 project partners, old project partners, but also possible new project partners, and to present an idea and concept. And then afterwards we decide, would it be possible to achieve the goal within 1 year? And then we got budget and the go to do this. Now, at the moment, I'm preparing together with these potential external partners, or also with my colleagues internally, what we can do. And beside working on those projects, we still always have students, have cooperation partners where we actually do the very first proof of concept. But then, finally, 1 year, and then I come back to what Adam said yesterday. It's hard, but it helps a lot to have this absolutely fixed deadline. Yeah.
The technical question. You've got a number of demonstrators where you have essentially multi-agent behavior. Is that in the main computer and you're, as it were, informing the individual agents what to do, like the avoidance programs, or is that all on board on, say, the flying objects?
On the flying objects, we are still not able to put everything on board because of the weight. So the calculation power is not ready yet actually on board. And also the flying objects always are very fast, and they cannot just stand still if they have to calculate. So then this leads to a crash. So in this case, we have external PCs getting the position of the flying objects using the camera system. Then they calculate externally the movement and send it back. And on board again, we calculate how to move the wings in order to achieve this flying maneuver. But on the Ant, in the Ant, it was the first time that we really brought everything directly on the robot. But this is much slower, and nothing can happen if it just doesn't work. And in this case, it's still an improving process. So if under perfect conditions, if we have the right light, for example, then the ants work quite well. But as soon if we have problems with communication, or if we have some problems with the light situation or so, then it's really hard, and then we also still have a lot of problems with completely autark systems.
Is there any last questions? Looks like there's a lot. Okay.
Hello. Question I would like to ask is, you know, you show the bionic hand.
Mm-hmm.
Is there anything for the eyes? For example, many people that are elderly will suffer from macular degeneration. So is there anything that you're developing for like internal problems for the body?
Actually, at the moment we don't.
Mm-hmm.
And unfortunately, this is not easy for us to do though, so because we are not in the medical business so far. So this is not our core business. We support the university hospital, as I said, in this case study with stroke patients. And this is even hard enough for us to do this beside all the other work. So far, I have to say we don't work on this.
But some of your applications can help with this, or?
Well, I don't know so far. So if you have an idea how it could help, we could discuss this. I don't thought about this at the moment.
I don't come from an architectural and engineering background. It's just I have a macular degeneration, but I know how I lost the eyesight, so I can work back to it. I've heard something about bionic eyes, but as far as I know, for people that are totally blind, all they can see is shadows. I can see more than that, but all they've done so far is people can see shadows. So, yeah. Anyway, thank you for your attention.
Welcome.
Is there any? Sorry, I'm a deer in headlights right now.
I may know how the thing learned from the chameleon. The blue silicon to scratch these beads, is that because the pneumatic vacuum to create internal surface to catch them, or because of the material is sticky so the beads can be catched?
Yeah, actually it's a combination of some effects. We don't using vacuum, but this sticky material, silicon, wraps over something, and then you get some vacuum effects inside, because it's just sealed due to the vacuum. But the main effect actually is that we grip in a form-fitting matter, because the silicon filled with water really wraps quite precisely about every shape. And then friction, some vacuumatic effects maybe, and form-fitting matter together allows us to grip almost everything.
Yeah, I think the form fitting is very important. But it has gravity or weight, how you can make sure the form will catch them, like they will not fall from the inside.
We can't make it sure actually. So it will grip until a certain force is pulling something down, and then we will lose it. So actually, probably later on, if we develop it further on, then we will have it in different sizes and different shapes in order to grip what we really need to grip. It's not one size fits all. That's not the case actually. Yeah.
So mainly it's the material intelligence, right? Material.
Yeah.
Okay, thanks.
Okay, can we take one last question and then bring this to a wrap? There's some questions in the back. Can you guys pass the microphone?
Sorry.
One more.
Yeah.
We'll call it a day.
No problem.
Yeah, most of your projects will take on the form of animals. Do you give them individual names?
I didn't get it. Sorry. Can you help me?
Have you named the kangaroos and the ants?
Yeah. But these are internal names actually. But I can say with the ants. So we had names like Brilliant, or Dead End, or Happy End, or things like this.
Okay, can we thank Elias?
I don't.
Check Architas of Taranto.